Hello everyone, welcome to lecture 1 of CS 7015, which is the course on deep learning. Today's lecture is going to be a bit non-technical. We're not going to cover any technical concepts. We're only going to talk about a brief or partial history of deep learning. So we hear the terms artificial neural networks, artificial neurons quite often these days, and I just wanted to take you through the journey of where does all this originate from. And this history contains several spans across several fields, not just computer science. We'll start with biology, then talk about something in physics, then eventually come to computer science and so on, right? So with that, let's start. So just some acknowledgements and disclaimers. So I've taken a lot of this material from the first paper which I have mentioned on the bullet. And there might still be some errors because it dates as back as 1871, so maybe I've got some of the facts wrong. So feel free to contact me if you think some of these portions need to be corrected, and it would be good if you could provide me appropriate references for these corrections. So let's start with the first chapter, which is on biological neurons. As I said, it spans several fields, so we'll start with biology, and we'll first talk about the brain and the neurons within the brain, right? So way back in 1871, 1873, around that time, Joseph von Gerlach actually proposed that the nervous system, our nervous system is a single continuous network as opposed to a network of many discrete cells, right? So his idea was that there's this one gigantic cell sitting in our nervous system and it's not a network of discrete cells. And this theory was known as the reticular theory, right? And around the same time, there was this some breakthrough or some progress in staining techniques where Camillo Golgi discovered that a chemical reaction that would allow you to examine the neurons or the nervous tissue, right? So he was looking at this nervous tissue using some staining technique, and by looking at what you see in this figure on the right hand side, the yellow figure, even he concluded that this is just one single cell and not a network of discrete cells, right? So he was again a proponent of reticular theory. So this is about Camillo Golgi. And then interestingly, Santiago Cayal, he used the same technique which Golgi proposed, and he studied the same tissue, and he came up with the conclusion that this is not a single cell, this is actually a collection of various discrete cells which together forms a network. So it is a network of things as opposed to a single cell there, right? So that's what his theory was, and this was eventually came to be known as the neuron doctrine, although this was not consolidated in the form of a doctrine by Cayal. That was done by this gentleman. So he coined the term neuron. So now today when you think about hear about artificial neural networks or artificial neurons, the term neuron actually originated way back in 1891, and this gentleman was responsible for coining that, and he was also responsible for consolidating the neuron doctrine. So already, as you saw on the previous slide, Cayal had proposed it, but then over the years many people bought this idea, and this guy was responsible for consolidating that into a neuron doctrine. Interestingly, he is not only responsible for coining the term neuron, he is also responsible for coining the term chromosome. So two very important terms were coined by this one person, right? So now here's a question, right? So around 1906, when it was time to give the Nobel Prize in medicine, what do you think, which of these two proponents, right? There are two theories. One is reticular theory, which is a single cell, and then there's this neuron doctrine, which is a collection of cells or collection of neurons. That our nervous system is a collection of neurons. So what do you think, which of these two guys who are proponents of these two different theories, who would have got the actual Nobel Prize for medicine? So interestingly, it is given to both of them. So till 1906, in fact way later till 1950 also, this debate was not completely settled. And then the committee said, okay, both of these are interesting pieces of work. We yet don't know what the situation is actually, but these conflicting ideas have a place together. And so the Nobel Prize was actually given to both of them, and this led to a history of some kind of controversies between these two scientists and so on. And this debate surprisingly was settled way later in 1950, and not by progress in biology as such, but by progress in a different field. So this was with the advent of electron microscopy. So now it was able to see this at a much better scale, And by looking at this under a microscope, it was found that actually there is a gap between these neurons, and hence it's not one single cell, it's actually a collection or a network of cells with a clear gap between them or some connections between them, which are now known as synapses, right? So this was when the debate was settled. So now why am I talking about biology? Why am I telling you about biological neuron and so on, right? So this is what we need to understand. So there has always been interest in understanding how the human brain works from a biological perspective at least. And around this time, the debate was more or less settled that we have this, our brain is a collection of many neurons and they interact with each other to help us do a lot of complex processing that we do on a daily basis, right? Right from getting up in the morning and deciding what do we want to do today, taking decisions, performing computations, and various complex things that our brain is capable of doing, right? Now the interest is in seeing if you understand how the brain works, can we make an artificial model for that, right? So can we come up with something which can simulate how our brain works, and what's that model, and how do we make a computer do that, or how do we make a machine do that, right? So that's why I started from biological neurons to take the inspiration from biology. And now what we'll get into in the next chapter is we'll start talking about artificial intelligence, and this is titled as From the Spring to the Winter of AI. So I'm going to talk about when was this boom in AI started, or when is that people started thinking and talking about AI seriously, and what eventually happened to the initial boom and so on, right? So let's start with 1943, where, as I was saying, that there was a lot of interest in understanding how does the human brain work, and then come up with a computational or a mathematical model of that, right? So McCulloch and Pitts, one of them was a neuroscientist and the other one was a logician, right? So no computer scientists or anything at that point of time. And they came up with this extremely simplified model that just as our brain takes the input from a lot of factors, right? So now suppose you want to decide whether you want to go out for a movie or not. So you would probably think about, do you really have any exams coming up? That could be your factor X1. You could think about, is the weather good to go out? Is it raining? Would it be difficult to go out at this point? Would there be a lot of traffic? Is it a very popular movie and hence tickets may not be available and so on, right? So your brain kind of processes all this information. You might also look at things like the reviews of the movie or the IMDb rating of the movie and so on. And based on all these complex inputs, it applies some function and then takes a decision, yes or no, that, okay, I want to probably go for a movie. So this is an overly simplified model of how the brain works and what this model says is that you take inputs from various sources, and based on that you come up with a binary decision, right? So this is what they proposed in 1943. So now we have come to an artificial neuron. So this is not a biological neuron. This is how you would implement it as a machine, right? So that was in 1943. Then this kind of led to a lot of boom in our interest in artificial intelligence and so on. And I guess around 1956, in a conference, the term artificial intelligence was formally coined. And within 1 or 2 years from there, Frank Rosenwald came up with this perceptron model of doing computations, or perceptron model of what an artificial neuron could be. And we'll talk about this in detail later on the course. I'll not tell you what these things are as of now. Just think of a new model was proposed, and this is what he had to say about this model, right? So he said that the perceptron may eventually be able to learn, make decisions, and translate languages. Do you find anything odd about this statement? Yeah, so learn and make decisions makes sense, but why translate languages? Why so specific? Why such a specific interest in languages? Right? So that you have to connect back to history, right? So this is also the period of the Cold War, and there was always a lot of interest. A lot of research in translation was actually fueled by the World War and events that happened after that, where these countries which were at loggerheads with each other, they wanted to understand what the other country is doing, but they did not speak each other's language. So that's why there was a lot of interest from espionage point of view or from spying and so on to be able to translate languages, and hence that specific required. And a lot of this research would have been funded from agencies which are interested in these things, right? In the defense or war or something. Okay. So, and this work was largely done for the Navy. And this is an extract from the article written in New York Times way back in 1957 or 58, where it was mentioned that the embryo of this perceptron is an embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So I'm not quoting something from 2017 or 18. This is way back in 1957-58, right? And that's why I like the history part of it. So recently there's a lot of boom or a lot of hype around AI, that AI will take over a lot of things, it will take over jobs, it might eventually, we might be colonized by AI agents and so on. So I just want to emphasize that I don't know whether that will happen or not, but this is not something new. We have been talking about the promise of AI as far back since 1957, 1958, right? This is not something new that people are talking about now. It's always been there, and to what extent this promise will be fulfilled is yet to be seen. And of course, as compared to 1957-58, we have made a lot of progress in other fields which have enabled AI to be much more successful than it was earlier. For example, we have much better compute power now. We have lots of data now thanks to the internet and other things, that you can actually crawl tons and tons of data and then try to learn something from a data, or try to make the machine learn something from data, right? So we have made a lot of progress in other aspects, because of which AI is now at a position where it can really make a difference. But just wanted to say that these are not things which have not been said in the past. It has always been that AI has always been considered to be very promising and perhaps a bit hyped also, right? So that's about 1957-58. Then now what we talk about nowadays, or for the past 8 to 10 years at least, when we talk about AI, we're talking about deep learning, and that is what this course is about, largely about deep learning. I'm not saying that other. And what deep learning is largely about, if I want to tell you in a very layman nutshell term, is it's about a large number of artificial neurons connected to each other in layers and functioning towards achieving certain goal, right? So this is like a schematic of what a deep neural network or a feed-forward neural network would look like. Now this is again not something new which has come up in the last 8 to 10 years, although people have started discussing it a lot in the last 8 to 10 years. Look at it way back in 1965-68, proposed something which looked very much like a modern deep neural network or a modern feed-forward neural network. And in many circles, he is considered to be one of the founding fathers of modern deep learning, right? So that's about that. 68, right? From 1943 to 1968, it was mainly about the springtime for AI. And what I mean by that everyone was showing interest in that. The government was funding a lot of research in AI, and people really thought that AI could deliver a lot of things on a lot of fronts for various applications, healthcare, defense, and so on. And then around 1969, an interesting paper came out by these two gentlemen, Minsky and Papert, which essentially outlined some limitations of the perceptron model, right? And we'll talk about these limitations later on in the course, in the second or third lecture. But for now, I'll not get into the details of that. But what it said, that it is possible that a perceptron cannot handle some very simple functions also. So you're trying to make the perceptron learn some very complex functions, because the way we decide how to watch a movie is a very complex function of the inputs that we consider. But even a simple function like XOR is something which a perceptron cannot be used to model. That's what this paper essentially showed. And this led to severe criticism for AI, and then people started losing interest in AI, and a lot of government funding actually subsided after 1969 all the way to 1986 actually. This was the AI winter of connectionism, so there was very little interest in connectionist AI. So there are two types of AI, one is symbolic AI and the other is connectionist AI. So whatever we are going to study in this course about neural networks and all, that probably falls in the connectionist AI paradigm, and there was no interest in this, and people, I mean, it's hard to get funding and so on for these 17 to 18 years, and that was largely triggered by this study that was done by Minsky and Papert. And interestingly, they were also often misquoted on what they had actually said in their paper. So they had said a single perceptron cannot do it. They in fact said that a multi-layer network of perceptrons can do it, but no one focused on the second part, that a multi-layer network of perceptrons. People started pushing the idea that a perceptron cannot do it, and hence we should not be investigating it and so on, right? So that's what happened for a long time, and this is known as the winter, or the first winter. Then around 1986 actually came this algorithm which is known as backpropagation. Again, this is an algorithm that we are going to cover in a lot of detail in the course in the 4th or 5th lecture. And this algorithm actually enables to train a deep neural network, right? So a deep network of neurons is something that you can train using this algorithm. Now, this algorithm was actually popularized by Rumelhart and others in 1986, but it was not completely discovered by them. This was also around in various other fields. So it was there in I think in systems analysis or something like that. It was being used for other purposes in a different context and so on. And Rumelhart and others in 1986 were the first to kind of popularize it in the context of deep neural networks. And this was a very important discovery because even today, all the neural networks or most of them are trained using backpropagation, right? And of course, there have been several other advances, but the core remains the same, that you use backpropagation to train a deep neural network, right? So something this was discovered almost 30 years back is still primarily used for training deep neural networks, right? That's why this was a very important paper or breakthrough at that time. And around the same time, so again, interestingly, so backpropagation is used in conjunction with something known as gradient descent, which was again discovered way back in 1847 by Cauchy, and he was interested in using this to compute the orbit of heavenly bodies, right? Because that is something that people cared about at that time. Today, of course, we use it for various other purposes, one of them being discovering cats in videos, or even for medical imaging, or for discovering whether a certain type of cancer is being depicted in a X-ray or things like that. There's a lot of other purposes for which deep neural networks and hence backpropagation, gradient descent, and other things are being used for. Right? But again, these are not very modern discoveries. These are dated way back 30 years, and even gradient descent is almost 150 years and so on. Right? So that's what I wanted to emphasize. And around the same time in 1990 or 1989, there was this another interesting theorem which was proved, which is known as the universal approximation theorem. And this is again something that we'll cover in the course, in the third lecture or something like that, where we'll talk about the power of a deep neural network, right? So again, the importance of this, or why this theorem was important, will become clear later on when we cover it in detail. But for now, it's important to understand that what this theorem said is that if you have a deep neural network, you could basically model all types of functions, continuous functions, to any desired precision. So what it means in very layman terms is that if the way you make decisions using a bunch of inputs is a very, very complex function of the input, then you can have a neural network which will be able to learn this function, right? In very layman terms, that is what it means. And if I have to hype it up a bit, or I have to say it in a very enthused and excited manner, I would say that basically it says that deep neural networks can be used for solving all kinds of machine learning problems, right? That's roughly what it says, but with a pinch of salt and a lot of caveats, but that is what it means, at least in the context of this course, right? So this is all around 1989, and despite this happening, right, some important discoveries towards the late end of 80s, which was backpropagation universal approximation theorem, people were still not being able to use deep neural networks for really solving large practical problems, right? And a few challenges there was, of course, the compute power at that time was not at a level where it could support deep neural networks. We did not have enough data for training deep neural networks. And also in terms of techniques, while backpropagation is a sound technique, it used to fail when you have really deep neural networks. So when people tried training a very deep neural network, they found that the training does not really converge, the system does not really learn anything, and so on. And there were certain issues with using backpropagation off the shelf at that time, because of which it was not very successful, right? So again, despite these slight boom around 86 to 90, where some important discoveries were made, and even follow up in 92, 93, and so on, there's still not a real big hype around deep neural networks or artificial neural networks at that time. There was again a slump, a slow winter right up till 2006, when this deep revival happened, right? So in 2006, a very important study was, or a very important contribution was made by Hinton and Salakut Dinov, sorry if I have not pronounced it properly, and they found that a method for training very, very deep neural networks effectively. Now again, the details of this are not important, we will be doing that in the course at some point, but what is the important takeaway here is that while from 1989 to 2006, we knew that there's an algorithm for training deep neural networks and they can potentially be used for solving a wide range of problems, because that's what the universal approximation theorem said. But the problem was that in practice, we were not being able to use it for much, right? It was not easy to train these networks. But now with this technique, there was a revived interest and hope that now actually you can train very, very deep neural networks for a lot of practical problems. So that sparked off the interest again. And then people started looking at all sorts of things, right? And even this particular study, which was done in 2006, was actually very similar to something done way back in 91, 93, and which again showed that you can train a very, very deep neural network. But again, due to several factors, maybe at that time, due to the computational requirements or the data requirements or whatever, I'm not too sure about that, it did not become so popular then. But by 2006, probably the stage was much better for these kind of networks or techniques to succeed. So then it became popular in 2006. And then this 2006 to 2009, people started gaining more and more insights into the effectiveness of this discovery made by Hinton and others, which was this unsupervised pre-training, right? That's what I spoke about on the previous slide, unsupervised pre-training. And they started getting more and more insights into how you can make deep neural networks really work, right? So they came up with various techniques, some of which we are going to study in this course. So this was about how do you initialize the network better, what is a better optimization algorithm to use, what is a better regularization algorithm to use, and so on. So there were many things which started coming out in this period 2006 to 2009, and by 2009 everyone started taking note of this, and again deep neural networks or artificial neural networks started becoming popular. That is when people realized that all this all the negative things that were tied to it, that you are not able to train it well and so on, have slowly, people have started finding solutions to get by those, and maybe we should start again focusing on the potential of deep neural networks and see if they can be used for large scale practical application, right? So this 2006 to 2009 was again a slow boom period where people were again trying to do a lot of work to popularize deep neural networks and get rid of some of the problems which existed in training them. And now from 2009 onwards, there was a series of successes which kind of which made everyone to stand up and take notice, right? That this is really working for a lot of practical applications, starting with handwriting recognition. So around 2009, these guys won a handwriting recognition competition in Arabic, and they did way better than their competitor systems using a deep neural network. And then there was success. So this was in handwriting recognition. Then there was speech. So it was shown that various existing systems, the error rate of these systems could be significantly reduced by using deep neural networks or plugging in a deep neural network component to existing systems, right? So this was handwriting, then speech, then again some kind of pattern recognition, which was on handwritten digit recognition for MNIST. This was a very popular data set which had been around since 98, and a new record was set on this data set, right? So this is the highest accuracy that was achieved on this data set around that time in 2010. And this is also the time when GPUs enter the scene, right? So before that, all of this stuff was being done on CPUs, but then people realized that very deep neural networks require a lot of computation, and a lot of this computation can happen very quickly on GPUs as opposed to CPUs. So people started using GPUs for training, and that drastically reduced the training and inference time. So that was again something which sparked a lot of interest, right? Because even though these were successful, they were taking a lot of time to train, but now with GPUs you could even take care of that. And this success continued, so people started gaining or getting success in other fields like visual pattern recognition. So this was a competition on recognizing traffic signboards, and here again a deep neural network did way better than its other competitors. And then the most popular, or the one thing which made neural networks really popular, was this ImageNet challenge, which was around since 2008 or 2009. And before 2012, when this LXNet was one of the participating systems in this competition, most of the systems are non-neural network based systems. And this competition is basically about classifying a given image into one of 1,000 classes, right? So this could be an image of a bird or a dog or a human or car, truck, and so on. So you have to identify the right class of the main object in the image, right? So, and in 2012, this LXNet, which was a deep neural network or a convolutional neural network based system, was able to actually outperform all the other systems by a margin of 6 to 7%, right? So the error for this system was 16%, and this was a deep neural network because it had 8 layers. the next year this was improved further and something known as ZFNet was proposed, which was again 8 layers, but it did better than LXNet. The next year even a deeper network with 19 layers was proposed, which did significantly better than LXNet. Then Google entered the scene and they proposed something which was 22 layers and again reduced the error. Then Microsoft joined in and they proposed something which had 152 layers, and the error that you see here is actually better than what humans do, right? So even if a human was asked to label this image, because of certain noise in the image and so on, even a human is bound to make more errors than 3.6%, right? That means even if you show 100 images to humans, he or she is bound to go wrong on more than 3 or 4 of these images, right? Whereas this system was able to get an error of 3.6% over the large test set. So this 2012 to 16 period where there was this continuous success on the ImageNet challenge, as well as success in other fields like natural language processing, handwriting recognition, speech and so on. So this is the period where now everyone started talking about deep learning and a lot of companies started investing in it. A lot of the traditional systems which were not deep neural network based people started converting them to deep neural network based systems, right? So translation systems, speech systems, image classification, object detection and so on. There were a lot of successes in all these fields using deep neural networks, right? And this particular thing that we are talking about, which is ImageNet, and the success in this was driven by something known as convolutional neural networks. I'll talk about the history of convolutional neural networks, and I call this part of history as CATS, and it will become obvious why I call it so. So around 1959, Hubel and Wiesel did this famous experiment. There's still, I think you could see some videos of it on YouTube, where there was this cat and there was a screen in front of it, and on the screen there were these lines being displayed at different locations and at different orientations, right? So slanted, horizontal, vertical and so on, and there were some electrodes fitted to the cat, and they were trying to measure that which parts of brain actually respond to different visual stimuli, right? So if you show it stimulus at a certain location, does a different part of the brain fire and so on, right? So, and one of the things of outcomes of the study was that that different neurons in brain fire to only different types of stimuli. It's not that all neurons in brain always fire to any kind of visual stimuli that you give to them, right? So this is essentially roughly the idea behind convolutional neural networks, starting from something known as neocognitron, which was proposed way back in 1980. You could think of it as a very primitive convolutional neural network. I'm sure that most of you have now read about or heard about convolutional neural networks, but something very similar to it was proposed way back in 1980. And what we know as the modern convolutional neural networks, maybe I think Jan LeCun is someone who proposed them way back in 1989, and he was interested in using them for the task of handwritten digit recognition. And this was again in the context of postal delivery services, right? So a lot of PIN codes get written or phone numbers get written on the postcards, and there was a requirement to read them automatically so that they can be, the letters or postcards can be separated into different categories according to the postcard and according to the postal code and so on, right? So, or the PIN code. So that's where this interest was there, and 1989 was when this convolutional neural networks were first proposed or used for this task. And then over the years, several improvements were done to that. And in 1998, this now famous dataset, the MNIST dataset, which is used for teaching deep neural networks courses or even for initial experiments with various neural network based networks. This is one of the popular datasets which is used in this field, and this was again released way back in 1998, and even today, even for my course, I use it for various assignments and so on. So it's interesting that an algorithm which was inspired by an experiment on cats is today used to detect cats in videos. Of course, among other various other things. It's just I'm just jokingly saying this. So now, so this is what the progression was, right? That in 2006, people started, or this study by Hinton and others led to this revival, and then people started realizing that deep neural networks can actually be used for a lot of practical applications and actually beat a lot of existing systems. But there are still some problems, and we still need to make these systems more robust, faster, and even scale higher accuracies and so on, right? So in parallelly, while there was a lot of success happening from 2012 to 2016 or even 2010 to 2016. In parallel, there was also a lot of research to find better optimization algorithms which could lead to better conversions, better accuracies. And again, some of the older ideas which were proposed way back in 1983. Now, this is again something that we'll do in the course. So, most of the things that I'm talking about, we are going to cover in the course. So, we are going to talk about the ImageNet challenge. We're going to talk about all those networks, the winning networks that I had listed there, LXNet, ZFNet, GoogleNet, and so on. We're going to talk about Nesterov gradient descent, which is listed on this slide, and many other better optimization methods which were proposed starting from 2011. So there was this parallel research happening while people were getting a lot of success using traditional neural networks. There was also interest in making them better and robust and lead to faster conversions and better accuracies and so on. So this led to a lot of interest in coming up with better optimization algorithms, and there was a series of these proposed starting from 2011. So AdaGrad is again something that we'll do in the course, RMS Prop, Adam, Eve, and many more, right? So many new algorithms have been proposed, and in parallel a lot of other regularization techniques or weight initialization strategies have also been proposed, for example batch normalization or Xavier initialization and so on. So these are all things which were aimed at making neural networks perform even better or faster and even reach better solutions or better accuracies and so on. So this is all that we are going to see in the course at some point or the other. Okay, so I was talking about successes in image, speech, pattern recognition, even natural language processing and so on. So one interesting thing here is about sequences, right? So I'll talk about sequences now. Now sequences are everywhere when you're dealing with data. So you have time series, which is like say the stock market trends or any other kind of a series, time series. Then you have speech, which is again a series of phonemes, or you can have music, you have text, which is a series of words. You could even have videos, which are a series of images, right? One frame, each frame can be considered to be an image and so on, right? So in speech data, one peculiar characteristic of speech data is that every unit in the sequence interacts with other units, right? So words on their own may not mean much, but when you put them together into a sentence, they all interact with each other and give meaning to the sentence, right? And the same can be said about music or speech or any kind of sequence data, right? So all these elements of the sequence actually interact with each other. So there was a need for models to capture this interaction, and this is very important for natural language processing, because in natural language processing you deal with sequence of words, or all your text is, or sentences or documents are all sequences of words, right? So that is very important, and the same in the case of speech also. So if you take up any deep learning paper nowadays, it's very likely that you will come across the term recurrent neural network or LSTMs, which are long short term memory cells and so on, right? So this is also something which was proposed way back in 1986, right? So a recurrent neural network is something which allows you to capture the interactions between the elements of your sequence. I said at a very layman level, but of course we are going to see this in much more detail in the course, and this was also not something new, even though you hear about it a lot in the past 3 to 4 years. The first recurrent neural network, and what you see here is exactly very similar to what we are going to cover in the course, was proposed way back in by Jordan in 1986, and its variant was proposed by Elman in 1990. Right? So this is again not a very new idea. This has existed for some time, but now there are various factors because of which it has been possible to now start using them for a lot of practical applications. As I said, one, you have a lot of compute time, the other, you have a lot of data, and the third is now the training has stabilized a lot because of these advances which I was talking about in terms of better optimization algorithms, better regularization, better weight initializations and so on. So it's become very easy to train these networks for real world problems at a large scale, right? So that's why they have become very popular and you hear about them on a regular basis. But it's again something which was done way back. And in fact, so from 1991 to 1994, actually people are also looking at various problems with training neural networks and recurrent neural networks, and they saw that this problem, which is known as the exploding and the vanishing gradient problem, which is again something that we'll see in the course in reasonable detail. Because of this problem, it's very difficult to train recurrent neural networks for longer sequences, right? So if you have a very long sequence or a time series, you cannot really train a recurrent neural network to learn something from that. And to overcome these problems, around 1997, long short-term memory cells were proposed, and this is again something that we'll cover in the course, and this is now almost the de facto standard used for training a lot of NLP work. LSTMs are used as one of the building blocks, and another variants of LSTMs which are known as gated recurrent units and some other variants. So this is also not something new, even though they have become very popular nowadays. Like almost any article that you pick about would talk about, any article on deep learning that you pick about would talk about recurrent unit networks or LSTMs or gated recurrent units. This is not something which is new. LSTMs had come way back in 1997. But again, due to various compute and other issues which I said at that time, it was not so easy to use them. But by 2014, because of these parallel progresses which I mentioned in terms of optimization, regularization and so on, people are now able to use RNN's LSTMs for large scale sequence to sequence problems. And in particular, a very important discovery at this time, or very important model which was proposed at this time, which is the attention mechanism, which is used in a lot of deep neural networks nowadays, which enabled to deal with a lot of sequence prediction problems, or for example translation, where you have given one sequence in one language and you want to generate the equivalent sequence in another language. So this is known as a sequence to sequence translation problem. So for that, people proposed a sequence to sequence attention network, and this was one of the key discoveries which then led to a lot of adaptation of, or rather adoption of deep neural networks for NLP, and a lot of research in NLP happened which was then driven by deep neural networks. Right? So a lot of existing algorithms which are non-neural network based algorithms which are traditionally used for NLP were slowly replaced by these deep neural network based algorithms. Okay? And again, this idea of attention itself is something that was explored earlier also, somewhere around 1991 or so, and it was something known as reinforcement learning was used for learning this attention mechanism. And what attention basically tells you is that if you have a large sequence and if you want to do something with this sequence, what are the important entities of this sequence or elements of this sequence that you need to focus on, right? So this is again something that we'll look at in detail in the course. Now since I mentioned RL, so we'll go on to the next chapter, which was now becoming much more ambitious with what you can do with deep learning, and people started beating humans at their own game, quite literally. So there was this, starting with Atari games in 2015, where researchers from DeepMind showed that you could train a deep neural network to play Atari games and do much better than what humans do, right? So that is something that they were able to show on Atari games. And then people started looking at other games. So then there was this Go, and there's this popular tournament in which AlphaGo, which is a deep reinforcement learning based agent, was actually able to beat the reigning champion at that time, or one of the best players of Go at that time. And then even at poker, where something known as DeepStack, which is again a deep reinforcement learning based agent, was able to beat 11 professional poker players at this game. And then other games like Defense of Ancients and so on, which is a much more complex strategy based game, where again deep reinforcement learning based agents have shown a lot of success in beating top professional players on this game, right? So this was all happening where deep learning now started showing a lot of promise in a lot of fields, NLP, vision, speech, and again this deep reinforcement learning and so on, which led to this complete madness starting from 2013, where almost for every application the traditional methods were then overridden or kind of beaten by deep neural network based systems. So something like language modeling, which has been around since probably 1950s or so, now the reigning algorithm or the better algorithm for language modeling is now something which is based on deep neural networks. And similarly for speech recognition, a lot of work or a lot of work based on probabilistic models was done in the speech area or in the speech literature over the past 30-40 years, and now all of that has been overcome by deep neural network based solutions. Same for machine translation, a lot of interest in this field. A lot of companies now have their machine translation systems based on deep neural networks, as opposed to the earlier phrase-based statistical machine translations or the probabilistic models which were used earlier. Similarly, for conversation modeling, dialogue, a lot of new work started in dialogue post a deep learning era, where people now realize that if you have a lot of sequences of conversations, you could actually try to train a deep neural network to learn from this sequence and have conversations with humans. Of course, we are nowhere close to human level conversations. We are very, very far off from them. But in limited domains, these bots are showing some success now. Same for question answering, where you're given a question and you want to answer it either from a knowledge graph or from a document or from an image and so on. And in the field of computer vision, things like object detection, most of the reigning systems or the best performing systems nowadays are deep neural network based systems, and a lot of advances are being made on these systems in the last few years. Same for visual tracking, where you want to track the same person in a video, or image captioning, where you want to generate captions for images. For example, people upload a lot of images on Facebook, and if you want to automatically caption them, or imagine you are on a reselling site, right? Something like OLX, where you upload your furniture and you don't provide a description from that, but can the machine already automatically generate a description for it so that it's easier for a human to read what that product is and so on, right? So similarly, video captioning, you are given a video and you want to caption the main activity which is happening in that video. All of these problems are being solved using deep learning based solutions, using a combination of something known as feed forward neural networks or convolutional neural networks or recurrent neural networks and so on. Visual question answering, you are given an image and a question and you want to answer that question. Video question answering, answering questions from videos. Video summarization, so if you are given a large video and you want to generate a trailer, a sort of a trailer for that video which contains the most important frames for that video. Even these systems are based on deep learning. Then this was all about classification, recognition and so on. But now people started getting more ambitious that humans are very good at creativity. So can we use machines to be creative, right? To generate images. So now if I've seen a lot of celebrity faces, can I generate new celebrity faces? Or if I've seen a lot of bedroom images, and if I'm an architect, now can I generate new bedroom images? Can we train a machine to generate new bedroom images? So a lot of phenomenal progress or work has happened in this field in the last 4 or 5 years, starting with things like generative adversarial networks, variational autoencoders and so on. And people are now starting to seriously invest into creativity, that how to make machines creative. Again, we are far off from where the desired output, but there's still significant progress happening in this field. Generating audio, so that was about generating images. Can you generate music also? And this is again about generating images and so on. So a lot of fields have adopted deep learning now, and a lot of state-of-the-art AI systems are based on deep neural networks. But now what is needed is, after all this madness where deep learning has taken over a lot of research areas, can we now bring in some sanity to the proceedings, right? So there's really a need for sanity. And why I say that is that because there's this paradox of deep learning. So there's this interesting question that why does deep learning work so well despite having a high capacity? So deep neural networks have a very high capacity, which means they are susceptible to overfitting. So most of you would have done some course on machine learning. So there you know that overfitting is bad because you're just memorizing the training data and then you might not be able to do so well on the test data. And overfitting happens when your model has a high capacity. So even though deep neural networks have high capacity, why are they doing so well? And we'll focus on this high capacity when we talk about the universal approximation theorem and give some arguments for why deep neural networks have such a high capacity. The other thing is they have this numerical instability, right? So we spoke about this vanishing and exploding gradients, and again we'll talk about this later on in the course. So despite these training difficulties, why is it that deep neural networks perform so well? And of course they have this sharp minima, which is again could lead to overfitting. So if you look at it as an optimization problem, it's not a neat convex optimization problem. So it's a very non-convex optimization problem. So why does it still do so well? So, and it's also not very robust. So here's an example on the right hand side, the figure that you show. So the first figure is actually of a panda, and the machine is able to detect this panda with some 57% confidence, right? You have trained a machine for a lot of animal images, you have shown it a lot of animal images. At test time you show it this image, the first image that you see on the right hand side, and is able to classify this as a panda with 57% confidence. But now what I do is I add some very random noise. So that second image that you see, which has some very random pixels, if I add it to this image, I'll get a new image, right? So every pixel in this image is added to this new noise image, and I get the image which you see on the third image that you see, right? To you and me, or to any average human, this still looks like a panda. There is hardly any difference between this image and the original image. But now if you pass this to the machine, all of a sudden, instead of recognizing this as a panda, it starts to recognize it as a gibbon, and that too with 99% confidence, right? So why is it that they are not very robust? And despite this not being very robust, why are deep neural networks so successful, right? So people are interested in these questions, and people have started asking these questions, and there are no clear answers yet, but slowly and steadily there is an increasing emphasis on explainability and theoretical justifications, right? So it's not enough to say that your deep neural network works and gives you 99% accuracy. It's also good to have an explanation for why that happens. Is it that some components of the networks are really able to discriminate between certain patterns and so on? So what's going on inside the network which is actually making it work so well, right? And hopefully this will bring in some sanity to the proceedings. So instead of just saying that I applied deep learning to problem X and got 90% success, it will also make some kind of more sane arguments as to why this works and what is the further promise of this and things like that, right? So that's roughly a quick historical recap of where deep learning started and where it is today, starting all the way back from advances in biology in 1871 to recent advances till 2017 and so on in deep learning, right? And here are a few URLs, so you could take a look at this for a lot of interesting applications of recurrent neural networks. There are a bunch of startups which have come up in this space, which are working on very varied and interesting problems. And here are all the references that I've used for this particular presentation. So that's where we end lecture 1, and I'll see you again soon for lecture 2. Thank you. So welcome to lecture 2 of CS7015, which is the course on deep learning. So we'll talk about Macaulay-Pitts neuron, thresholding logic, perceptrons, and a learning algorithm for perceptrons, and talk about the convergence of this algorithm. And then we'll talk about multi-layered network of perceptrons, and finally the representation power of perceptrons. So let's start module 1, which is on biological neurons. So remember, during the history we had started all the way back in the 1880s when we spoke about biological neurons. So we'll just start there, spend a few minutes on it, and then go on to the computational models, which is Macaulay-Pitts neuron. So now this is a course on deep learning, so we are going to talk about deep neural networks. Now the most fundamental unit of a deep neural network is something known as an artificial neuron. Now the question is, why is it called a neuron, right? Where does the inspiration come from, right? So we already know that the inspiration comes from biology, and more specifically it comes from the brain, because we saw that way back in the 1890s this term neuron was coined for neural processing units, or the cells in our brain, right? So now before we move on to the computational neurons or the artificial neurons, we'll just see the biological neurons in a bit more detail, and then we'll move on from there, right? So this is what a typical biological neuron looks like. So here actually there are 2 neurons. This portion is called the dendrite, so it is used to receive inputs from all the other neurons, right? So that's the place where the input comes in. Then remember we said that in 1950s we discovered that these neurons are actually discrete cells, and there is something which connects them. So that connection is called a synapse, and it decides the strength of the connection between these 2 neurons, okay? So there's an input, there is some strength to the connection. Then once this neuron receives inputs from various other neurons, it starts processing it, right? So that's the central processing unit, which is called the soma. And once it's done this processing, it's ready to send its output to other set of neurons, right? So that output is carried on by the axon. So we have inputs, we have some weights attached to the input, we have some processing, and then an output, right? So that's what a typical biological neuron looks like. And let us see a very, very cartoonish illustration of how this works, right? How the neuron works. So our sense organs interact with the outside world, and then they pass on this information to the neuron, and then the neuron decides whether I need to take some action. In this case, the action could be whether I should laugh or not, right? Whether the input is really funny enough to evoke laughter. So if that happens, this is known as something that the neuron has fired, okay? Now, of course, in reality, it's not just a single neuron which does all this. there's a massively parallel interconnected network of neurons, right? So you see a massive network here. Now the neurons in the lower level, right? So these neurons, they actually interact with the sensory organs. They do some processing based on the inputs. So they decide whether I should fire or not. And if they fire, they transmit this information to the next set of neurons, right? And this process continues till the information is relayed all the way back. And then finally you decide whether you need to take any action or not. Again, in which this case, it should be laughter, right? So that's how it works. And when I say massively parallel interconnected network, I really mean it, because there are 10 raised to 11, which is roughly 100 billion neurons in the brain, right? Okay. Now this massively parallel network also ensures that there is some division of work. Now what do I mean by that is not that every neuron is responsible for taking care of whether I should laugh or not every neuron is responsible for processing visual data. Some neurons may process visual data, some neurons may process speech data, and so on, right? So there's this division of work. Every neuron has a certain role to play. So for example, in this cartoonish example that we took, right? So there might be this one neuron which fires if the visuals are funny, right? Whatever you're seeing is funny. There will be one neuron which finds Sheldon's speech to be funny, right? The way he speaks, so that might be funny. And there might be another neuron which actually finds the dialogue content to be funny, right? And now all of this pass on the information to the next level, and this guy would fire if at least 2 of these 3 inputs are funny, right? So that means I have some threshold based on which I decide whether to react or not, right? If it's really funny, then only I'll laugh, right? Otherwise I'll not laugh, right? So the neurons in the brain, as was obvious in the previous slide, are arranged in a hierarchy. And now we'll take a more realistic example where we look at the visual cortex. So this is the portion of the brain which is responsible for processing visual information, right? So as you see here, you have our retina from where the information starts flowing, and it goes through various levels, right? So you follow the arrows, and you will see there are several levels. There's one level here, then another here, and so on, right? So it's again, as I was trying to illustrate in that cartoon, the information is relayed through multiple layers, and then it goes all the way back to the spinal cord, which decides that in this case, I need to move the muscle, right? So that's what is being decided here, right? So the information flows through a hierarchy of layers. And in this particular case, I'm going to focus on these 3 circled layers, which are V1, V2, and AIT, right? So these actually form a hierarchy, and let's see what this hierarchy does, right? So at layer 1, you detect edges and corners. So I'm looking at you all. I just see some dots and some shapes. So that's what layer 1 recognizes. I just recognize some edges and some dots and so on. Now layer 2 tries to group all of these together and come up with some meaningful feature groups, right? So it realizes, oh, these 2 edges actually form the nose, these 2 dots actually form the eyes, and these 2 edges actually form the mouth, right? So that's a slightly higher level of processing that it is doing. And then layer 3 further collects all this and leads to higher level objects, right? So now it's realizing all these things put together is actually a human face, right? So you had edges and circles or dots, then you had some feature groups, and then the feature groups combined into objects, right? So that's how this hierarchy processes. So here's a disclaimer. I understand very little about how the human brain works, right? And what you saw is a very oversimplified explanation of how the brain works, right? What I told you is there's an input, a layer of networks which does, a network which has many layers which does some processing, and then you have an output, right? That's the very simplistic view that I gave you, which is an oversimplified version, but this version suffices for everything that we need for this course, right? This is not a biology or a neural processing course, right? So it is enough for this course. So that's where we'll end module 1. Let's start with module 2, which is about Macaulay-Pitts neuron. So as we had done this during the history lecture, way back in 1943, Macaulay and Pitts, they proposed a highly simplified computational model of the brain, right? So now let's see what's the motivation. We know that our brain is capable of very complex processing. It's capable of taking a lot of inputs from various sources and then help us take various decisions and take various actions, right? Now what if we want a computer to do this, right? We want a model which is very similar to how the brain works, or at least how we think the brain works, which takes a lot of inputs and then does some processing and helps us take a decision, right? So what they proposed is this model which will take a lot of inputs, and these inputs are all binary, okay, all these inputs that you see here. These inputs are fed to this Macaulay-Pitts neuron, which is an artificial neuron,
and it is divided into two parts, right? So the first part collects all the inputs. So remember you had these dendrites which were taking all the information from everywhere, right? So this just collects all the information, and then the second part sees what this aggregation is, right? I've collected a lot of information from all the sources. Now the second function will decide what this aggregation is, and based on that it will take a decision whether to fire or not, right? And so the output is again Boolean. If it's 0, the neuron does not fire. If it's 1, the neuron fires, right? So let's take a concrete example, right? So suppose I'm trying to make a decision whether I should watch a movie or not, right? So x1 could be, is the genre of the movie thriller? Similarly, there could be another variable, say xn, which says is the actor Matt Damon, right? So these are all various such factors, right? I could take is the director Christopher Nolan, is the music given by someone, and so on, right? So all these are probably factors which help me decide whether I want to watch this movie or not, right? And we want this neuron to help us make that decision, okay? So now what is happening here is these all inputs, right? They can be either excitatory or inhibitory. So let me tell you what is inhibitory first, right? So you are taking input from a lot of sources. Now say one of these sources or one of these inputs is, am I ill today? Am I down with fever, right? So if that input is on, irrespective of who the actor, director, or whatever is, right, I'm not going to watch the movie, right? Because I just cannot leave from my bed, right? So these are known as inhibitory inputs. Irrespective of what else is on in your input features, if this input is on, your output is always going to be 0. That means the neuron is never going to fire, right? So you could think of it as, suppose my mood is not good today, I don't feel like getting up, or if I injured my leg or anything, right? If any of these conditions is on, irrespective of what the other factors are, I'm not going to watch the movie, right? So that's an inhibitory input. An excitatory input on the other hand is not something which will cause the neuron to fire on its own, but it combined with all the other inputs that you are seeing could cause the neuron to fire. And how? So this is how, right? So these are all the inputs that your neuron is taking. All I'm going to do is I'm going to take a sum of these, right? I'm going to take a aggregation of all of these. So this, what does this count actually give me? The number of inputs which are on, right? The number of inputs which are value 1. That's all this aggregate. This is sum of all the ones in my input, right? Now, this is what G does. This is a very simple function. It's just like taking a sum of my inputs. Now, the function Y takes this as the input. That means it takes this sum as the input. And if this sum is greater than a certain threshold, then it fires. If the sum is less than a certain threshold, then it does not fire, right? So again, see what is happening here. It's same as now if you depend on the actor, director, genre, and so on, and you find, okay, at least 2 of these 3 conditions are satisfied. At least I'm happy with the actor and the director, even though the genre is not something that I care about, I'll watch the movie, right? Or you might be a very niche movie watcher who only goes to a movie if the actor matches your requirement, the director matches your requirement, and the genre and the music and everything matches your requirement, right? So your threshold in that case would be high. So this is how it is going to help you make decisions, okay? Now again, a very simplified model, and this is theta is called the thresholding parameter. That is the value which decides whether the neuron is going to fire or not. And this overall thing is known as the thresholding logic, okay? So this is what a Macaulay-Pitts neuron looks like. Now, let us implement some Boolean functions using this MP neuron. So from now on, I'll just call it MP neuron, and we'll try to implement some Boolean functions using it. Okay. So now, why are we interested in Boolean functions? Because we have overly simplified the way we take decisions, right? We are saying that the way we take decisions is we take a lot of Boolean inputs, is actor Matt Damon, is genre thriller, and so on, and based on that, we produce a Boolean output, right? So our inputs is all Booleans. So you have x1 to xn, which are all Booleans. And your output is also Boolean, right? So that's a Boolean function that you're trying to learn from x to y. Is that clear, right? Your x just happens to contain n different variables here, okay? And a lot of decision problems you could cast in this framework. You can just imagine, right? Whether to come for lecture today or not, again, is you could cast it depending on various Boolean inputs, right? Okay. And this is a very concise representation of the Macaulay-Pitts neuron. What it says is, it takes a few Boolean inputs, and it has a certain threshold. If the sum of these inputs crosses this thresholds, then the neuron will fire, otherwise it will not fire, okay? That's a simple representation of the MP neuron. Now suppose I'm trying to learn the AND function, okay? when would the AND function fire? All the inputs are on. So what should be the value of the threshold in this case? 3. Everyone agrees? Right? Okay. What about the OR function? 1. Okay. Let's see a few more. This function. So let me tell you what this function is, right? So this, you see this circle here, right? So what that means is that this input is a inhibitory input. If that is on, then the neuron is not going to fire, right? That's how I'm representing it. So now tell me, what should the threshold for this be? It's not so hard. See, if x2 is on, it's not going to fire, right? So you have 4 rows, 0, 0, 0, 1, 1, 0, 1, 1. So 2 of those are ruled out. It's not going to fire. Now out of the remaining 2, when do you want it to fire? So what should be the threshold? 1. Everyone gets that? Anyone who does not get that? Okay, good. Now what about this function? 0 or 3? 3 is not even a valid option. Okay. 0? Everyone agrees to that? Fine? Okay. And what about this? 0. Okay. So you get this? So now if you have a certain number of input variables and the function that you're trying to model, the decision that you're trying to make is a Boolean function, then you could represent it using these MP neurons. Whether all Boolean functions can be represented in this way or not, that's still not clear. I'm just showed you some good examples. We'll come to the bad examples later on. Okay. Okay, here's the question, right? So can any Boolean function be represented using a Macaulay-Pitts neuron? So before answering this question, right, so we'll see a bit of a geometric interpretation of what an MP neuron is actually trying to do. Okay. So let's take the OR function where you have 2 inputs, x1 and x2, and this neuron is going to fire if x1 plus x2 is greater than or equal to 1. Right? That's clear? That's how the definition is. Okay. Now, if you look at this, right, x1 plus x2 greater than or equal to 1. Okay. Now let's ignore the greater than part first. So we'll just talk about x1 plus x2 equal to 1. What is this? Equation of a line. Everyone gets that? Okay. Now, in this case, since we are dealing with Boolean inputs and we have 2 axes, x1 and x2, how many input points can we have? 4, right? 0, 0, 0, 1, 1, 0, 1, 1, right? So we could have these 4 points. So just note that this is an x1 and x2 axis, but only 4 inputs are valid here, right? This is not a real numbered axis. Okay, there's only Boolean inputs possible here. Okay. Now, what does a line x1 plus x2 equal to 1 tell you? Which line is that? So one which passes through 1, 0 here and 0, 1 here, right? So this is that line. Okay. Now what do we want? That for all those inputs for which the output is actually 1, they should lie on the line or on the positive side on the line, right? And all those inputs for which the output is 0, they should lie on the other side of the line. Is that happening? Right? So what is actually the MP unit actually learning? A linear decision boundary, right? It just, what it is doing in effect is actually it's dividing the input points into 2 halves, such that all the points lying on that line, right, are, all the points for which the input should be 0 lie below this line, and all the points for which the output should be 1, right? Sorry, in both cases it should have been output. So let me just repeat it. All the points for which the output is 0 lie below this line, and all the points for which the output is 1 either lie on this line or above the line. Okay? Is that fine? Okay. And so let us convince ourselves about this if it is not already clear from the equation. For how many of you it's already clear from the equation that this is exactly what it does? For a large number of you, right? But still we'll just do a few examples and move ahead. Now for the AND function, what's the decision boundary? x1 plus x2. Oh no, that's the decision boundary equal to 2, right? Okay. So again I have these 4 points. Only these 4 points are possible. Now where is my decision line? Passing through that 1, 1 and intercepting this somewhere around 2, 0 and this around 0, 2, right? So that's the line which I am interested in. Okay. Now again, do you see that our condition is satisfied? That all the inputs for which we want the output to be 1 are on or above the line, and all the inputs for which we want the output to be 0 are below the line, right? Okay. Now what about this function? What's the threshold? 0. So what would the line be? x1 plus x2 equal to 0, which passes through the origin, right? And again, all the points are either on or above the line, right? So this part we are going to call as the positive half space, and this we are going to call as the negative half space, okay? So far everything is fine, okay. Now what if we have more than 2 inputs? In a 2-dimensional case, when we just had x1 and x2, we are trying to find a separating line. In the 3 dimensions case, what will we do? Plane. Okay, good. And in the higher dimensions? Hyperplane. Very good. Okay. So this is now your 3-dimensional case, right? Again, there are 3 axes here, but not all points are possible. How many points are possible? 8 points. And which is the function that we are trying to implement? All. So for these 8, out of these 8 points, for how many is the output 1? 7. And for 1 it's 0. So what is the kind of plane that we are looking at? We are looking for a plane such that 7 points lie on or above it and 1 point lies below it. And which is that point? 0, 0, 0, right? So now what's the equation of that hyperplane? x1 plus x2 plus x3 is equal to 1. Okay, good. You see this? So you see that all the 7 points are visible, but the point 0, 0 is not visible because it's on the other side of the plane, right? So this is doable in 3 dimensions also, and again in higher dimensions also, right? You could find in hyperplane. Okay. So the story so far is that a single Macaulay-Pitts neuron can be used to represent Boolean functions which are linearly separable. So a linearly separable function is such that there exists a line such that for that function, whichever points produce an output of 1 lie on one side of the line, and whichever points produce an output 0 lie on the other side of the line. This is a very informal definition. Later on we'll try to make it more formal. Okay. So is that fine? Okay. So this is where we'll end the previous module. Go to the next module, which is perceptron. Okay. So far the story has been about Boolean input, but are all problems that we deal with, we are only dealing with, or do we always only deal with Boolean inputs? So yeah, so what we spoke about is Boolean functions, right? Now consider this example. This worked fine for a movie example where we had these is actor so much and is director so and so and so on. But now consider the example where you're trying to decide, you're an oil mining company and you're trying to decide whether you should mine or drill at a particular station or not, right? Now this could depend on various factors like what's the pressure of on the surface, on the ocean surface at that point, what's the salinity of the water at that point, what's the marine aquatic life at this point, and so on, right? So these are not really Boolean functions, right? The salinity is a real number, density would be a real number, pressure would be a real number, and so on, right? And this is a very valid decision problem, right? Companies would be interested in doing this, right? So in such cases, our inputs are going to be real. But so far, Macaulay-Pitts neuron only deals with Boolean inputs, right? So we still need to take care of that limitation. Now, how did we decide the threshold in all these cases? I just asked you, you computed it and you told me, right? But that's not going to work out. I mean, it doesn't scale to larger problems where you have many more dimensions and the inputs are not Boolean and so on, right? So we need a way of learning this threshold, okay? Now, again, returning to the movie example, maybe for me, the actor is the only thing that matters and all the other inputs are not so important. Then what do I need actually? I need some way of weighing these inputs, right? I should be able to say that this input is more important than the others. Right now I'm treating all of them equal. I'm just taking a simple sum. If that sum crosses a threshold, I'm fine, otherwise I'm not fine, right? But maybe I want to raise the weight for some of these inputs or lower the weight for some of these inputs, right? So whether it's raining outside or not, maybe doesn't matter. I have a car, I could go, or I could wear a jacket or an umbrella or something, right? So that input is probably not so important, right? And what about functions which are not linearly separable, right? We have just been dealing with the goody stuff, which is all linearly separable. But we'll see that even in the restricted Boolean case, there could be some functions which are not linearly separable. And if that's the case, how do we deal with it, right? So these are some questions that we need to answer, okay? So first, we'll start with perceptron, which tries to fix some of these things, and then we'll move forward from there. So as we had discussed in the history lecture, that this was proposed in 1958 by Frank Rosenblatt, and this is what the perceptron looks like. Do you see any difference with the Macaulay-Pitts neuron? Weights, right? You have a weight associated with each of the input. Otherwise, everything seems okay, right? So this is a more general computational model than the Macaulay-Pitts neuron. The other interesting thing is that so of course we have introduced these weights, and we also have a mechanism for learning these weights. So remember, in the earlier case, our only parameter was theta, which we were kind of hand setting, right? But now with the perceptron, we'll have a learning algorithm which will not just help us learn theta, but also these weights for the inputs, right? How do I know that actor is what matters or director is what matters? Given a lot of past viewing experience, right? Given a lot of data about the movies which I've watched in the past, how do I know which are the weights to assign this, right? So we'll see an algorithm which will help us do that, right? And the inputs are no longer limited to be Boolean values. They can be real values also, right? So that's the classical perceptron, but what I'm talking about here and the rest of the lecture is the refined version, which was proposed by Minsky and Papert, which is known as the perceptron model, right? So when I say perceptron, I'm referring to this model. So this diagram also corresponds to that. Okay. So now let's see what the perceptron does. Okay. This is how it operates. It will give you an output of 1 if the weighted sum of the inputs is greater than a threshold, right? So remember that in the MP neuron, we did not have these weights, but now we have these weighted sum of the inputs. And the output is going to be 0 if this weighted sum is less than the threshold, right? Not very different from the MP neuron, right? Now I'm just going to do some trickery and try to get it to a better notation or a better form, right? So is this okay? I've just taken the theta on this side, okay? Now is this okay? Notice that here the indices were 1 to n. Now I've made it 0 to n. And the theta has suddenly disappeared. So what has happened? W0 is minus theta, right? And x0 is 1. Does anyone not get this? Right? If I just started from 1 to n, then it would be summation I equal to 1 to n wi xi plus w0 x0. But I'm just saying w0 is equal to minus theta and x0 is equal to 1, which exactly gives me back this, right? So very simple, x0 equal to 1 and w0 equal to minus theta. So in effect, what I'm assuming is that instead of having this threshold as a separate quantity, I just think that that's one of my inputs which is always on, and the weight of that input is minus theta. So now the job of all these other inputs and their weights is to make sure that their sum is greater than this input which we have, right? Does that make sense? Okay, fine. So this is how this is the more accepted convention for writing the perceptron equation, right? So it fires when this summation is greater than or equal to 0, otherwise it does not fire. Okay. Now let me ask a few questions, right? So why are we trying to implement Boolean functions? I've already answered this, but I'll keep repeating this question so that it really gets drilled in. Why do we need weights? Again, we briefly touched upon that. And why is W0, which is negative of theta, often called the bias? Okay. So again, let's return back to the task of predicting whether we would like to watch a movie or not. And suppose we base our decisions on 3 simple inputs: actor, genre, and director, right? Now, based on our past viewing experience, we may give a high weight to Nolan as compared to the other inputs. So what does that mean? It means that as long as the director is Christopher Nolan, I'm going to watch this movie irrespective of who the actor is or what the genre of the movie is, right? So that's exactly what we want, and that's the reason why we want these weights, okay? Now, W0 is often called the bias as it represents the prior. So now let me ask a very simple question. Suppose you are a movie buff. What would theta be? 0, right? I mean, you'll watch any movie irrespective of who the actor, director, and genre is, right? Now, suppose you are a very niche movie watcher who only watches those movies which the genre is thriller, the director was Christopher Nolan, and the actor was Matt Damon. Then what would your threshold be? 3, right? High in this case. Okay? I always ask this question. Do you know of any such movie? It always takes a while. Interstellar. Okay. So the weights and the bias will depend on the data, which in this case is the viewer history, right? So that's the whole setup, right? That's why we want these weights, and that's why we want these biases, and that's why we want to learn them. Okay. Now, before we see whether and how we can learn these weights and biases, one question that we need to ask is, what kind of functions can be implemented using the perceptron, and are these functions any different from the Macaulay-Pitts neuron? So before I go to the next slide, any guesses? Okay, I'm hearing some interesting answers which are at least partly correct. Okay. So this is what a Macaulay-Pitts neuron looks like, and this is what a perceptron looks like. The only difference is this red part, which is the weights which have gone added, right? So it's again clear that what the perceptron also does, it divides the input space into two halves, where all the points for which the output has to be 1 would lie on one side of this plane, and all the points for which the output should be 0 would lie on the other side of this plane, right? So it's not doing anything different from what the perceptron was doing. So then what's the difference? You have these weights, and you have a mechanism for learning these weights as well as the threshold. You are not going to hand code them. Okay. So we'll first revisit some Boolean functions and then see the perceptron learning algorithm. Okay. So now let's see. What is the first condition, right? This condition, if I actually expand it out, then this is what it turns out to be, right? And what is that condition telling me actually? W0 should be less than 0. Clear? So now based on these, what do you have here actually? What is this? A system of linear inequalities, right? And you know you could solve this, right? You have algorithms for solving this, not always, but you could find some solution, right? And one possible solution which I have given you here is W0 is equal to -1, W1 equal to 1.1, and W2 equal to 1.1. So let's just draw that line. Okay. So what's the line? It's 1.1 x1 plus 1.1 x2 is equal to 1. Okay, that's the line, and this is the line. And you see it satisfies the conditions that I have. Is this the only solution possible? No, right? I could have this also as a valid line. I could, if I could draw properly, right? All of these are valid solutions, right? So which result in different W1, W0, and W0s. Okay, so all of these are possible solutions. And in fact, I've been telling you that you had to set the threshold by hand for the Macaulay-Pitts neuron, but that's not true, because you could have written similar equations there and then decided what the value of theta should be, right? So you could try this out. For the Macaulay-Pitts neuron also, you'll get a similar set of conditions, or similar set of inequalities, and you can just say what is the value of theta that you could set to solve that, right? Okay. So that ends that module. Before we go to the next section, which is on learning, I just want to introduce the concept of errors and error surfaces and tell you how it relates to these multiple solutions that we were talking about. So for simplicity, what we'll do is we'll just set the threshold to minus W to 1, which is setting the threshold to -1. And now I'll try different values of W1 and W2. Okay, so I was saying that there are multiple values of W1 and W2 possible, and these are all real numbers, right? We are not constrained by having them as Boolean values. Okay, so now this is one solution which I tried. I tried setting W1 to -1 and W2 to -1. What is wrong with this line? Does it lead to any errors? How many? Just one error, right? So this makes an error of 1 out of the 4 inputs. Now let me just try some other values of W1 and W2. Okay, this line. Again one error. Okay, what about this line? Not 4, 3, because 0, 0 is anyways on this side of the line. Okay, so now given this, now tell me that my quest is to find these W's, right? I want to find W1, W2, and so on. Now given this discussion on errors, can you tell me a condition that I'm looking for? I want to find W1, W2, or up to Wn such that errors are minimized, and in the best case, errors are 0, right? So that's what I want, right? So this, just I want to make a case that the search for W's is driven by certain objective, and this objective is to minimize the error. Okay, fine. So now, since we're doing this, let us plot the error surface corresponding to different values of W0, W1, and W2. And once again, for simpler analysis, we'll just keep W0 to be fixed at -1. And now what I have, so just don't read this bullet as of now, even this one. So I have this W2 here, so that's my one axis, and I have W1 here, which is my another axis. Okay. Now what I'm going to do is, I'm going to try different values of W1 and W2. So this axis can go from -infinity to +infinity. Of course, for the sake of showing here, I've just had it from -4 to 4. Okay. So now what I'm going to do is, I'm searching for some values of W's, W1 and W2, so that my error is 0. And let's do a brute force, right? I'll just try every value between -4 to 4. Okay. And in fact, one of the solutions which I proposed actually was this 1.1 comma 1.1, right? That's the line which we saw on the previous slide and which led to 0 errors. And that's the dark blue surface here. So how did I compute this error? Actually, I just substituted 1.1 comma 1.1 here. And then I put in all the 4 values combinations for x1 comma x2, right? And I realized that I'm able to satisfy all of them. So I don't get any error, right? Now instead of that, if I had put something different, so let me just go back to the previous slide, which was say -1 comma -1, right? Which is, I think, somewhere around here, right? -1 comma -1, I guess. So for that, I am in this light blue region where the error was 1. So I make errors for one of the inputs, right? So it's a very brute force way of finding this, and this is not going to work, right? Because we have lots of inputs to check. But this is just to give you an intuition that we're looking at errors and we're trying to find a value of W1 comma W2 which minimize this error, okay? So that's the idea behind errors and error surfaces. We'll now go to the next module, which is the perceptron learning algorithm. And we'll now see a more principled approach of learning these weights and threshold. But before that, we'll just again revisit our movie example and make it slightly more complicated. Now here, what the situation is that we're given a list of M movies and a class associated with each movie indicating whether we like the movie or not, right? So now we have given some data of the past M movies that we have seen and whether we like this movie or not. And now instead of just 3 variables, we have these n different variables based on which we are making decisions. And notice that some of these variables are real, right? They are not Boolean anymore, right? The rating could be any real number between 0 to 1, okay? And now based on this data, what do we want the perceptron to do actually? So I've given you some data, these factors. I've also given you the label 1 and 0. So if the perceptron, if I tell you, okay, my perceptron has now learned properly, what would you expect it to do? Perfect match, right? So whenever I feed it one of these movies, it should give me the same label as was there in my data, right? And again, there are some movies for which I have a label 1, which are positive, some movies which I have a label 0. So I'm once again looking to separate the positives from the negatives, right? So it should adjust the weights in such a way that I should be able to separate, right? So that's the learning problem that we are interested in, okay? So now with that, I'll give you the algorithm. Okay, this is the perceptron learning algorithm. We have certain positive inputs which had the label 1. We have certain negative inputs which had the label 0. And now I don't know what the weights are, right? I have no prior knowledge of what the weights are going to be. I need to learn them from the data. So what I'm going to do is I'm just going to initialize these weights randomly. Right? So I'm just going to pick up some random values for this. So this should be small n. So this should be small n. And now here's the algorithm. While not convergence, do something. So before I tell you what to do, can you tell me what is meant by convergence? When will you say that it has converged? When it is not making any more errors on the training data, right? Okay, or its predictions are not changing on the training data. So that's the definition of convergence, okay? Now here's the algorithm. I pick up a random point from my data, which could either be positive or negative, right? So it comes from the union of positive and negative, basically all the data that I have. I pick up a random point from there. If the point is positive, right? And this is the condition which happens. What does this tell me? If the point was positive, what did I actually want? Greater than 0. But the condition is less than 0. That means I made an error. So I've made an error, then I'll just add x to w. I see a lot of thoughtful nodding. I hope you are understanding what is happening. Let's see. So what is w actually? A dimensional? N dimensional. N plus 1, right? Because w naught is also inside there. So actually there should be w naught also here. Right? And what is x? Again n dimensional, right? And that's why this addition is valid. So let's understand that the w and x both are n dimensional. Okay. Now let's look at the other if condition. Can you guess what the other if condition is? If x belongs to n and summation is greater than or equal to 0, then, okay, so that means you've completely understood how this algorithm works. Because that's right. So now consider two vectors w and x. So remember what we're trying to prove is, or get an intuition, not prove actually, get an intuition for why this works. Okay. So we'll consider two vectors w and x, and this is what my vectors look like. Very similar to the case that we are considering, w0 to wn and 1 to n. So this again, x naught is just 1, right? Okay. Now this condition that I've been talking about, it's nothing but the dot product. Right? How many of you have gone through the prerequisites for today's lecture? Okay, good. So it's just the dot product, okay? Now we can just rewrite the perceptron rule as this instead of the dot product. I mean, instead of using that summation thing, we can just say that it's a dot product, okay. Now we are interested in finding the line W transpose X equal to 0. So that's our decision boundary, right? Which divides the input into two halves, okay? Now every point on this line satisfies the equation W transpose X equal to 0. What does that mean actually? Yeah, so just a simple example is that if I have the line x1 plus x2 equal to 0, then all the points which lie on the line satisfy this equation, right? So you could have 1 minus 1, 2 minus 2 and so on, but 2 comma 2 cannot be a point on this line, right? Every point lying on this line satisfies this equation. So every point lying on this line actually satisfies the equation W transpose X equal to 0. So that, can you tell me what is the angle between W and any point on this line? How many of you say perpendicular? Okay, why? The dot product is 0, right? So if their dot product is 0, they are orthogonal, right? So that means if I take this line, then my vector W is orthogonal to this, it's orthogonal to this point, to this point, to this point, to every point on the line, which is just the same as saying that the vector is perpendicular to the line itself, right? As simple as that. So the angle is 90 degrees because the dot product gives you the cos alpha, and that is 0, right? And since it's perpendicular, as I said, to every point of the line, it's just perpendicular to the line itself, right? So this is what the geometric interpretation looks like. This is our decision boundary, W transpose X, and the vector W is actually orthogonal to this line. Okay? That's exactly the intuition that we have built so far, okay? Now let us consider some points which are supposed to lie in the positive half space of this line, right? That means these are the points for which the output is actually 1, okay? Now, can you tell me what is the angle between any of these points and W? Oh, you guys are actually trying to tell me the angle? You've got some measuring stuff? No, so I'll give you 3 options. Equal to 90, greater than 90, less than 90. Less than 90, it's obvious from the figure, right? Now if I take any point which lies in the negative half space, what is the angle going to be between them? Greater than 90, right? Again obvious. And it also follows from the fact that cos alpha is W transpose X by something, and we know that for the positive points, W transpose X is greater than equal to 0, right? That means cos alpha would be greater than equal to 0. That means the angle alpha would be less than 90 degrees. And for the negative points, W transpose X is actually less than 0. That means cos alpha would be less than 0. That means alpha would be greater than 90 degrees, right? So it actually follows from the formula itself, but it's also clear from the figure. So keeping this picture in mind, let us revisit the algorithm, okay? So this is the algorithm, okay? Now let's look at the first condition, which was this. Now if X belongs to P and W transpose X is less than 0, then it means that the angle between X and the current W is actually greater than 90 degrees. But what do we want it to be? Less than 90 degrees. And our solution to do this is, but we still don't know why this works. Now anyone knows why this works? Okay, so let's see why this works, okay? So what's the new cos alpha going to be? It's going to be proportional to this, right? It's going to be proportional to this. I'll just substitute what W nu is, fine. That means if cos alpha nu is going to be greater than cos alpha, what is alpha nu going to be? Less than, and that's exactly what we wanted. This angle was actually greater than 90 degrees. So we want to slowly move it such that it becomes less than 90 degrees. It's not going to get solved in one iteration, right? That's why till convergence. So we'll keep doing this, right? We'll keep picking the x's again and again till it reaches convergence. That means till we are satisfied with that condition, right? Now let's look at the other condition. X belongs to n and W transpose X was greater than equal to 0. Then it means that the angle alpha is actually less than 90 degrees, and we want it to be the opposite, okay? I'll just quickly skim over this. W minus this, X, right? Okay, I forgot to mention that this is actually a positive quantity, right? I mean, that's why that result holds, okay? That means cos alpha nu is going to be less than cos alpha. And there's slight bit of mathematical incorrectness I'm doing here, but that does not affect the final result. So I'll just gloss over that and you can go home and figure it out. But still the final, it doesn't take away from the final intuition and interpretation, right? And so now the new cos alpha is going to be less than the original cos alpha. That means the angle is going to be greater, and that's exactly what we wanted, okay? So we'll now see this algorithm in action for a toy data set. So this is the toy data set we have, and we have initialized W to a random value, and that turns out to be this, right? I just picked up some random value for W and ended up with this particular configuration for W, okay? Now, we observe that currently W transpose X is less than 0 for all the positive points and is actually greater than or equal to 0 for all the negative points. If you don't understand W transpose X, it's just that all the positive angle points actually have a greater than 90-degree angle and all the negative points actually have a less than 90-degree angle. So this is exactly opposite of the situation that we want. And now from here on, we want to actually run the perceptron algorithm, right, and try to fix this W. And how does it work? Remember, we randomly pick a point, okay? So say we pick the point P1. Do we need to apply a correction? Yes. Why? Because it's a positive point and the condition is violated, right? So now we add W equal to W plus X and we get this new W. So notice that we have a new W, okay? We again repeat this. We again pick a new point and this time we have picked P2. Do we need a correction? At least from the figure it looks like the angle is greater than 90, right? So we'll again do a correction. We'll add W is equal to W plus P, right? This X is actually, sorry, P2, and this is where we end up, okay? Now again we pick a point randomly, N1. Do we need a correction? So this is what our W is, this line here, and N1, right? So we need a correction, okay? Now what is the correction going to be? Minus. And then the W changes, okay? Now we pick another point N3. Do we need a correction? No, at least from the figure it seems like the angle is greater than 90. And we continue this, right? For N2 we don't need a correction. Now for P3 again we don't need a correction. The angle looks less than 90. Oh sorry, actually we need a correction. The angle is slightly greater than 90. And this is our correction, okay? And now we keep cycling, and now as I keep cycling over the points, I realize that I no longer need any correction, and it should be obvious from the figure that for this particular value of W, now all my positive points are making an angle less than 90 and all my negative points are actually making an angle greater than 90. That means by definition now my algorithm has converged, right? So I can just stop it. So I can just make one pass over the data. If nothing changes, I'll just say it has converged, okay? Now does anyone see a problem with this? It will never converge in some cases. So can someone tell me why? Yeah, we are considering only the cases where the data is linearly separable, right? That we already assumed. So what you're trying to tell me is that you're going over these points cyclically. So let me just rephrase and put words in your mouth. That what you're trying to tell me actually is that I take a point, I adjust the W. But now for the next point, I maybe go back to the same W because that point asks me to move it again. And I keep doing this again and again and basically end up nowhere, right? And that's why this will never converge. That's exactly what you're trying to tell me, right? Or that's exactly what I'm forcing you to tell me. So that's not the case, right? This algorithm will converge. In this module, we'll talk about the proof of convergence for the perceptron learning algorithm that we saw in the previous module. So we have some faith and intuition that it actually works. We just need to formally prove it that it actually converges, right? So that's what we're going to do in this module. So before that, a few very simple definitions. So if you have two sets of points P and N in an n-dimensional space, then we say that these points are absolutely linearly separable if there exists some n plus 1 real numbers, which are W0 to Wn, such that every point which belongs to P, right? P is the case where the output is 1. Then these set of weights satisfy this condition, right? And every point which lies in the negative set, the set of weights satisfy this condition, right? So nothing very different from what we have been saying so far. It's just formally defining it, right? Now, our proposition is that if the sets P and N are finite, and there's a fixed number of points in that, which was the case in the toy example that we were doing, and which will be the case in most examples that we do, and linearly separable, right? The perceptron learning algorithm updates the weight vector. Okay, before I go there, right? Okay, let me not give you the definition and let me ask you the definition, right? So now, given this definition, the first definition, and given this part of the proposition, can you tell me what do I need to prove if I need to prove that the algorithm converges? Okay, that's one way of looking at it. But what was happening in that wrong argument which was I was making, that it continuously kept toggling, right? That means I'm not making a finite number of updates, right? I have to keep changing again and again, and this process continues in a loop, right? So that's how I'm going to define convergence, that the perceptron learning algorithm updates a weight vector a finite number of times, right? It only needs to update it a finite number of times, and it will reach a configuration such that now it's able to separate the P from the N. Okay, that's what the proof of convergence means, right? So, in other words, if you are going to pick up these vectors randomly from the set P and N cyclically, as we were doing in the toy example, then a weight vector WT is found after a finite number of steps, which will separate these two steps, these two sets, right? So that's what we are trying to prove. So that's the definition of convergence. And does it make sense? Right? Okay. So proof is on the next slide, and it's going to take me around 5 to 10 minutes to prove it. So just stay focused. Right. So here's a few setup. Right. So I'm going to, before I go to the actual proof, I'm going to make a setup so that it becomes easier for us to prove it. Right. So the first thing that I'm going to say is that if there's a point which belongs in negative set, then the negative of that point belongs in the positive set. Right. And that's very clear, because if the point belongs in the negative set, then W transpose X is less than 0. But then W transpose minus X would be greater than or equal to 0. Right. So if I take the negative of the point, I can just put it in the positive set. So instead of considering these two different things, P and N, I'm just going to consider one P prime, which is a union of P and all the N points negated. Okay. Is the setup clear? If this is a setup, then what is the condition that I need to ensure for every point in P dash? W transpose P should be greater than or equal to 0, right? So I don't care about the negative case. I've just made everything positive now, and I've not done anything wrong here. Right? It's just a simple trick. Okay, and now this is how the algorithm will look in this setup. These are the inputs with label 1, inputs with label 0. N minus contains the negation of all the points in N, and P prime is a union of these. Now again, I start by initializing W randomly. While convergence, I'll do something. I'll pick a random P from P prime. Now what is the if condition? Less than 0. Do I need the other if condition? No, right? Because everything is now positive. Okay. And the other small thing that I'm going to do is I'm going to normalize P. Okay. So that again does not mean, because we're talking in terms of angles, and I'm not changing the direction of the vector, I'm just shrinking it, right? So I'm just, or maybe scaling it also. I'm just making it unit norm. So that does not change anything, right? So it's still, everything still holds, okay? And in particular, you can see here, right? So if this condition was true, this condition will also be true, okay? So far just, I've done some simple tricks to make things easier for me later on. So now P has been normalized. Now remember that this data is linearly separable. That's what we started the proposition with. If P and N are linearly separable, then the perceptron learning algorithm will converge, right? So now if P and N are linearly separable, irrespective of whether we have the perceptron learning algorithm or not, what do we know? That there exists a W star, which is the solution vector, right? There exists at least one W star, which is the solution vector, right? Such that it will separate the P points from the N points. So this vector which we don't know, but we just know that it exists, so we can refer to it. So we'll call this W star, okay? Fine. Now we start the proof. So W star is some optimal solution which we know exists, but we don't know what it is, right? Now suppose you are at time step t. So remember that this algorithm is going on while convergence. So you have time step 1, 2, 3, you're picking up points. So you're at a time step t, at which you pick up a random point pi, and you find that the condition is actually violated. So this should actually be less than 0, right? You find that the condition is violated. So now what will you have to do? W is equal to W is 1. So I'll just call it the new W, Wt plus 1 is equal to the old W plus Pi. Okay. Now what I'm going to do is, I'm going to consider the angle beta between W star and Wt plus 1. I don't know what W star is, but we can still assume it exists and make some calculations based on that, right? So what's the angle between W star and Wt plus 1? It's beta, and what's the cos of that angle? This. And remember that we don't have W star here because we had assumed that it's the normalized vector, right? So we don't need that bit, okay? This is actually equal to 1. Okay. So now if I just take the numerator, W star in dot product Wt plus 1. Now I'm going to expand Wt as Wt plus Pi. Fair? Well, that's exactly what I did on the previous step. Is it okay? Fine. Now what is Pi actually? It's, so what you had is you had these P1, P2, P3, my handwriting is really horrible, and up to Pn, right? So I've just picked one of these Pi's, okay? Now what I'm going to define is, now suppose this is these are my Pi's, right? So these are all the vectors that I have. Now suppose I have this W star. Suppose this was the W star that I'm interested in. Now for each of these I could compute W star P1, W star P2, and so on up to W star Pn, right? And I could sort them. Now what I'm doing is that for whichever of these points W star Pi is the minimum, okay, I'm going to call that value as delta. Suppose W star P1 is the smallest quantity out of W star P1, W star P2, W star Pn, right? And I'm calling that quantity delta, okay? So I have this quantity here, and my delta is the minimum of all the possible values that it can take. It can take W star P1, P2 up to Pn, so delta is the minimum quantity. So here I have an equality, okay? Now are you okay with this? This is the minimum quantity, right? So any Pi that I put in here, it is always going to be greater than or worst case equal to delta. Fair? Okay, fine. Now again this W2 itself, I could write it as Wt minus 1 plus Pj because that also would have come up from some update in the previous step, okay? Again this is there, which I could call it as delta and still retain the greater than equal to here, okay, fine. So let's see where are we heading with this, right? Now notice that we do not make a correction at every time step. When I was running the toy algorithm, I was not making a correction at every time step. We were only making a correction at those time steps for which the condition was violated. So now if I am at tth time step, maybe I have made only k which is less than or equal to t corrections. At max I would have made t corrections, but it could have been less than that also, okay? So now every time we make a correction, we are adding a value delta to this, right? So at the time step t, what would happen? I had started off from W naught. I have reached time step t, and I have made a case that I have not made t updates, I have made k less than or equal to t updates, right? So how many deltas would get added? K delta. So I could say that with respect to W naught, where I had started from, this is what this quantity is, okay? Is that fine? Anyone has a problem with this? Okay. So far what have we shown, right? We started with this condition was true, again not less than equal to, and hence we made the correction, right? This was the point that we picked up at the tth step, and hence we made that correction. And we also showed that the numerator is actually greater than equal to this quantity, right? We showed it by induction, fine. Now let's look at the denominator, and in particular let's look at the denominator squared, okay? Is this step okay? Right? This is actually Wt plus 1 dot product Wt plus 1, but Wt plus 1 can be written as Wt plus Pi. Is this okay? This bracket needs to disappear. Right? Is that okay? Fine. Now, what is what is this quantity? No. That's less than equal to 0. So now can you guess what is the next thing that I'm going to write? Right? That's correct. Yeah, it's a negative quantity. Yeah. So that is going to be less than equal to this. Yeah. Okay. Yeah. So that's fine. And what about pi square or this term? Huh? Because this is less than, right? That's why. Yeah, correct. Okay. Is this fine? Okay. Now what is pi square? 1. Okay. Now can you guess what I'm going to do? By induction? K. Okay. That's okay. So what is Wt square again? Right? Just as Wt plus 1 square was Wt square plus 1, Wt square is going to be Wt minus 1 square plus 1, right? And how many such ones will get added? K of those, right? Starting from W naught. Okay. So what have we shown? The numerator is greater than equal to this. The denominator is less than this. Okay. Now if I put them together, I actually get that cos beta is going to be greater than equal to the numerator over the denominator. Okay. Now what is this quantity proportional to? K, k square, k cube, square root of k, k by 2, square root of k, right? You have, I mean, roughly speaking, you have a k here, you have a square root of k here. So I could roughly speaking say that it is proportional to square root of k. So as k grows, what will happen to cos beta? It will grow, and that's fine, right? It can keep growing. Only until 1, right? So cos beta is going to be proportional to k. What is k? The number of updates that you make. Now, if I were to take that degenerate case which you guys were hinting at, where that it will keep changing again and again, what will happen to k? It will keep going to infinity. Can that happen? No, because cos beta will blow up, right? And that is not allowed. So k has to be finite so that cos beta stays within its limits, right? Hence, are we done? How many of you think we are done? How many of you are satisfied that we are done? It's not a trick question. So we are done. Please, we are done. Okay. So yeah. So this says that we can only have a finite number of such k updates that we make, and after that the algorithm will converge. Is that okay? So we have a proof of convergence. Okay. Now coming back to our questions. This is where we had started at one point. What about non-Boolean inputs? So perceptron allows that, right? We took IMDb rating and critics rating as an input. Do we always need to hand code the threshold? No. We now have perceptron learning algorithm. Are all inputs equal? No. We now assign weights to input. What about functions which are not linearly separable? We still don't know, right? So that's where we are headed now. Okay. Not possible with a single perceptron, but we'll see how to handle this. Okay. So far the story is clear to everyone? Okay. So we'll end this module here. So in this module, we'll look at linearly separable Boolean functions again, and we'll try to make some more statements about them. Okay. So what do we do? So the guiding question that we have is, what do we do about functions which are not linearly separable? And let us see one such very simple function. Can you guess what function I'm going to talk about? All of you were paying attention in the first lecture. Good. Right? So here's the XOR function. Now these are the set of inequalities that result from the XOR function. I hope. Yeah. Right? Now let's see. The first condition implies that W naught should be less than 0. Second condition implies this. Third condition implies this. Fourth condition implies this. Just looking at this, can you tell me, can you find a configuration for W naught, W1, W2 such that these inequalities can be satisfied together? No, right? Because 2 and 3 want you to be greater than -1, minus W naught, And when you take an addition of that, it has to be less than minus epsilon. So that's not going to happen, right? So you see a contradiction. So this is a simple Boolean function which the perceptron cannot handle because it is not linearly separable. If it's not linearly separable, there does not exist a line. If there does not exist a line, you cannot find the line, right? So, and in fact, you can look at it visually, right? So these are the red points for which the output should be 0 or 1, and the blue points are the points for which the output should be 0. Hey, we need to change this. I think we were using blue as positive and red as negative. And you can't just draw a line, right? There's no way you can draw a line such that the blue points lie on one side and the red points lie on the other side, right? So, and it's a simple 2-input function, right? So it's not that I've taken a very contrived example, okay? And most real world data is not linearly separable and will always contain some outliers, right? So here maybe you have some data where you're trying to say that people which live in this part of the world belong to a certain, or maybe people who live or work here have a certain qualification. People who work in this company may have a certain different qualification, right? And there might be some outliers, right? It's not that it's always going to be very clean. So now what do I mean? Okay, and this is not, it's not necessary that the points will only be outliers. In fact, there could be a clear case where there are no outliers, but still you cannot find a line such that you separate the positive from the negative. Can you think of such an example? Good, right? So this is clear data. There's no outliers here as such. I mean, it's just saying that everyone who lies within this boundary has a certain characteristic, and outside that boundary, people have a different characteristic, right? And there's no outlier here, but you can't separate this data with a line. So all functions that you deal with are not going to be linearly separable. So you have to work around those, right? And while a single perceptron cannot deal with this, we'll show that a network of perceptrons can indeed deal with such data. So that's where we are headed, okay? So before going there, we'll discuss some more Boolean functions in more detail, and I'll try to see what kind of non-linearly separable Boolean functions are there, right? So first of all, how many Boolean functions can you design from 2 inputs? How many can you design? 16. Looks like a good number. From 3 inputs, 256. How many of you understand this? Okay, let's see. So let us begin with some easy ones that you already know, right? So these are 2 inputs, x1, x2. What is this function? Always off. The other extreme is always on, and I've already given you the answer. F16, right? So, and then you have the AND function, the OR function, and then some other functions, right? So why did you reach 16 actually? Because with 2 inputs, you will have these 4 values to take care of, and each of these are again binary. So you actually have 2 raised to 2 raised to n, right? So for 3 inputs, 2 raised to 2 raised to 3 would be 256, right? Okay. Now that's the easy part. Of these, how many are linearly separable? I love it when you actually stare at it and seriously try to find the answer when you can't really do that, right? So it turns out all of them except the XOR and the NOT of XOR. Okay. So for the 2 input case, there are 2 functions which are not linearly separable. Okay. For n inputs, how many functions would be not linearly separable? It's an arbitrary. Okay. N is not the answer. You're not going to disappoint me. Not n. Okay, but what's the answer? Yeah, okay. So for n inputs, we'll have 2 raised to 2n functions. Of these, we don't know how many are going to be not linearly separable. That's not a solved problem. Although I encourage you to go and find the answer. I'm looking for a goodwill hunting kind of a moment. But yeah. So, but all it suffices to know is that there exists some which are not linearly separable, right? And that everyone agrees, right? That there exists some, right? And as n grows, probably that number will increase and so on, but it's not known exactly. You can't write it as a function of it. Okay. Okay. So what we have done so far is looked at Boolean functions, how many Boolean functions can exist, and of that we just have concluded that there would be some which are not linearly separable. So we'll end this module. We'll go to the next module, where we talk about a network of perceptrons, and then we talk about the representation power of a network of perceptrons. So this module should have been titled as Network of Perceptrons. Okay. So now, in particular, what we are going to see is how any Boolean function, whether linearly separable or not, can be represented using a network of perceptrons. Now what do I mean by represented using a network of perceptrons? What it means is that I'll give you a network of perceptrons. You take any Boolean function, feed any value of x1 to xn, and the network will give you the same y as is expected from the truth table. Right? That's what representation means, just to put it out clearly. Okay, fine. And now I'm going to again do a setup. I'm not giving you the solution, I'm just making some setup, and then we'll discuss the solution, right? So for this discussion, we'll assume that true equal to +1 and false equal to -1. So instead of 0 and 1, we'll assume -1 and +1, okay? And these are your inputs, x1 and x2. We are taking the 2 input case. And I'll have 4 perceptrons first. I'll have 4 perceptrons. And I'll also have very specific weights connected to from the inputs to these perceptrons. So red means -1 and blue means +1, right? So the first 2 inputs are connected with a weight of -1. The next 2 inputs with -1, +1, +1, -1, and the last would be +1, +1, right? Okay. Now, once I have this, I'll set the bias of all these perceptrons to -2. Okay. So that means they'll fire only if their weighted sum of the inputs is greater than 2. Okay, fine? Okay. Now after this I'll have one more perceptron. So I had 2 inputs. I converted that to 4 values. These 4 values are now going to feed into one more perceptron. Okay. And these weights, I'll not fix them. These are the weights that I'm going to learn. Okay, these. And the final output of this perceptron, which is the green perceptron, is the output of the network, right? So now coming back to what I said, that it can represent any function, what I mean is that you take any function, feed in any combination of x1, x2, this network will give you y, and I'm telling you that it will match the truth table of that function. Okay, fine. Now let's define some terminology. This will also stay with us for the rest of the course. So this network contains 3 layers. The layer containing the inputs is called the input layer. Very creative. The middle layer containing the 4 perceptrons is called the hidden layer, and the output layer, which gives you the output, is called the output layer. Okay, the output perceptron, which gives you the output, is called the output layer. Right. So you have an input layer, a hidden layer, and an output layer. And the outputs of the 4 perceptrons, I'm going to call them as H1, H2, H3, and H4. Okay. And the red and blue edges are called the weights for the layer 1, which we have not learned. We have actually set them by hand. And the weights for W1, W2, W3, W4 are called the weights for the second layer. I've got the layer 2 weights. And these are the weights that we want to learn. Okay. Now, I make this claim that this network, it can take any Boolean function. It can implement any Boolean function. Right? So this same network can implement any Boolean function. That means if I take this network and if I try to learn the values of W1, W2, W3, W4 for any Boolean function, whether it was originally linearly separable or not, I'll be able to implement it. Right? So isn't this an astonishing claim? Any Boolean function. Do you think this is an astonishing claim? Well, not really, if you really understand what is happening here, right? So let's see what exactly is happening here. So when will perceptron 1 fire? When the input is false, false, 0, 0. Will it fire for any other input? When will perceptron 2 fire? Any other input? Same for the next perceptron? Same for the next perceptron? So you start getting an intuition of what is happening here? You do? Okay, let's see. So now for this particular network, now that I've given you some intuition of what is happening, basically every node or every neuron in the hidden layer is catering to one of the inputs, and it will fire only for that input, it will not fire for anyone else, right? So now let's try to implement the XOR function and see what are the, okay. So now let's try to implement the XOR function and see what are the set of inequalities that result from this. Earlier, when we tried to look at the set of inequalities, we ended up with a contradiction. Let's see if that happens now. So this is x1, x2, this is the XOR function, so that's just like any truth table. Then I'm noting down the intermediate values, and then my final input to the green perceptron is going to be summation of these. Okay, fine. And it will fire if this summation is greater than equal to 0, or else it will not fire. Okay. Now for the first case, when the input is 0, 0, what is H1 going to be? 1, and everything else is going to be 0. That's exactly what we saw in the previous slide. So what is the summation going to be? Just W1, right? So it's W1 H1 plus W2 H2 so on, but H2 to H4 are 0, so only thing that remains is W1. For the second case, W2. For the third case, W3. And for the fourth case, W4. So is it clear now what is happening? Let's go a bit more into detail, right? So now for the XOR condition, what are the conditions that we need? W1 should be less than W0, right? Because this should not fire. W2 should be greater than equal to 0. W3 should be greater than equal to, sorry, W0, not W is not 0. And W4 should not fire, so W4 should be less than W0. Are there any contradictions here? By design, no, right? So we have made sure that for the final layer, only one of these guys feeds to it. So it doesn't matter what the remaining outputs are, right? They don't interfere with each other. Unlike earlier, where we had conditions like W1 should be something, W2 should be something, and then W1 plus W2 should be something. There are no such contradictions here, because we have made sure that every neuron in the middle layer actually caters to one specific input, and now the weights in the final layer can be adjusted so that we get the desired output for that input, right? So I can set whatever value of W1 I need to set so that I can fire the neuron, right? In fact, I could just fix W0 as 0, and then I can adjust the weights of W1, W2, W3, W4, right? And I can implement the XOR function. Right? So are you convinced that this can be used to implement any Boolean function? How many of you are not convinced? So the negative question never works. How many of you are convinced? Sure? Okay. Now what if we had 3 inputs? Before that, it should be clear that the same network can be used for any of the remaining 15 functions, right? And for each of these functions, we'll end up with a different value of W1, W2, W3, 4, but we'll be able to satisfy the truth table, right? And you can go home and try it, which I'm sure you will do. So what if we have a function of 3 inputs? 256. What is 256? No. 8, right? Fine? Sure? Okay. So this is what it will look like. And anything specific about the weights of the initial layer? Can you tell me what the weights would be? Just tell me red, 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 blue, blue, whatever colors you like, just tell me. First perceptron, what would the weight colors be? Red, red, red. Then? Okay, enough. Okay, so this is how it will look like, right? And now the same thing will work with the same logic. For any Boolean function of 3 inputs, you'll get these 8 inequalities, and they'll not interfere with each other. And you can set the values of W1 to W8 so that you can satisfy it. Okay, fine. So what if we have n inputs? 2 power n perceptrons in the middle layer, right? Okay. So now here's the theorem. Any Boolean function of n inputs can be represented exactly by a network of perceptrons containing one hidden layer with 2 raised to n perceptrons and one output layer containing 1 perceptron, right? We just saw an informal proof of this. We just constructed it. I just gave you the answer, right? This is how you will get it, right? Now note that a network of 2 raised to n plus 1 perceptrons, is it sufficient or necessary, or both? Sufficient, yes, that's what it says. Is it necessary? No. We already saw the AND function, which we can just represent using a single perceptron, right? So it's not necessary, but it is sufficient. Okay. So this is a very powerful theorem if you think of it, right? So now this whole objection, right? Remember this history, and when we had this AI winter, when people showed that perceptron cannot handle the XOR function, that's for a single perceptron. If you have a network of perceptrons, you can actually have any Boolean function. But what's the catch? As the value of n increases, the number of neurons increases exponentially, right? But still in theory, you could have a solution. Okay. Now again, why do we care about Boolean functions? I keep coming back to this. Why do we care about Boolean functions? Because we took this, and so the question that I want to answer is, how does this relate back to our original problem, right? We know, okay, any Boolean function can be implemented. How do we go back to our original problem, which is whether we like a movie or not, right? And we could see that there's a whole family of problems there, right? Whether we like a movie or not, whether we like a product or not, whether I want to go home today or not, yes, no, any kind of a yes, no problem, right? There's a whole family of problems there, right? So let us see. So we are given this data from our past experience, right? So we are told that this is what the movie looks like. These are the actors, directors, genres, everything. We also know whether we like these or not. So we have a set of positive points and we have a set of negative points, right? And now we want to have a computational model which can satisfy this data. That means once the model is trained, once whatever algorithm I use has converged, it should be able to give me the correct output for a given input. Right? That's what we are interested in, and that's a real classification problem that we are interested in. Now, for each movie, we are given these factors as well as the decision, and as I said, PIs and NIs are positive and negative points. The data may or may not be linearly separable. Right? It's not necessary that the data is linearly separable. Those were the goody cases, right? But in general, that may not happen. But do we worry about it now? No. What the previous theorem told us is that irrespective of whether your data is linearly separable or not, I can give you a network which will be able to solve this problem, modulo that it might be very expensive in the number of neurons in the middle, right? But if you keep that aside, I have a solution for this. And that's why we care about Boolean functions, because many problems we could actually cast to it in a simplistic way if we ignore the real inputs. And if you even think of the real inputs, right? Suppose it could take all values between 0 to 1. You can always make it binary. You could say that is the value between 0 and 0.1, is the value between 0.1 and 0.2, and you could make it as small, the scale as small as possible, right? So that's why we care about this. So the story so far has been that the networks of the form that we just saw, right, which contain one input layer, output layer, and one or more hidden layers, these are known as multi-layer perceptrons. But a more appropriate terminology would be multi-layered network of perceptrons, right? Because the perceptron is not multi-layered. You have a network of perceptrons, and that network has many layers, right? But generally, there is this abuse of notation. We always call it MLP, which is multi-layered perceptrons. And the theorem that we just saw gives us the representation power of an MLP, and it basically tells us that it can represent any Boolean function that we want to deal with, right? So that's where we'll end this class, and in the next class, we'll talk about sigmoid neurons. Okay, thank you. We are in lecture 3 of CS 7015, and today we are going to cover the following modules. We are going to talk about sigmoid neurons, gradient descent, feed-forward neural networks, representation power of feed-forward neural network. So let's start. So here are some acknowledgements. So for one of the modules, I have borrowed ideas from the videos of Ryan Harris on visualized backpropagation. They are available on YouTube. You can have a look if you want. For module 3.5, I have borrowed ideas from this excellent book which is available online. It's the URL is mentioned in the footnote. And I'm sure I would have been influenced and borrowed ideas from other places, and I apologize if I'm not acknowledged them properly. If you think there are some other sources from which I have taken ideas, then let me know. I'll put them in the acknowledgements. Okay. So with that, we'll start with module 3.1, which is on sigmoid neurons. So the story ahead is that it's enough about Boolean functions, right? Now we have done a lot of Boolean functions, but now we want to move on to arbitrary functions of the form y is equal to f of x, where x could belong to Rn and y could belong to R. Right? So what do I mean by this? Right? So let me just explain this with the help of an example. So I'll again go back to our oil mining example, oil drilling example, where we are given a particular location, say in the ocean, and we're interested in finding how much oil could I drill from this place, and that is what I would base my decision on, right? Whether I want to actually invest in this location or not. And then what we are saying is that this could depend on several factors. So we could have x1, x2, x3 up to xn, right? Where this could be the salinity of the water at that location. So this could be a real number. This could be the density of the water, right? So average density. This could be the pressure on the surface of the ocean bed, and so on and so forth, right? So each of these values independently belongs to the set of real numbers, right? So each of this is a real number, and we have n of these. So together they belong to Rn, right? So I can say that I have n such real numbers, and I could just put them in a vector and say that I have an input x which belongs to R raised to n. Okay, so we have this x which we can say belongs to Rn, and in this particular case we want to predict y. We want to take this as an input and predict a y, right? And what is y in this case? We want to predict the quantity of oil that we could mine, right? So what does y belong to? Again, a set of real numbers, right? It could be some gallons or liters or of water, right? So this again belongs to r. So these are the kind of functions that we are interested in now. We want a function which takes us from, okay, I'm having this x, which belongs to Rn, right? It's a vector of dimension n, and takes us to a value belonging to R, right? So you clearly see that this is different from the case when we had n variables, each of which was just Boolean, right? So these were only 0, 1 inputs. Now we have real inputs, and these are the kind of functions that we are interested in. Now, can we have a network which can represent such functions? Now, what do I mean by represent such functions? We already spoke about this when we were doing Boolean functions. Okay, so what do we mean by representing the function? We mean that if I'm given a lot of training data, right? So I'm given these x1, x2, each of these belongs to Rn, right? And I'm also given the corresponding labels. Now I want a network which should be able to give me the same predictions as are there in my training data. So it should be able to take any of these xi's as input, and it should give me the same yi corresponding to it. And I'm saying approximately, which means I'm okay with some error, right? If it's within some, as long as it's close to the actual value, I'm fine with it. So that's what I mean by a network which can represent such functions. Is that working definition of represent clear? Right? So that's very similar to the definition that we had used for Boolean functions. Right? We had said that we should be able to get the truth table, the network should be able to represent the truth table exactly. So that's very similar to the definition that I'm using here. Okay? And then before we do that, right, before we come up with a network which can do this for arbitrary functions, we have to graduate from perceptrons to something known as sigmoid neurons. So please remember this overall context that we dealt with a lot of Boolean functions. We analyzed them carefully, and we saw that we could come up with these networks which could represent arbitrary Boolean functions, right? And they could represent them exactly as long as we have one hidden layer. Of course, the catch was that that hidden layer could grow exponentially. Now we want to graduate from Boolean to real functions. That means you have a real input of n variables and one or more outputs, and you should be able to represent this exactly. Right? So that's where the transition is. So that's the story that we are looking for. Okay, so let's start. So recall that a perceptron will fire if the weighted sum of its inputs is greater than the threshold. Right? Just recall that. Fine. So now I claim that the thresholding logic which is used by a perceptron is actually very harsh. Now what do I mean by that? Let's see. So let us return to a problem of deciding whether we like or dislike a movie. Right? That's the same problem that we have been dealing with. And now consider that we base our decisions only on one input, which is the critics rating, which lies between 0 to 1. Okay? And this is what my model looks like. It takes the input as the critics rating. I've learned some weight for it, and my threshold is 0.5. Okay? What does this mean? It means that if for a given movie, the rating is 0.51, will it predict like or dislike? Like. So then I should go and watch the movie. What about a movie for which the critics rating is 0.49? Dislike. So now you see what I mean by harsh, right? So both these values are very close to each other. But for one, I say I like it. For the other, I say that I won't like it, right? So it's not how we make decisions, right? You would have probably said something equal for both the movies, right? You would have not given such a drastic decision. So why is this happening? So you might say, oh, this is a characteristic of a problem that you have picked up. Maybe that's the critics rating, which is between 0 to 1 or something. But I want to convince you that this is not a characteristic of the problem that I have picked up, but this is something to do with the perceptron function itself. So this is what the perceptron function looks like, right? So this sum of all the inputs, the weighted sum of all the inputs, I'm calling it by a quantity z, right? And this is what I'm going to plot on this axis. So this is my z axis, okay? Now what does the perceptron say? That when this value of z becomes greater than w naught or minus of w naught, it will fire, and when it's less than minus of w naught, it will not fire, right? That's what it says. So this is a characteristic of the perceptron function itself. It is going to have this sharp decision boundary that whenever your sum crosses this threshold, you will say 1, and whenever your sum does not cross this threshold, you will say 0. So in this toy example about the movie critics, it just happened that this was 0.5, and so it was saying yes for 0.51, and it was saying no for 0.49, right? So this will happen for any problem that you pick up, okay? So to counter this, we introduce something known as sigmoid neurons, okay? And this is just a smoother function or a smoother version of the step function. You see that? Okay. How many of you know what a sigmoid function, what's the formula for a sigmoid function? Quite a few. Okay, good. And here is one such sigmoid function which is called the logistic function. So remember that sigmoid is a family of functions. These are functions which have this S-shaped. Logistic function which I have shown here is one such function. And the other function that we will see in this course is something known as the tan H function. Right? So let me just get into a bit more detail with this logistic function. I just want you to understand it properly. So this quantity here, remember we were writing it as W transpose X, right? Which was summation I equal to 0 to n Wi Xi. Remember this? Right? So now I'm just going to consider this to be 1 over 1 plus e raised to minus W transpose X. Now I'm going to ask you some questions and try answering those. What happens when W transpose X tends to infinity? What happens to the sigmoid function? 1. And that's exactly what is happening here. As this tends to infinity, as this keeps growing, right? So remember this axis is Z, which is the same as W transpose X, right? This is W transpose X, okay? So as it tends to infinity, your sigmoid goes to 1. What happens if W transpose X is minus infinity? 0. And that's exactly what is happening here, right? And what happens when W transpose X is equal to 0? Half, right? So this is that value corresponding to half. Is that clear? Okay, so that's how a sigmoid function behaves. Fine. Now we no longer see a sharp transition. It's a very smooth function, and the sigmoid function lies between the values produced by the sigmoid function, right? What is the range that they lie between? 0 to 1. What is another quantity of interest that you know which lies between 0 to 1? Probability. So that's one advantage of sigmoid functions. So now you can interpret the value given by a sigmoid function as a probability, right? So what does it mean in our movie example again? So it just tells me in those two cases that with 51% probability I like the movie, or with 49% probability I like the movie. So now this is not very drastic or very harsh, right? I'm not saying yes or no, I'm not committing myself. I'm just giving you a number which is proportional to how much I like the movie. So it can be interpreted as a probability, okay? Now here's the overall picture, right? So this is the difference between the perceptron function and the sigmoid function. So notice that here we had this if-else condition, right, which was leading to that sharp boundary. Now here we don't have that if-else condition. We just have a function which is a smooth function, okay? And here's another picture. So this is not smooth, not continuous, and not differentiable. Everyone agrees with that? It's not smooth here, right? It's not differentiable here. Whereas this is smooth, continuous, and differentiable. And the contents that we covered today, it will be very important to deal with functions which are smooth, continuous, and differentiable. Okay. So for a lot of this course, calculus is going to be the hero of the course. A lot of the things that we do will be based on calculus. And in calculus, always if you have smooth and continuous and differentiable functions, they are always good, right? So that's why we want to deal with such functions. Okay. So with that, we end module 1. We'll start module 2, which brings us to a typical supervised machine learning setup. Okay, this is a very important module. Please pay attention. So now we have a sigmoid neuron. We have taken care of the fact that the perceptron was a very harsh function. So we have a smooth function. So things are fine. Now what next? Where do we go from here? What is my next topic going to be? Yes, a lot of you are giving the right answers. We need to learn these weights. It doesn't help just to define the function. This function depends on certain weights. And now I need to give you an algorithm which will help you to learn these weights. Now remember when I talked about perceptrons, before giving you an algorithm, what did I revisit? What did I talk about? The error surfaces, right? And then I had motivated from there that our goal is to find a set of weights which give us zero error in that case, right? Or in general, speaking generally, they should give us minimum error, right? They should help us to minimize the error, right? So I need to set up that a similar story here. So we'll again revisit the concept of error. So now, in the case of perceptron, I had shown you this figure, which this data is not linearly separable, which is obvious. And I had told you that perceptron cannot handle this data. Right? But what do I mean by it cannot handle this data? It cannot give zero error, right? But what would happen if I run the perceptron algorithm on this? Take a guess. What does the perceptron algorithm do? Fine. And convergence is my condition, right? I could make that condition a bit loose. What is a valid convergence condition that you would use here? Till almost all my points are separated properly, right? So instead of aiming for 100% separation, I could have a threshold which says as long as 90% of the points are separated, I am fine with it. That looks like a reasonable thing to do, right? So now if I run the perceptron algorithm with that condition, what do you think will I get as the decision boundary? Everyone has a picture in mind, okay? Let's see. Does this match what you had in mind, roughly? Of course, there are many things possible, but it will basically pass through this. Now what is happening here? What is the problem? There are 3 blue points which are wrongly classified and 3 red points which are wrongly classified. But in most real world applications, we'll find that this line is not too bad. We could live with this error, right? This is probably 3 out of 30 on both sides, which is roughly 10% error. Unless you are using it in some mission critical applications or in healthcare where it's a life and death situation or something, in most cases you could live with this, right? So if you are trying to predict whether people will vote for a particular party, if you make this kind of error, it would be largely okay, unless it's a very close election, but largely it would be okay, right? So we could live with this kind of errors in most cases. So from now on, we are not going to be too optimistic, and we are going to say that there would be some error, but my job is to find the weights such that my error is minimized. Okay, I want the minimum possible error that I could get. Is that fine? Okay, so again, whatever weights we want to learn, we are going to be driven by some error function, and we would want to minimize that error function. Okay, so this brings us to a typical machine learning setup, which has the following components. So this perhaps is the most important slide in the course, and I'll say this at least for 100 other slides in the course, but at least for now, this is the most important. Okay, so you are given some data xi, yi, and you're given n such elements, right? So let me just elaborate on this and I'll give you some instances of this. Let me give you some instances of this, right? So one thing which I already told you was this. So this is my x and this is my y. So one example which I gave was about movies, right? So this was genre, actor, and critics rating and so on, right? This is one instantiation of this problem. I could also give you another instantiation which was, I just told you, oil, right? So this is how much oil can I get, and here my factors were salinity, density, and so on, right? There were many other factors. Okay, so this was my x. Again, x belongs to Rn, where n is some number, integer. And another example could be, say, fraud detection. So I have a customer, I'm a bank, I have a customer who has bought some credit card, and I want to predict whether he or she would commit a fraud, right? And I would look at factors like what is his occupation, right? Maybe salary, maybe family size, and so on, right? There could be various factors which I could look at, right? So here again, this becomes an x, okay? And you could think of various such examples, right? Where you're given an x and you're given a y. Okay, so this is the data that you have. Now, what is machine learning then? Where does machine learning fit into this, right? So we know that there is some relation which exists between y and x. In each of these cases, all of us are convinced that there is some relation, right? So whether a person would commit a fraud would depend on these factors. It's reasonable to assume that. It's not a very wild assumption, right? Whether you would find oil at a location would depend on some of these factors, right? It's related. And similarly for the movie case, right? So there exists some true relation between x and y, such that if I plug this value of x into the relation, it would give me the value of y. There exists a true relation. This true relation could be governed by various things, right? It could be governed by physical laws, example in the oil mining case. It could be even governed by biological laws, again the marine life in that location and so on. it could be governed by economic laws, it could be covered by psychology, right? We don't know why a person cheats, what is his function that he's using when he cheats and so on, right? So these could depend on various factors, but we all agree that some function exists, hence we get these values for this particular input, right? For every input we get a certain value, so there is some function which takes us from the input to the output. We don't know what this function is, right? We never know in practice. It's a very, very complex function is all that we know. We don't know this exact function. If we knew this exact function, then there's no problem to solve, right? We just use that function and you can predict how much oil and all of us can become billionaires, right? So that is not the case, right? We don't know what this function is. So then what do we do in machine learning? We make an assumption, okay? We make an assumption that there is some function which takes x to y, and this function is governed by some parameters, right? And this is our approximation of how the real world works. And now under this assumption, we want to predict the parameters of this model, given the data, okay? Now let's take a very simple case where we could assume that y is equal to wx plus b. I'm taking this in the scalar single dimensional case, right? Now how would you estimate the values of w and b? Oh, come on. If I give you 2 data points, you can estimate the value, or should I write it? That would jog your memory, right? This is how we all learn, right? So m and c you can estimate if I give you 2 data points, right? So that's the simplest case. Now we'll make similar assumptions, but more complex functions, and just as we could estimate m and c from the data, we would expect to estimate w's also from the data, okay? So that's what the machine learning setup is. So let's see. So the model, when we talk about a machine learning model, it's our approximation of the relation between x and y. And we are free to make any such approximation, right? So I could say that this is what I think is the relation between y and x, and which is governed by some parameters w. Do you know what is this function? Have you seen this before? Oh, no, not sigmoid. Okay, which model is this? Logistic regression, right? Okay. But I could also have made a different assumption. I could have made this assumption. What do I get? Linear regression. Okay. Please note that this error on the slide. Okay. And I could make some other assumption. I could assume that y is actually a quadratic function of x, right? And I'm free to make any assumptions. The only thing I need to ensure is there is some parameter involved. What is wrong with making this assumption? If this is valid, is this also valid? If not, why? There are no parameters. So, no, not for any x we'll get it will still depend on the value of x, right? If I plug in different values of x, I'll still get a different output. There is nothing to learn. What do I do with all the data that I have, right? There's absolutely nothing I can use it to learn. I have just said that y is equal to 1 over 1 plus e raised to minus x. I can ignore all the data that you had given me. Whenever you give me a new x, I'll just plug it into this formula and tell you the answer, right? And that's bound to be wrong because I have not adjusted this formula. Now once I put in the w's, it gives me this degree of freedom where I can now adjust the formula. I can learn the w's in such a way that my predicted y's are very close to the actual y's, right? So that's why we always need a parametric form, right? Of course, there is non-parametric learning also, but I'm just saying in this supervised setup, we are thinking of models where you have parameters, okay? Okay, so you have the data, you have the model. The model always has some parameters. In all of the above cases, w is a parameter, right? Either the small w, which is a vector, or the capital W, which is a matrix, right? So notice that this is a matrix. This is 1 cross n cross n, and n cross 1, right? Fine. Now, how do we learn these parameters? That's the question that we need to answer, right? How do we learn these parameters? We are convinced about 2 things, that we never know the true function, so we come up with an approximate function, and we have to insert some parameters in that function. So far, good. Now I have to be able to learn these parameters, right? Now for learning these parameters, we have something known as a learning algorithm. So did you see any learning algorithm so far? Perceptron learning algorithm, right? So you already saw the perceptron learning algorithm, and it was able to learn the weights for a perceptron. There are various such algorithms. Today we are going to learn one such algorithm, which is gradient descent, okay? Now any kind of learning, what is it driven by? Learning is driven by errors. Objective function, right? So the analogy which I like to give is, suppose you're trying to learn trigonometry, right? You have a chapter, that's your training data. The chapter has a lot of formulae, that's your training data. Now, what's your objective? There are two objectives actually. I'll tell you the easy objective. The training time objective is that once you read through the chapter a few times, at least whatever formulae are given in the chapter, you should be able to produce the correct output for them, right? So if I ask you what is sine square theta plus cos square theta, you should be able to answer that, right? You should be able to give me the correct answer, right? So in other words, you're trying to minimize the error on the training data, right? Whatever training data you have, which is the chapter content, you want to make zero errors in anything which is given in the chapter. That's your training error. Of course, there's also something as known as a test error. Because after you have learned the chapter, I'll give you an independent set of exercises which might contain questions which you had not seen in the textbook earlier, right? So you would have seen sine square theta plus cos square theta, but now I could ask you some other formula which you should be able to give me answers if you have learned properly, right? So now, right now, we are just talking about the training error. That means getting all the formula in the chapter correctly, and our chapter is actually the training data which is given to you. This is what we are reading. So it is always going to be driven by an objective function, and our goal is, just as we wanted to minimize the errors that we make on the formulae given in the chapter, we want to minimize the errors on the training data. Is this setup absolutely clear to everyone? Anyone who does not understand this has any doubts? See, this is the same framework that we'll use again in lecture 18, 19, 20 and so on to explain some more complex models, right? So you have to absolutely make sure that you understand this, right? It's not very difficult, but just make sure you understand this. Okay, fine. So let's concretize this a bit more, and we'll consider our movie example and try to fit that into this framework. So what's our training data there? We're given movie, comma, like, dislike. And when I say movie, I am just using a shortcut. It's actually all the details of the movie, right? Genre, actor, director, critics rating, and so on. That's our input. And our output is the like, dislike value. What is the model that I chose? What is the model that I chose? I don't know what's my true relation between when I like a movie or not, but I made this approximation that this is how y depends on x, and I made sure I introduced some parameters there. I could have chosen some other functions also, but I chose this, right? Now the parameter is w. This should be bold w. The learning algorithm that we are going to use is gradient descent, which we'll be seeing soon. And what's an objective function here? Can you tell me a formula? So we have been talking about it in terms of English, that I should be able to get predictions which are as close to the true prediction. Now can you put it into a formula? Yi minus yi hat, where hat is the prediction, right? This is the prediction. So that's yi minus yi hat, that should be minimized. Is that fine? Whole square of that. So why do you square it? So that's correct. So for all the training points, n training points, I want to minimize the square difference between yi, the true prediction, and the prediction. The true value and the predicted value. Is that fine? And why do I use squares? Differentiable is 1. The other thing? The positive errors and the negative errors should not cancel, right? So it would be happen that on some movies, I make a positive error of 0.5, right? That means the actual label should have been 0.5 and I gave 1. On some movies, I make a negative error of 0.5 and these would cancel each other and I'll get the false impression that I'm making 0 errors. But once I square the values, the negative values also become positive, so this cannot happen, right? So that's why we always use the squared error function, and also this is differentiable, which is more important, right? Okay. Now the learning algorithm should try to minimize this particular quantity, okay? So this is a typical machine learning setup. Almost any supervised learning problem that you see, you could cast it in this framework, change the y hat function appropriately, change the parameters appropriately, maybe use a different learning algorithm depending on the problem that you're trying to tackle, and you should be able to fit it into the same framework. Is that fine? Okay. At least for this course, everything that we do, we will largely be able to fit it into this framework. Okay, fine. So that's where we end this module. And we'll move on to the next module where we will try to learn these parameters. And initially, we'll try to learn them by guesswork. And I'll show that that's actually infeasible. That's why we need a more principled approach. Okay. So we'll keep this supervised machine learning setup in mind. And now we'll focus on this model and discuss an algorithm for learning the parameters which are W and B, right? Given some data using a given appropriate function, objective function, right? So that's what we are going to focus on, okay? Now sigma here stands for the sigmoid function, the logistic function in this case. Right? This sigma is actually the logistic function. And now I'm going to simplify this further so that it helps us to do a better analysis. I'm just going to consider the case where I have just one input and a bias, okay? And also following the normal terminology in the literature, this W naught from now on I'm going to call it B, because that's the normal convention. B stands for bias, okay? So I have two parameters W and B which I need to estimate, okay? And this is my model for the movie example. And the other change which I'm going to make is, instead of deciding whether I like or dislike, which is 1, 0, the setup that I'm going to work with is that I'm giving the critics rating and I want to predict the IMDb rating, right? So I'm given a real value and I also want to predict a real value. For no particular reason, this just makes life easier for me for explaining a few things. But the same thing or the same algorithm would also hold if you had a binary output, right? And we'll see that later on in the course, okay? So is the setup clear? We just have two parameters W and B, and we are going to assume that Y belongs to real numbers, it's an IMDb rating, and X also belongs to real number, it's a critics rating, okay? Now let's see. What we are given as training is a set of points. We are given some n training pairs, and now we understand what this means. That means for a lot of movie, I am giving the critics rating, and I'm also given the true IMDb rating for them. Of course, in the two variable case, this does not make much sense, but just bear with me, okay? And now the training objective is such that whatever my function predicts, which is a function of W, X, and B, that should be very close to the true output that I know, right? This is the function that I want to optimize, okay? Now let me ask you this. I'm trying to tell you that I'm going to give you an algorithm for training this network. Now suppose I've trained this, okay, with two data points, 0.5, 0.2 and 2.5, 0.9, right? At the end of training, I'll give you some values of W and B. Let's call them W star and B star. These are the final values of W which I have given you, W and B. What do you expect from these values? What do you expect at the end of training? If I say, okay, now the network has learned, what do you expect? You're still going to the test case. I'm just talking about the training still, okay? We expect such that what happens if I plug in at the end of training? If I plug in the value 0.5 here, what should happen? 0.9, right? So this is what you expect at the end of training. If you plug in the value 0.5, it should be very close to 0.2, the output. And if you plug in the value 2.5, it should be very close to 0.9, right? This is exactly what you expect. And this is what training means, okay? Fine. In other words, we hope to find a sigmoid function such that these 2 points lie on that function. Can you imagine a geometric picture for this? What would happen actually? How many of you can imagine it? Okay. How many of you get it now? Right? This is what will happen, right? So you'll get a sigmoid function such that these 2 points lie on that. Fair? Okay. And that exactly means that when I plug in this value, I'll get this value, and when I plug in this value, I'll get this value, right? So that's what it means. Okay. So let us see this in more detail. And now what we'll do is, our quest is for this W star and B star, and we'll try to find this manually. I'll do some random guesswork and try to find this, because I don't have any clear principled algorithm for finding it as of now. So I'll just use some guesswork. So I'll give my initial guesswork as W equal to 0.5, B equal to 0. For no reason, I just picked up some values, right? And this is what the function that I got. What does this mean, this function? An error. So the sigmoid formula should be here. We should have the sigmoid formula here. So is this a good, are you happy with this solution if I give you? It's okay. Are you happy with this solution? Is this good, bad, ugly? There has to be something. Bad, okay, we'll not call it ugly. Okay. So why is it bad? It's not passing through those ponds. Okay, I'll ask you a question. How bad is it? Can you assign a number to it? We're always good at qualitative stuff, but quantitatively, can you tell me a number? How bad is this? Can you tell me a way of finding how bad this is? I already told you in detail how to find that how bad it is. The loss function, right? we have the loss function. Let's see that again and see if we can find out how bad this is. Okay. So this is what my loss function is. Okay, and I have 2 data points. I'll just expand it out. Fine. Now I'll plug in the values. I know this is 0.9, and I'll compute the value of f 2.5. I'll plug in this and I'll plug in this. Okay, and this is what I get. So this is how bad it is. What did we actually expect it to be in the good case? 0. So this is not 0, this is 0.073. So now we have a quantitative handle on how bad this is. Okay, so let's keep this in mind and let's try to continue guessing. So we want the loss function to be as close to 0 as possible. We are not there yet. So then I make a different guess. I say, okay, let me try minus 0.10, 0.00. What happened now? Is it now good, bad, ugly? Now let's call it ugly, right? So it is worse. And how do I know it's worse? Because I plugged it into the loss function and I got a value which is greater than the value at which I was. So I clearly know this is bad. Okay, so now this is how my mind is working, right? Oh, as far as W was positive, things looked okay. At least I was close to 0 in the first decimal. Now when I made it negative, that does not look good. So let me just keep it positive and keep increasing it, right? So I saw 0.94 and I also tweaked the B a bit. I've done complete random guesswork, right? Now what happened? Good, bad, ugly? Better. Okay? Now what will you do? What would your next guess would be? Make W even more positive? Perhaps that would help, and be even more negative, and so on. I can continue in this manner and actually get very close to the solution. So I can do this guesswork and find these values, but it's still an educated guess, right? I'm not guessing in the dark. This is what is helping me drive towards those guesses. Right? I'm just looking at these values and making an educated guess, right? And that's the educated guess which I took, that probably making W even more positive would help. But this is still brute force in a sense, right? This is not something that you'd want to do when you have 100,000 parameters and so on, right? And 1 million data points and so on, right? Okay. So let us look at something which is better than our guesswork algorithm. So we are not there yet. Actually, on the next slide, I'm still going to talk about the guesswork algorithm, and eventually we'll get to something which is better than the guesswork algorithm. Okay. So since we have only 2 points and 2 parameters, what I can do is I can take all possible values of W and B. Okay? That's what I was trying. I was picking up some values of W and B. Why just pick some values of W and B? I'll pick all possible values of W comma B, right? And I'll fix the range. I cannot pick it from minus infinity to infinity, but I'll pick a range. I'll say from minus 6 to 6. Let me try all values of W comma B, compute the loss, and plot it. Right? Now let me tell something about this error function, because this is going to stay with us for quite some time. So what you see here is something like a flying carpet. This is error. This is color coded. Red is bad. Red are the places where the error is high. Blue is good. Blue are the places where the error is low. Darker the shade of blue, lower the error. Darker the shade of red, higher the error. So in particular, if I look at this point, what has happened is I have taken the corresponding value of W comma B, right, which is say minus 4 comma minus 1, right, something like that. I've plugged that value into my loss function and I got this as the loss function. This as the loss value. And that's what I have plotted for all values between minus 6 to plus 6 and minus 6 to plus 6 for W and B. So everyone understands how I have constructed this error surface? Okay? Fine? Okay. Now this of course becomes, and now what I can do is once I see this error surface, I know, oh good, this is the point where I need to be. This is the darkest shade, and this is where the error is the lowest. So I can just pick a W comma B value which lies there. This is fine for this toy example where you just have 2 parameters. But this becomes untractable once you have more data points and many more parameters. And that's what happens in most real world applications, right? So this is not a feasible way of going about things, right? And here again, note that I have only taken the range from minus 6 to 6. I don't even know what will happen if I have to look at all values of W comma B, right? Maybe there was something outside here, right, which was even more lower error or something like that, right? So I don't really know that. So I can't really use this. So I need something better than this plotting the error everywhere and finding it out. That's pure brute force. A surrogate to this was the guesswork algorithm, but which is again something we cannot do for if we have large number of parameters. So everyone gets this, that this is a way of finding the solution, but this is not feasible, right? That's the only point I'm trying to make. Okay. And we look at the geometric interpretation of what was actually happening in the case of the guesswork algorithm with respect to the error surface. Okay, so I had chosen some values of w comma b. The first value that I chose actually gave me an error of, if you remember, it was some 0.073 or something like that, right? So that's the point. Then I decided to take a very random guess, and my error actually increased. So you see that I'm actually climbing up on this error surface. I've gone from a slightly darker shade of blue to a lighter shade of blue, right? And then I corrected myself and then kept moving in a direction where I was going towards the darker and darker shades of blue. So what I was actually doing is I was trying to traverse the error surface and land up in the good regions, which were the dark blue regions. Now what I want to do is, I want an algorithm which will allow me to do this in a principled manner, which is neither brute force nor guesswork. Okay, so that's where we'll end that module, and we'll move on to the next module where we'll talk about gradient descent. How many of you have done gradient descent before? Almost all of you. Okay, so what we want to do is find a more efficient and principled way of navigating the error surface. Is everyone with me in that? Okay, and the goal is to find a better way of doing this. Okay, fine. So let's start by setting up things. We'll define some notations and some parameters and so on, and from there on we'll try to come to the algorithm. Okay, so my parameters in this case were w comma b. What I'm going to do is I'm going to put them into an array or a vector, right, and call that vector as theta. So theta is the vector of parameters, and theta belongs to r what? R2, right? There are two parameters here, so it's a two-dimensional vector. Okay. Now what I want is, again what I'll do is I don't know what the value of w comma b is, so I started with a random guess. So that's always going to be my starting point, right? I'll always start with a random guess, and from there on move on to good values. Now once I've started with a random guess, I want you to tell me some changes that I can make to w and b so that I land up in better situations, right? That means I land up in situations where the error is less. Is that fine? Okay. So that change in w and b, I'm going to call it as delta w and delta b, and that again is a vector which is storing these two values. Okay. So this is the picture, right? I want to take theta and I want to add a small change to it. So this is my theta. This vector is actually theta, right? This is the theta vector. I want to add a small change to it, which is again a vector, right? This is delta w comma delta b, such that I'll get a new value for theta nu, right? So theta nu would be what? Actually, theta nu is equal to w nu comma b nu, right? Is that fine? That's what theta nu means. Okay. Now what has happened is actually when I've added delta theta to theta, I've moved in the direction of delta theta, right? I've come from here to here. Okay. Now I'm going to be a bit conservative, and I'm going to say that while I'm okay in moving in the direction of delta theta, I don't want to make a giant stride. What I'll do is I'll just move by a small quantity in that direction, right? So this delta theta is this large magnitude. So all I'm saying is that I'll move in that direction. I'm fine with that. Okay. But I don't want to make a giant stride. I'll just take a small stride in that direction, right? So eta is a scalar which actually scales down delta theta. Okay. So now if I'm going to take only a small step in that direction, instead of this large change, I'll just get a smaller change, theta nu, right? So the red vector is actually going to be the movement which I make. That's the new value of theta. So theta nu is equal to the original theta plus a small step in the direction of delta theta. So everything is clear? We're done? We're done with gradient descent? What is missing? What is delta theta, right? I'm telling you I want to move in a certain direction, but what is the right delta theta to use? How many of you know the answer to this? What is the answer? Move in the direction opposite to the gradient. Why? Where does that answer come from? Not the ML class folks. How many of you know why we need to move in the direction opposite to the gradient? Why? Okay, we'll see. Okay, so that's the question that we need to answer. If I give you an answer to this question, then what is it I'm doing? I'm giving you a principled way such that you start from a random value of theta, move in certain direction, and it will ensure that your loss has decreased, and then you have to keep doing this, right? So that's the setup, and the answer to this comes from Taylor series. So now what I'm going to do is, I'm going to give you the right direction, delta theta. Fine. And for ease of notation, I'm going to call it as u. So remember what this delta theta is? What is it? Change in w, comma, change in b. So it's a vector in R2. Remember that? Okay. I'm just going to call it as u. Now this is what Taylor series tells me. What it tells me is that if I'm at a certain value of theta, and if I want to change that value a bit, then what is going to be the new value of the loss function, or any function for that matter? And this is the formula for that. Okay. Now let's see what are some quantities here. What is this quantity? Scalar, vector, matrix? Scalar. This? Vector. We just did that, right? It's a vector. What about this? What is this quantity actually? Gradient. What is a gradient? What is a gradient? No, you're telling me how to use the gradient. I am asking you what is the gradient. You're giving me absolutely correct and absolutely useless definitions. That's a very good answer. Okay. So now what I'm going to do is I'm going to digress a bit. Okay. And I'm going to tell you something about derivatives, partial derivatives and gradients, and then we'll come back to this. Okay. So now suppose you have a function L. This is L in my handwriting. This is a function of w. Okay. And say this function is w square. Okay. Now what is this called? The derivative of the function with respect to w. This is the derivative, and you know this is 2w. Okay. Now suppose I have a function b square. Now what is this quantity? This is the partial derivative of the function with respect to w. Why partial? Because it's considering b as a constant and taking the derivative with respect to only one of the variables, right? This happens to be. And what is this quantity? Oh, sorry. So it's w comma b, right? This is the partial derivative with respect to b. Okay. Now can you tell me what is a gradient? So the gradient is nothing but just these two partial derivatives taken together and put into a vector, right? Now suppose I had a function which depended on 100 variables. What would the gradient be? Size of the gradient? R100, right? It would be a 100-dimensional case. Okay. So now can you tell me with this, I wouldn't say knowledge, but this primer, can you tell me what this is? This is a gradient vector which is right there in front of you in red ink. This is what it is, right? Fine? Everyone okay with that? So actually the right way to write this, and probably we need to correct in the slides, would be theta. So remember that theta is equal to w comma b. So this is the derivative of L theta with respect to theta, which is nothing but the collection of the partial derivatives with respect to the components of theta. Is that fine? So everybody understands what's a derivative, partial derivative and gradient? Okay, fine. So now the gradient is a vector in this case. Fine. Okay. So now what is this quantity? It's a, no, it's, what is this? The dot product between these two vectors. Okay, fine. Now one last thing, and many more things actually. So what is this? Square of the gradient. This is not the square of the gradient. What is this? Hessian, fine. Everyone knows the textbook. What's it? Can you tell me what does it? It's a scalar, vector, matrix? Matrix. What's the size of this matrix? 2 by 2. What are the elements of this matrix? Second order partial derivatives, right? So it's the gradient of the gradient, right? Is that fine? So what does that mean? You had this gradient. This is the gradient. Now you want to take the gradient of this again with respect to w comma b, right? That's what this means. It's a gradient of the gradient, right? So what that means is, we'll take the gradient of the first quantity again with respect to w, so that would be dou square by dou w. What would this quantity be? Okay, what would this be? Is that fine? And you can fill in this quantity, right? So now it's clear what the Hessian is the derivative of the derivative, and it would be a matrix. Okay, is that clear to everyone? Yeah. So I have a habit of doing a lot of these basic stuff. I know that the top 20% of the class gets really pissed off when I do this, but as a philosophy, I teach for the bottom 30% of the class, so I don't mind that. And the other thing is I use slides, so I don't write a lot of math, so I can cover a lot of material despite doing all this basic stuff, right? So I'm going to stick to that. What I'm trying to say is that write this in the feedback that you don't like this basic stuff, but it's just that I'm going to ignore that feedback, okay? I mean, just being honest, right? So I like doing this because it just takes me 10 minutes to do this, and for the rest of the class, I don't have to look at blank faces afterwards, right? So it really helps me a lot, okay? Fine, so is that all clear? All the quantities here are clear. So now, so this is the gradient, this is the Hessian, and now eta, remember what did we say about eta? It's a small quantity. And what do we do with small quantities always in maths? We ignore them, right? So once we take their powers, we always ignore them. Whether it's correct or not, who cares? I mean, someone has told it it's good to ignore, so we'll ignore it, right? So now all these higher order terms we can ignore, right? That means I'll only consider this. Fine? So let's again look at what the setup is. The setup is that I have some value of theta. I want to move away from that value such that, what do you say about this loss compared to this loss? I'll call this the new loss, and I'll call this the old loss. What is the relation between them? The new loss should be less than. So if I or someone gives you a u, okay, someone gives you this u, okay, then when would you say it's a good u? If this condition holds. Everyone agrees with that, right? So I've found a good direction to move in if this condition holds. Now, this condition actually implies that this condition should hold, right? This is L theta plus eta u, right? So if I just do minus here, I get this, right? So this quantity, which should be less than or equal to 0, implies that this quantity should be less than or equal to 0. And remember, eta is a positive constant. Okay? Why can't it be negative? Yeah, why? Because we wanted to take a small step in that direction. If we make it negative, we will do what? We will reverse the direction. We don't want that as of now, right? So eta is, that's for a positive quantity. So that means this quantity should be less than 0. Is it fine with everyone? Okay. Okay. So far, after all this story, what we are left with is, this condition should hold for the u that I am trying to choose, so that I can be sure that I have chosen the correct u. Right? And the definition of correct u is that the loss at the previous step, the loss at the new step should be less than the loss at the previous step. Is that fine? Okay, so that's what we have arrived at. Now, what is the range of this quantity? That's why I asked you, what is this? This is a dot product. Okay, I'll leave it at that. So now you tell me what's the range of this. People from the ML class cannot answer. Did I cover this in the ML class? No? What is the range of this? Not a very hard question. Plus or minus? Very good. How many of you understood that answer? He said plus or minus mod of u into mod of gradient, the gradient vector, right? Why is it so? Easy. Let beta be the angle between ut and this, sorry, it should not be u transpose, between u and the gradient. Then we know that this condition holds. Cos beta is given by this quantity, and we know that cos beta lies between -1 and 1. Okay. Now, if I just say that this quantity is equal to k, then I can just get this condition. Okay. Now, let's see what are we trying to do. We are trying to find a u such that this quantity is negative. Okay. Okay. We are trying to find a u such that this quantity is negative. Now, if I just stop at negative, we would like to make it as negative as possible, right? Because the more the negative it is, the more will be the decrease in my loss function, right? Because this quantity tells me how much my loss decreases. So, the more the negative it is, the more the loss will decrease. So, let me make it as negative as possible. Now, what is that value? When will that happen? When alpha is, you know the answer, you started with the answer. No. What is that one phrase which you have marked up? Move in the direction. Okay, now think of that. What would happen when this is the most negative it can be? What would the angle be? 180 degrees. How many of you get that? Because when this is the most negative, that means the cos beta is actually -1. And when is cos beta -1? When the angle is 180 degrees. That means u should be such that it is at 180 degrees to the gradient. Hence, repeat the phrase. Move in the direction opposite to the gradient. Is that fine? Everyone gets it now? Why you need to move in the direction opposite to the gradient? Okay, fine. So, this is what the gradient descent rule is. You are at a particular value of theta. You want to move to a new value of theta such that your new loss is less than the current loss. What gradient descent tells you is move in a direction opposite to the gradient. Okay. So, are you fine with this? Now, with gradients, I have come to scalars, but I'll just explain what I've written here. So, this quantity is nothing but theta t plus 1, right, is equal to theta t, right, and what is this? Right. So, the new theta is equal to the current theta minus, why? Because we want to move in the direction opposite. So, it's basically theta t plus 1 is equal to theta t plus eta into a negative direction, right? The direction negative to the gradient, hence you get that minus out. Okay. So, is that clear? Now, what are these quantities? Let me just take that carefully. So, this quantity is gradient of the loss function with respect to w, sorry, the partial derivative of the loss function with respect to w evaluated at w is equal to wt and b equal to bt. What does that mean? So, remember, when you are dealing with derivatives, there is always a formula and then a value at a particular value. So, what's the derivative of x square? With respect to what doesn't matter, 2x. Okay. Okay. So, derivative of x square with respect to x is 2x. What is the value of this derivative at x equal to 1? 2. Right. So, you see the difference? You have a formula which is 2x. Now, you substitute a particular value and you get the value at that particular value. Okay. So, that's what this means, because you are already at wt comma bt. Now, you can't subtract a formula from here, right? You have to subtract a value. So, you know what the formula is. You plug in the values of wt comma bt, get that value and subtract it from your current wt. Is that fine? Okay. So, everyone completely understands what the gradient descent rule is. Okay. Fine. Good. So, now we have a more principled way of moving in the WB plane. What do I mean by that? Remember, this was our WB plane. This was our error. This is something what our error surface looked like. It was this flying carpet. I was randomly moving on the WB plane earlier, right, and trying to guess what the error is, or trying to compute the error and then settle for a particular value. Now I have a more principled way of moving in the WB plane. I know what is the next step based on the current step. I just need to move in the direction opposite to the gradient. Okay, so let's try to, so this is what it tells me for one step. But I need to keep doing this till, what's that golden word? Convergence, right? I have to keep doing this till convergence. Okay, so let's create an algorithm out of this rule. I'll start at time step 0. I'll do this for some max iterations, right? Instead of saying till convergence, I'll do it for some iterations. At every iteration, this is how I'll update my weights. I'll take the current weights, subtract the gradient from that, and get the new state. Not subtract the gradient, subtract this quantity and get the new weights. So now is everything clear? Is the gradient descent algorithm done? Can you do it for the toy network which I had? Is there something still missing? Eta is fine, we'll take a small value, 0.01 or something. I've still not told you what these are, right? I mean, it's okay to write it. You know these are derivatives, but what is this actually? Okay? So let's see that now. So that's what we are going to see next. Okay. Oh, I'm really going slow today. Fine. Do you guys need a break? You're really in a hurry to wind up the lecture and go. Are you sure you don't need a break? Okay. I don't know whether to be happy about it or sad about it. I'll be happy. Okay. I'll assume that you're enjoying the lecture so much that you don't want a break. Okay. So now we want to find out, we are in our quest is for this delta, the partial derivative with respect to W and partial derivative with respect to B. That's the thing which we had plugged in the formula, but we don't know what that is, right? So we need to find that out. So now for simplicity, let's assume there is only one point to fit, which is x comma y, right? So earlier we had this x1, y1 and x2, y2. Now I'm just assuming there is only one point, which is x comma y. So now what is the loss function? Earlier I had this summation over I equal to 1 to 2, but I have just one x comma y, so I'll just use that. Okay, this is what my loss function. And what are the quantities that I'm interested in finding? One is this, the partial derivative of this loss function with respect to W. Okay, so let's do this. Let's actually derive this. So this is what it looks like. Now you have to help me in deriving this. What will I do first? Tell me the next step. 2 into f of x minus y and push the gradient inside. Push the derivative inside. Is that fine? Anyone who has a problem with this? Okay, next. Y is a constant. This is the true y, remember. So that's why this is a constant. This is not the predicted y. Okay. Now this quantity. What is f of x actually? Sigmoid function, right? So I'll just write it. Now this is the quantity that I need the derivative for. So I'll just write it here. What's the next step? This is of the form 1 over x. So what will it be? Minus 1 over x square, and then you put the derivative inside. Is that fine? Now the quantity inside is of the form e raised to x. So the derivative is e raised to x, and you push it inside. Is this fine? So this on slide should come, both these are coming together. So is that fine? Okay. Now what is this actually? F of x. What is this? This is actually 1 minus f of x. Just take my word for it for now. You can go home and work it out, right? So this actually, if you do 1 minus this and do some trickery, you will get to this quantity, right? So what you get is a very simple formula, f of x into 1 minus f of x into x. So I'm going to substitute back here. So now I exactly know what the partial derivative of w is. Okay, fine. So if there is only one point, then this is what the partial derivative with respect to w is going to be of the loss function, right? If there were 2 points, what would happen? If there were 2 points, my loss function was, this is a sum of 2 elements, and I am taking some derivative of a sum. I'll get a sum of derivatives, right? So how many of you will not cringe if I say this is the answer? Anyone who has a problem with this? You get this? How many of you don't get this? How many of you get this? Okay, good. Fine. Now can you do a similar thing for B? Can you tell me the answer without actually deriving it? Yeah, I can perfectly understand what you're saying. Yes. X won't be there, right? Because this last x that you see here came because w into x was there. But with B we are not multiplying x, so what you will get is this. You can go home and check. Okay? So now we have everything that we need. Now we actually have everything that we need. Okay? No more trick questions. So now we'll write code to do this. Okay? We'll actually implement the code and see what happens. So these are the two data points that I had, 0.5, 0.2 and 2.5, 0.9. The first thing which I need is something which can implement the sigmoid function. So this is 1 over 1 plus e raised to minus wx plus b. Is that fine? Okay. Now I need something which can compute the error. So this is summation of half into f of x minus y the whole square. I'll go over all the data points, summation of half into f of x minus y the whole square. Is that fine? Now what I'll do is, I'll take this, try out a lot of values of w comma b and plot the error surface. Okay. But this is only for illustration. In practice I'll not do this. We just know that this error surface exists. I just want to verify that whatever algorithm I come up with does an efficient navigation of this error surface. That's what I want to verify. Okay, that's why I'm plotting this. Okay. Next I need a function which can compute grad of b. We just saw this on the previous slide. This is f of x minus y into f of x into 1 minus f of x. Right? Simple? Everyone is fine with this? Then I need a function which can compute the grad with respect to w. Same thing, except that I have this x at the end. So I have all the ingredients in place. Now what will I do? What is the next thing that I'll write? The main loop. Right? I'll write the main loop now. Okay? So this is what the main loop looks like. I start with some random initialize for w comma b. Remember that our initial theta, which is composed of w comma b, is going to be some random guess. So I started with a random guess, which is minus 2 comma 2. I've chosen eta to be 1. That means I'm not going to be conservative. I'm going to move in the direction of the gradient. Okay? If I'd chosen at 0.01 or 0.001, I would have been conservative. And I'm going to run this till 1000 epochs, which is my notion of conversions. Okay? Now in each epoch, what I'm doing is, for every data point, so remember that this gradient with respect to w was a summation of I equal to 1 to 2 and that formula, right? So for each data point, I'm computing the grad, adding it, right? So that's the summation part. Similar thing I'm doing for b. Once I have computed the gradient, which is the summation quantity, I'm just moving in the direction of the gradient. Is that fine? Everyone understands the code. It's simple Python code and it does exactly what I had shown in the pseudocode. Okay. Now let's execute this code and see what happens. Okay. So I'll start with my random point, which was minus 2 comma 2, and now I'm going to actually run this code and keep plotting what happens on the figure. Okay. So just pay attention. Fine. So now here's how the code is running. See what is happening? What is happening actually? So at every point, I'm changing my w so that I'm moving in the direction of the gradient. I keep doing that. As I keep doing that, my error keeps decreasing. Why? Because that's exactly what we got from Taylor series, right? If we do this, the error is bound to decrease, right? And then we keep doing this, and after a few iterations, we'll actually reach almost the valley, which is the 0 error, right? And this same thing would happen if you start from anywhere else. It will keep moving in a principled way and reach the low error configuration, right? Now some of you would say that maybe this was the shortest path, right? It could have just rolled over from there. But that is not a principled way of doing that, right? The principled way of doing it is to move in the direction of the gradient. You might take a longer route, but reach your destination. Taking shortcuts is always risky in life as well as here, right? So, so don't, please, this is an advice for your assignments and so on, right? So Yeah. So this is the more principled way, and we'll reach the solution, right? So that's what is happening here. So we actually derived everything that we needed, and this is all you need to write for gradient descent for this toy example that you had. Now answer this question. Now suppose I had 100 such variables. Instead of w comma b, I had 100 such variables. What would happen? So don't try to visualize it. In terms of the code, I'll just need to have these functions for all of those, right? I'll have to calculate it by hand, but still doable. It's just a lot of tedious work. Of course, later on we'll see a more refined way of doing this, where we can do a lot of these computations at one go, right? So we can directly start operating in vectors as opposed to scalars here, right? I'm treating w and b separately here. I could have actually had a function which tells me grad of theta directly, right? And later on we'll see something like this. Okay, but for now, the code is still running here. Now it suffices. So later on we'll see gradient descent in more detail in the course, and we'll also see a lot of variants of gradient descent. But for now it suffices that we have an algorithm which can learn the parameters of a sigmoid neuron, right? So just as we had the perceptron learning algorithm, we have the gradient descent learning algorithm which can help us learn the parameters of the sigmoid neuron starting from random values, and it gives a principled approach for doing that. Okay, so before we move on to the next module, right, some small corrections from yesterday's class. So one was this partial derivative. It should have been dou w square. So you've already taken one derivative with respect to w, and now you're taking another derivative, right? It's the gradient of the gradient, right? And similarly, this should have been dou b square, okay? And this should have been dou w dou b. Okay, the other small thing which I wanted to say was, yeah, so when I was executing this algorithm, right, so I forgot to mention that just notice what is happening is the black dot that you see, the black dots that you see, right, and which are very close to each other actually because you're just making small movements, those are the changes in the w comma b values, and the red dots are the corresponding loss to that w comma b values, right, just to clarify, okay. So that's why you see a movement on the WB plane, which is this movement, and as you keep changing that, your loss function changes and it becomes better and better, right? That means it goes closer to 0. So in this module, we are going to talk about the representation power of a multi-layer network of sigmoid neurons, right? So I'm going to compare these two things which are written in the title. So first tell me, what was the representation power of a multi-layer network of perceptrons? Okay, I roughly hear what you're saying, and basically what you're telling me is that a multi-layer network of perceptrons with a single hidden layer can be used to represent any Boolean function precisely, right? No errors. That's what we saw with that illustrative proof where we actually constructed one such network. Now what's the representation power of a multi-layer network of sigmoid neurons? So a multi-layer network of neurons with a single hidden layer can be used to approximate. Okay, so just see the difference in the language, right? So this was represent, that means exactly. This is approximate, that means I'll tolerate some error. Any continuous function instead of Boolean function to any desired precision, right? So this was precisely with no errors. This is up to any arbitrary desired precision. So what does this mean actually? What is the meaning of this? So there is a guarantee that for any function, okay, which takes your original x from Rn to Rm. What is the m that we have been considering in all our examples? 1, right? We just care about one output, but it can be Rm also. We can always find a neural network with one hidden layer containing enough neurons, right? So that's the operating phrase here, enough neurons, whose output g of x. So that means you would have a network. It would take as input an x. It would produce some y hat. And that is what I'm calling as g of x, right? That g of x would be very close to the true function f of x, right? So remember that we said that there is this true function f of x which gives us the true y's, and we are trying to predict this y hat. So the true y I'm calling by f of x, and the y hat I'm calling by g of x, and you can come up with a neural network which can give you values, which can predict values which are very close to your true values, right? Does that make sense? Do you see the value of this theorem? What is it trying to tell me? Can you give me an interpretation of this? Why is this so useful? Do you know what this theorem is called? Universal approximation theorem. And we did that in the history, right? So this was 1989. Okay. What is the significance of this? Why do we care about such arbitrary functions? And what is this theorem telling us actually? It's of course telling us something about the representation power of a multilinear network of sigmoid neurons. But why is this important? Okay. So we'll see that. So the remainder of the lecture, I've borrowed ideas from this URL. You should actually read this. It's a very interesting book. It's available online for free. Very illustrative. So please take a look at it. Okay. So now actually what we are interested in is we are interested in knowing whether a network of neurons can be used to represent any arbitrary function like the one shown in the figure. Okay, so let me put some labels on this so that you understand what I'm trying to say. Suppose this is salinity. Okay, again I go back to my oil mining example and I say that my decisions are based only on a single variable, which is salinity, and this is actually how the amount of oil varies, right, as the salinity increases. It's a very arbitrary function. It's definitely not a linear function. It's not even a quadratic function. It's not an exponential function. It's just some arbitrary function. But a mathematical function, this is possible. It's quite likely that salinity has this influence on oil production, or maybe it does not. But I'm just taking that as an example, right? Now, what do we want the network to learn? If I take some data and train the network, at the end of training, what do I want? So if I feed it this point after training, what should happen? It should give me this value, right? That's what training means. And that means I should be able to approximate this curve, right? If I do that, that means I have learned from the training data. Okay, so let's see. Now, we make an observation that such an arbitrary function can actually be approximated by a lot of something that we call as tower functions. Okay, these are all pulse functions, which you have many of these and you could have an approximation, right? And you can see that this approximation is bad at many places, right? But still it's an approximation. It largely gives you the same shape as the original curve. What would happen if I increase the number of such tower functions? The approximation would improve, right? If I keep increasing it, the approximation would go more and more better, right? So now just try to keep things in mind what I read in the theorem, right? You can make it arbitrarily close to the actual value. That means you can keep doing something so that your approximation becomes better and better. And you already see something of that sort, right? This is still in the sense of a figure. We need to relate this back to a neural network. But you see that as I'm increasing these tower functions, I become arbitrarily close to the actual function. Okay? Now, this is what is actually happening, right? I have multiple such tower functions. I'm adding them up. All of them are shifted in time, right? So this tower function is actually this one. This tower function is actually this one, and so on, right? And I have not drawn the remaining ones. I'm taking all of these tower functions, adding them up, and getting my original function, right? And the more such tower functions have, the better is the approximation. How many of you are perfectly fine with this? Okay, good. Okay. Now we make a few observations, right? All these tower functions are actually the same. What's the only difference? They're just shifted and their magnitude changes, right? But they're all tower functions, right? So let's think of this that if I know how to make a rectangle, then I can make any rectangle, right? I just need to change the size of the rectangle and maybe shift it or orient it differently or something, right? So they're all similar. I just need to learn how to draw a tower, right? That's what my quest is. Now, if I take the original input salinity, pass it through multiple such blocks, each block is capable of making a tower function, and each of these would give me one of these towers that I'm looking for. And I'm looking for so many of these, right? If I have as many such tower makers, then I could get these towers. I could just add them up and then get the original function back, right? Okay? And the more these I have, the better is my approximation, right? So I'm taking as input the salinity and trying to predict the oil. Does this make sense? Okay. Still, we have not figured out a neural network way of doing this. We are still building intuitions of how to do this. Okay. Now, our job now is to figure out what goes in this black box. That's the tower maker, and how does it connect to neural networks. If we figure that out, then our story is complete. Right? Then we know that a neural network can actually do this, and that precisely proves the statement which I had made, that it can represent arbitrary functions. Okay, fine. So we'll figure this out over the next few slides. Now, if we take the logistic function and set w to a very high value, what will we get? Just try to think about it. So the answer is already written, but I want you to imagine it. W covers what? The slope, right? As I make W very high, what will happen is I'll get the, so let's try changing the value of W, okay? I'll just increase the value of W and see what happens to the sigmoid curve. Oh, there's some error here. Actually, there's some problem here. The W value should have increased, and that's how the sigmoid slope increases, not the B value. The B value comes later on. Okay, so actually, sorry about this. The W value as I keep increasing, so don't think that B is increasing, think that the W is increasing. It will become sharper and sharper, and it will come very close to the step function, right? It will not become exactly the step function, that will only become in the limit, but if I keep increasing, I'll get very close to the step function. Everyone agrees with this? Okay. Now what happens if I increase the value of B? It will shift. Everyone is confident about that? Okay. Can you tell me why? What will shift actually? The point at which the transition happens, right? So what is this point actually? This is the point at which I get that half value, right? And let's look at our function. This is our function. When will I get that half value? When Wx plus B is 0, right? So that means x equal to minus B by W. That's why it's proportional to B. So as I keep increasing the value of B, this will keep shifting. Okay? Is that fine? Everyone okay with this? Okay. Okay. Now what if I take two such modified sigmoid functions which are shifted differently and both are very close to the step function, right? So here's where one threshold is, here's where the other threshold is, and now I subtract this one function from the other. What will I get? You know the term. You'll get a tower, right? Is that fine? Everyone gets this, right? So these places up to this point both are 0, so 0 minus 0 will be 0. At this, for this small range, this is 1 and this is 0, so that 1 minus 0, and then afterwards both are 1, so 1 minus 1 would be 0. So you get that tower function, okay? So now I have my tower maker, okay? Okay. Now can we come up with a neural network to represent this operation? I want a sigmoid neuron. I was working with a sigmoid neuron with some arbitrary weights, right? So that I recover that step function. Can you imagine now, given x, I want this tower function. And that's exactly what one of the blocks was, right? So what I'm asking you is, oh God. Yeah. So I'm asking you to give me a neural network for this. Can you think of it? Can you try imagining it? Sorry? 2 neurons in the hidden layer. How many of you agree with that? Okay. Can you take some more time to imagine what it would be? Okay. And I've already. Okay. Right? So this W1, B1, if I set it appropriately, I'll get this step function. If this W2, B2, I set it appropriately, I'll get this step function. Now I needed to subtract one from the other, right? So I'll do plus 1, minus 1. This is just a simple addition and I'll get this. Is that fine? Everyone agrees with this? This is just an adder, right? This is just an aggregator. Everyone gets this? So now I've given you the tower maker. if you put enough of these tower makers and learn the W's appropriately, what will you get? That function that we were needed. So you can approximate it arbitrarily to any precision that you want, as long as you keep increasing the number of these units, right? So these units actually give you one tower. More of these units that you have, actually this much. This is the input, right? Okay, the more such tower makers that you have, the more is the bars that you will get, and then you can approximate. Everyone gets the intuition behind this? Fine? Okay. This all is always good in 1 dimensions. Now what will happen in 2 dimensions? What if we have more than one input? What is a tower there? Do you all know what's a tower there? If you say no, I'll give you a 0 on the assignment. Remember the last question of the assignment? Did you all make a tower? Did you all make a 2D tower? Did you all copy that? No, okay. Okay, so what if we have more than one inputs? Suppose we are again trying to take a decision about whether we'll find oil at a particular location of the ocean bed. And suppose now we base it on 2 factors, right? So say this is salinity. Okay, this should be x1, should be x2, and should be y. Okay, and this is pressure. Okay. Now just observe about the red and blue points. So the red points are where you will not, for those configurations of salinity, pressure, you will not find oil, and the blue points are for which you will find oil. What is the one thing that you can tell me about the red points and the blue points? Not linearly separable, right? But we still want to be able to learn this. Is that fine? A single perceptron cannot do it. I'll also make a case for a single sigmoid neuron cannot do it. And then I'll show you that. In fact, first I'll show you that with a network of neurons we can do it. And then I'll show you that with a single sigmoid neuron you cannot actually do that. Okay. So now this is again a valid problem. You could imagine that you will get this kind of data where you have 2 factors and your function is some arbitrary function of these 2 factors. It's not a neat linear boundary between the blue and red points. Everyone sees that the blue and red points are not linearly separable. You cannot draw a plane such that all your red points lie on one side and the blue points lie on the other side. Everyone sees that. Okay. But the solution which I have plotted here, that's a good solution. It makes sure that all the red points are in this region and the blue points are outside. So it will predict a high value for these red points and a 0 value everywhere for the blue points. Is that obvious? How many of you understand that figure? Okay, good. So now I want to show that even in 2 dimensions, I could come up with a neural network which could actually approximate this. And again, what will I look for? A tower maker, right? I just want something which can make towers and approximate it. Okay. So this is what a 2-dimensional sigmoid looks like. This is slightly incorrect because what I have done is I've actually set W2 to 0. So if you, actually I would want you to do this, go back and plot this for W1 equal to 3 and W2 equal to 3. Okay, just go back and plot this and see what you get. You'll not get such a smooth, such a nice looking S, but you will still get something which looks like a snake's hood, right? So you'll still get that S-shaped function. It's just that it will be bent at some points and it will be thinner at some points and broader at the other points. So just go back and see, and then you'll realize what is happening, right? So here, again, what we want to figure out is, from the single sigmoid, I was able to take you to a tower function, right? From a 2-dimensional sigmoid, what does a tower mean here, and how do I take you to the tower? Okay, so that's what I want to do. So I've set W2 equal to 0, and it will become obvious why I have done that. So just understand what the figure is doing, right? So this, if you just look at this is like the cross cut, right? So you're looking at the front view of this figure, and that's just the sigmoid function without the W2, right? And now since I have set W2 equal to 0, no matter what I set x2 to, the same function will get repeated throughout that axis. Do you get that? So that's why this entire function is just getting repeated throughout this axis, and then you just get a similar S-shaped function. Everyone gets that? How many of you don't get that? How many of you get that? Okay. So this, if you look at the front view, this is the sigmoid of one variable. But since I have set W2 to 0, no matter what I change x2 to, the function is going to remain the same. So it will just get copied throughout the x2 axis. Is that okay? Fine with you? Okay. Now, what will happen if I increase W2? W1? Same thing, right? It will just keep shifting till it becomes almost like a 2D step function. Okay. Now, what will happen if I increase B? Shift. I can do the same thing here also. Same logic applies here also. Okay. Now, what is the next step that I'm going to do? Take two of these which are shifted by some point and then subtract. What will I get? Everyone had this figure in mind? So just see, right? So this portion, both are 0. So 0 minus 0 would be 0. This portion, this is 1, but this is 0. So that would be 1 minus 0. And again, in this portion, both of them are 1. So 1 minus 1 would be 0. So you'll get this kind of function. Would you like to live in such a tower? I'm very serious. Yes or no? No. Why? It's open from two sides, right? You can't live in this tower. So you want something which is a closed tower, right? So how will you do that? Give me an intuition. We'll do the reverse thing. What will be set to 0? W1, okay? And this is how it would look. The orientation would change. And again, so notice that this is your sigmoid function. And since I have set x1 to 0, no matter what I change along the x1 axis, the same function gets copied and you get a nice looking sigmoid function, okay? Now again, I'll do the same thing. I'll increase the W. I'll get a close to a step function. I'll increase the B. I'll move along this axis. Next step, take two of these, subtract, get what? Another tower function. This is also not a tower that you like to stay in. So what do I do now? Add them. Sure? Add this tower to the other tower. This is what you did on the assignment? You don't remember. Okay. Fine. So now what will happen if I add these two? Will you get a tower function? What will you get? You'll get a tower function with a parking floor. Right? Is that what you'll get? Everyone understands why this is? Okay. So this portion, both are 0, so you get 0. Same logic applies for all the four corners, right? Is that fine? Okay. Now for this portion, or rather this area, right? So this guy is 0, this guy is 1, so you'll get a 1. The same logic applies for all these four corners. In the center, both are actually 1. So 1 plus 1 would give you 2. So this is 2, this is level 2, this is level 1, this is level 0. Is that fine? So what have I done so far? I've taken my x1, x2, passed it through some transformations, right? What are these transformations we'll see, but transformed it through these multiple hoops, right, where I adjusted the w's and b's, and I have got some z, right? And this is how that z behaves. For different values of x1, x2, I'll get these different values, and these values range from 0 to 1 to 2. Is this picture clear? I've taken my original x1, x2, passed it to some of these transformations, and irrespective of what my x1 to x2 is, this tells me the entire range of values that I'll get. For some combination of x1, x2, I'll get 0. For some combinations, I'll get 1. For some combinations, I'll get 2, and some combinations also between 1 and 2, right? So these places where it transitions. Is that clear? Is that picture clear to everyone? Okay. So now I can treat this as the output z. Okay. Now from here, how do I go to a tower? Threshold it. How will you threshold it? What do you want? You only want this much part to exist, right? This without the parking floor. How will you do it? Any output which is greater than or equal to 2, you want to keep it. Any output which is less than 2, you want to make it 0. If I do this, will I get a tower? Right? Oh, sorry, greater than or equal to 1. Any value which is greater than or equal to 1, you want to keep it. Anything which is less than 1, you want to make it 0. So this entire thing will get demolished. How do you do this? This is an if-else. Okay. What? okay, if else. If something is greater than equal to 0, do something, else do something else. What's that? Perceptron, right? But we don't want to use perceptron. We want to use sigmoid neurons. Have you learned an approximation from a sigmoid neuron to a perceptron? Very high W, right? You get the intuition? Let's see what we do on the next slide. So I take this, any Z which comes from here, I'll pass it through a sigmoid neuron which a very high slope such that the threshold is at 1. Anything which is greater than 1 will pass out as 1. Anything which is less than 1 will go to 0. So everyone sees how we took this structure and converted it to a tower? We have this tower now. Now what do I do with this? I need multiple such towers and I can approximate this. I could put a tower here, here, here and so on. I could have these multiple towers and here of course all my towers would be of 0 height, right, in this region. Right, so now I can cover the entire 2D space with a lot of tower functions and approximate this exactly. That's a very weird statement, approximate this exactly. Right? I mean approximate this to arbitrary precision, right? Everyone gets this? Do you see why we constructed these tower functions? And now we can put them inside this cone and approximate it, okay? Okay, now all this is fine. I was making some towers. Can you now give me a complete neural network which does this? I want you to imagine that. Remember, you're taking, what I'm asking you to do is this, x1, x2. Give me this such that I get this two-dimensional tower. I don't know how to draw it. Something like this, maybe, whatever. Yeah, so I want this two-dimensional tower. What is this network of perceptrons going to look like? Just go back to all the operations that we did and try to imagine in your mind. No, we'll not use perceptron because we can always use a sigmoid neuron instead of a perceptron with a high W. I don't expect you to answer this, I just want you to imagine this, right? Just try with a, there's something known as a pen, there's something known as a paper. Okay, so here's the solution, right? So what's happening here? You have this salinity and oh, actually this is slightly wrong. I don't know why you guys are saying it's correct. Actually at both places I need both the inputs. It's just that in one case I don't care about that input because I've set W2 to 0. So I learn these weights W1, W2, B, W1, W2, B. Of course here the network should learn that W2 is equal to 0. Right, and then it will get this one tower. Gurneet, this needs to be modified. This figure is incorrect. So we need x1, x2 both as inputs, and we need to label it with W1, W2 equal to 0, and B, and so on. Right. So we will discuss this later. Anyways, but you get the idea, right? That you take these two inputs, make one tower, take the inputs again, make another tower, add them up to get this function, pass it through this step neuron function, step sigmoid function, so that you get the tower. So this is one block. You'll have many such blocks, each of which will learn different W's and B's so that they get shifted, and then you'll place them all together. You'll have an aggregator on top of this which will combine them. Just a minute. How many of you get this? Okay, good. Yes, so that's a good question. I'm going to come to that, right? So I have very conveniently given you a solution where I have, what is the bad thing that I have done? I have hand coded these things, right? I have hand coded W1s, W2s and Bs. Is that fine in practice? No, I mean that's where we started off, right? We don't want to hand code these, right? So now you know a learning algorithm for a single sigmoid neuron. Now what you have is a network of neurons, right? For this network of neurons, I need to give you a learning algorithm driven by the objective function that whatever output it gives would be very close to that arbitrary function that you're trying to model. If I give you a learning algorithm, then you would be convinced that if this has to be minimized and the weight configuration which it needs to arrive at as W2 is equal to 0, then the algorithm should be able to do that, right? Because we have some faith in these algorithms in the case of a single sigmoid neuron, that with the right objective function, it will give me a principled way of reaching that objective function. In this big network, my objective function is to approximate this true function, right? So now if I give you that as the objective, that whatever outputs the network generates, right? The network might generate something like this. So that has to be very close to the true output. That's the objective function that I'm going to use in that learning algorithm. And if that learning algorithm works, which we'll prove, then you should be able to arrive at the necessary weights to make this approximation. Right? Is that clear? And in fact, you might not even have to do these multiple towers in practice. All I'm trying to prove is that there's one solution which exists. Right? If there's one solution which exists, I can say that, okay, the network can learn that. That's the only claim I'm making. I'm not saying this is the only solution. Right? Same as in the case of the Boolean functions, where I said that one solution exists where you have 2 raised to n neurons in the hidden layer. That was a sufficient solution. That was not a necessary solution. For the AND function, we were actually able to do it with a single sigmoid neuron. Right? So just keep that in mind. I'm just giving you a sufficient solution. Right? And the network could actually learn something better than this also. Right? This is again a very bulky solution. Why? It scales with the number of neurons is proportional to number of input variables that you have, right? So that's okay for a sufficient solution, but you would want something better than that, right? All I'm trying to say is that it can approximate. I'm just telling you the representation power. And just as we had the catch there, that the hidden layer is very large, the same catch applies here also. Is this story clear to everyone, right? So I've given you a solution. I've not told you how to learn the weights. I've given you a network. Now later on, we'll discuss a learning algorithm for this network. And we'll have some confidence that given a particular objective function, that learning algorithm can strive to go to minimum error or minimize the quantity of that objective function. Okay, that's going to come in 2 lectures from now. Is that fine? Okay. And that was for the tower function. Now I could have actually directly done this, right? So I wanted to approximate these functions. So I could have placed a lot of these kind of things here and approximated it, right? So that instead of that very high slope sigmoid function, I could just use a normal sigmoid function also. Okay? And again, there's an error here, but I hope you get the picture, right? It's just that you feed both the inputs to them. Okay. So for one-dimensional input, we needed 2 neurons to construct a tower. For 2-dimensional input, how many neurons did we need? I'm just counting these because these are simple aggregators, right? And this is one constant at the end. So how many did we need actually? O of 2n. I mean, yeah. So for n, how many would we need? Just try to work that out. Okay? So I'll ask you that in the quiz. How many do we need for n dimensions? Okay. Now, why do we care about approximating any arbitrary function? We'll again try to close the loop now. We saw that we can approximate any arbitrary function, but now again I want to come back to the point, why do we want to do this? And can we tie this back to the classification problem that we were dealing with, right? And this is the data which I had given you, which was there were some points, some values of x and y. Sorry, this should be x1 and x2. Right? So this is pressure and salinity or salinity and density, and this is the output, which is oil. Okay. Now this is what the function actually looks like. Now what would have happened if I had used a single sigmoid neuron to try to approximate this function, to try to represent this function? And sigmoid neuron in 2 dimensions, right? So the 2-dimensional sigmoid. What would have happened? Can you give me one solution for this? Remember earlier I had said that perceptron cannot handle data which is not linearly separable. But then I anyways used it for data which was not linearly separable. And we got some line such that we got some errors. The red points and the blue points were not clearly separated. So I'm asking you for a similar thing here. I force you to use a sigmoid neuron. What would you give me? Is this fine? This is one of the possibilities. Of course, it could have been oriented differently and several things. What is happening here is that for these blue points, it is acting correctly. But for these red points, it is not acting correctly. I'm assuming red is positive and blue is negative. I think, yeah, that should have been the other way around. Yeah, but let's assume red is positive and blue is negative. Again, now for these red points, this part is working fine, but it's misclassifying all these blue points, right? So for all these bad locations, it's actually saying that you can find oil. And for all these good locations, here it's saying that you cannot find oil. That's what a sigmoid neuron would do, right? And you could have multiple solutions are possible here, right? But all of them would have this problem that it will make errors on some red points and some blue points, right? But the true solution that we wanted is something like this. Again, there are multiple solutions possible, right? You could have anything is, and you could have even finer ones, right? You could just have this much. Okay, there are many things possible. This is one such solution. What the illustrative proof told you is that you can actually use a network of perceptrons and approximate this arbitrary function which exists between the input variables and the output variables. Right? This is the function which exists between the input variables and the output variables. Now you could take these multiple two-dimensional tower functions and approximate it. With the catch that you might need many of these in the hidden layer, but you can still do that. Okay? So that's why this theorem is important, because now any problem that you take, right, any problem that you will have in machine learning would always want you to take an x, learn a function of x which takes you to y. This function will have some parameters, right? And now what this theorem is saying is that you could adjust these parameters such that you can arbitrarily come close to the true function, right? So that's the significance of this. And any machine learning problem that you can think of in the sense of classification or regression, you would find that this is useful, right? I'm giving you a very powerful tool to do that. Of course, with the catch that I'm not giving you any bound on the number of neurons that you will need. I'm just saying use as many as you want, right? Is that fine? Okay, so that's where we'll end today's lecture.
So welcome to lecture 4 of CS7015, the course on deep learning. Today we'll talk about feed-forward neural networks and backpropagation. So a quick recap of the story so far, right? So we started with MP neurons. We saw there were some problems with MP neurons. They could handle only Boolean inputs and Boolean outputs, and the threshold needed to be hard-coded. So from there we moved on to perceptrons, which allowed for real inputs, real outputs, and real inputs and binary outputs. And we also learned an algorithm for learning these weights and parameters, right? So we there was no need to hand code these parameters anymore. But then we found that for a single perceptron, there's a limitation. It can only deal with functions which are linearly separable. So then we went on to a multi-layered network of perceptrons, and we proved by illustration that it can handle any arbitrary Boolean function, whether linearly separable or not. The catch is that you will need a large number of neurons in the hidden layer, right? Then we also observed that perceptrons have this harsh thresholding logic, so which makes the decisions very unnatural. It's 0.49, it's negative, 0.51 is positive. So we wanted something more smooth. So the smoothest approximation to the step function, which is the perceptron function, was the sigmoid function. Sigmoid is a family of functions, and we saw one such function which was logistic function. And then we saw that it's very smooth now, it's continuous and differentiable. Now for the sigmoid neuron, a single sigmoid neuron, we saw a learning algorithm which was gradient descent. And we proved principally that it will always go in the direction where the loss decreases, right? So that was the basis for gradient descent. And then we graduated from a single neuron to a network of neurons and made a case that such a network of neurons with enough neurons in the hidden layer can approximate any arbitrary function, right? Okay, so I have told you that it can approximate any arbitrary function. What does that mean? And what is the thing in the network that does all this? All the tower functions, and the tower functions depend on weights and biases. So there, in that illustrative proof, again, we were adjusting the weights and biases by hand, right? We knew that we wanted these very tiny tower functions, and we were doing it. Now from there, where should we go? We need an algorithm to learn these weights and biases, right? So that's what backpropagation is. So today I'm going to formalize these feed-forward neural networks. We just did it by illustration the other day. Now I'll introduce you to the terminology and see what the input outputs are and so on. And then we'll look at an algorithm for learning the weights in this feed-forward neural network. Okay, so let's begin. So a lot of this material is inspired by the video lectures by Hugo Larochelle on backpropagation. He has a course on neural networks. It's available on YouTube. You can check it. Okay, so let's first begin by introducing feed-forward neural networks, right? So what is a feed-forward neural network? The input to the network is an n-dimensional vector. Okay, so that means my input belongs to Rn. That's fine. The network contains L-1 hidden layers. Right? We already know what hidden layers are, right? We have been defining that terminology since multi-layered perceptron. So you have these hidden layers, and there are L-1 of these. And then it has
one output layer containing k neurons. Okay, this is what a feed-forward neural network looks like. What is missing here? The weights, right? So each neuron in the hidden layer, okay, before that, each neuron in the hidden layer and the output layer can be split into two parts, right? So I'll call the first part as the pre-activation and the second part as the activation. Have you seen this split before? Right? What does the pre-activation do? Aggregation. And what does the activation do? Non-linearity, right? So we have this pre-activation and activation at every layer. And AI and HI are vectors. Is that correct? Because this entire thing, or rather this part is H1 and this part is A1. Both of these are vectors, right? And for this discussion, I'm going to assume that everything till here belongs to Rn. Okay, so the input was Rn and all the hidden layers also have n neurons. Is that fine? So please pay a lot of attention to this couple of slides because this is going to stay with us for the rest of the lecture and perhaps 2 more lectures and even for the course, right? So this is very important that you understand this, the way we are defining a feed-forward neural network, okay? The input layer can be called the 0th layer. What I mean by that is that I could refer to this as H0, okay? There is no A0, H0 here because there's no pre-activation activation. You're just given the input, so I'll just call it as H0, okay? And the last layer can be called as H of L, right? Whatever you get from this green part, you'll call it as H of L, okay? What's the dimension of H of L? R raised to k, right? It belongs to Rk because I have said here that you have k neurons, each corresponding to k classes, okay? Now, we have weights between the input layer and the first hidden layer. Now, can you tell me this belongs to Rn? This also belongs to Rn. So what's the dimension of W1? N cross n, right? Because it contains weights for connecting each of these inputs to each of these hidden layers. There are n here, n there, right? So it's n cross n. And what are the dimensions of the bias? N, one corresponding to each of the hidden inputs, fine? And this is only for up to this layer because till here I have assumed everything is n. Now what about the output layer? N cross k, and the bias is k dimensional, okay? So this is what the network looks like, but now I have to give you some functions, right? I've shown you a diagram, but what does it mean mathematically? Because remember that we're always interested in writing something of the form y is equal to function of x, right? And that is not well defined yet. Okay, so let's start defining that. Ignore the red portion for now. Okay, I'll go over it. So each of these activations, right, or rather the pre-activations is given by bi plus wi into hi minus 1. So what it means is that these activations take inputs from the previous layer, multiply them by the weights, and also add the bias. Is that clear? So let's see it, right? For example, if I look at A1, which is this vector. So that's 3-dimensional, and I'm assuming it's 3-dimensional for simplicity. So it's A11, A11, A12, A13, right? And that is equal to, how do I get rid of this? Okay. B11, B12, B13 plus this matrix multiplication. Is this clear to everyone? Okay, I know it's trivial, but I'm still going over it, right? So let's not, okay. And then how do you do this matrix multiplication? Row was multiplied by the column, right? So this is what you will get, right? And in the end, I can write it as this, right? And this looks very similar to what we have been seeing throughout, right? From MP neuron to perceptron to sigmoid neuron, and now this case, right? So it's just an aggregation of all your inputs, a weighted aggregation of all your inputs. That's the case which I wanted to make, right? And that's obvious now. So you understand what these are, right? So this is Rn. In our case, we have assumed n equal to 3. What is this? I'll keep asking till this is completely fine with everyone. Rn, and this is n cross n, and this is n cross 1, r cross n, I mean Rn, sorry. Is it fine? So everyone understands the operation happening here. It's a weighted aggregation of your inputs. So every guy here is a weighted aggregation of all the inputs, okay? Now after that, I do hi of x is some function of ai of x. Okay. What does this mean? So this is again a vector, right? I've assumed that it's three-dimensional. So these are the three elements of hi. So these are the three guys. Now these are some function of these light blue guys. Okay. Now how does that function operate on the vector? It operates element-wise. Not all functions on vectors are element-wise, but this particular function we are going to do element-wise. That means that h11 is equal to g of a11, h12 is equal to g of a2, and h13 is equal to g of a13, right? Where if I take g of a13, one of the functions that I could choose is the sigmoid function, so it would just be 1 over 1 plus e raised to minus a13, right? So what is happening is I'm taking this value and passing it to the sigmoid function to get, I'm taking this value and passing it to the sigmoid function to get h11, taking this value, passing it to the sigmoid function to get h12, right? So the key thing to understand here that this is a element-wise operation, right? It's not operating on the vector, that doesn't make sense. It's operating on every element of the vector, right? Okay. And G is called the activation function. It could be logistic, tan H, linear, anything, right? So we'll see some of these functions later on, okay? Now, the activation at layer I, this is supposed to be activation at the output layer. The activation at the output layer is given by the final function, right, which is f of x is equal to O of a of, so let's see. So this is a3. In our case, L was equal to 3 because we had L minus 1 hidden layers and the Lth layer was the output layer, right? So this is AL. So this is what I have computed here, the light green part of the figure that you see, right? Now based on that, I want to produce an output, right? So that day someone had asked me a question that why do we always choose sigmoid? Because sigmoid will clamp the output to 0 to 1. What if I want to predict the amount of oil which will not be between 0 to 1, right? That's why for the output we'll use a spatial function that we'll call the output function, and later on I'll show you that it depends on the task at hand. Okay, so it's going to change with the task that we're going to do, right? So we are just going to say that the final output, which is h of L, is equal to some function of the pre-activation at that layer. Is this terminology clear to everyone? How is each function operating? Is that clear to everyone? Okay, and we'll see some examples of the output activation function. Fine. Now just for simplicity, I'm going to remove the x's from the bracket, right? So instead of calling everything ai of x, hi minus of x and so on, I'll just call them ai, hi and so on, right? So that just simplifies things. But we know that everything is a function of x because x is the input and that passes through some functions and we get the final output. Okay, fine. So this is the notations that we are going to use. Is the dimension of everything that you see here, every variable that you see here, completely clear to everyone? Dimension of ai, bi, w, hi, x, everything is clear? Okay, and the output layer has a slightly different dimension than the other layers because there we have k classes as opposed to n neurons everywhere else. Okay, fine. Now, I need to put this in the paradigm that we saw for supervised machine learning. What were the 5 components there? Data, model, parameters, learning algorithm, objective function, right? Okay, everyone remembers that? Okay, so I said that we'll do deep neural networks and we are trying to write this y hat as a function of x. But then what I gave you is just a diagram from which this is not clear whether y hat is actually a function of x. How many of you think y hat is actually a function of x? Very few, okay. So let's see what exactly is our model assumption here, right? So the question, let me repeat the question just to be clear. So I had said that we are given some data. We don't know the true relation between y and x. We make an assumption that y is related to x using some function f, right? And it has some parameters. And then we like to try to learn the parameters of that function. So what is the function here? So what is your model? What have you assumed as the model? Can you write y as a function of x? If yes, what is that function? How many of you have the answer or think you have the answer? Okay, I think I can't wait more. So I'll give you the answer, then it will become very obvious. Okay, so this is how y is a function of x, right? So let's see what is happening. I took the original x, which was this. I transformed it, added b1. That was the dash at layer 1. No, this thing. Pre-activation at layer 1. I passed it through the activation function, right? Okay, now again, let's be clear about the dimensions. What's the dimension of this? N. What's the dimension of this? N cross N. So what's the dimension of this product? N. What about this? So what's the final dimension of this? Rn. Now you're passing it through a function g. That function is operating element wise. So what's the output dimension? Rn. So this is again Rn. Okay, now this. So now you see the whole story, right? So now this n cross n guy multiplies with this n guy. Again you get a vector. Again pass it through a non-linearity. Was it so hard? It's obvious now, right? You just take an x, just note down all the transformations that you have done. That's what a function does, right? It passes it through the through first a linear transformation. This is a linear transformation, then a non-linear transformation, then again linear, non-linear, and so on, right? So just see how far we have come from where we started off, right? We started off with simple things like W transpose X, right? That was the perceptron model, where we were taking decisions based on W transpose X, and we were saying y is equal to 1 if this quantity is greater than something, y is equal to 0 if this quantity is greater than something, right? That's where we started off with. We made it slightly more complicated by doing this. This was sigmoid neuron. Now from where have we gone? To this, right? So we have increased the complexity of the network. With great complexity comes great power, right? We have already seen the representation power of deep neural networks, right? So it comes from this complexity that you have. You have a lot of linear and non-linear transformations, right? That adds to the complexity of the network. It has more parameters. At each linear transformation, you have some parameters, and you're also using a lot of non-linearity. So that's the reason why deep neural networks are so powerful, right? Do you get that? Okay, fine. So just to impress again, right? So any machine learning algorithm that you have, you should be able to write it in this form, right? That y is a function of x with some parameters, and then your job boils down to learning these parameters, right? It just happens that here y is a very complex function of the inputs. Is that clear? Okay, so I'm not deviated from the original story. I'm still being able to write y as a function of the x with some parameters. Okay, what are the parameters? All the w's, all the b's, right? So w1 to wl and b1 to bl. And the algorithm that we're going to see today for learning these parameters is called gradient descent, but we'll use it with backpropagation, where backpropagation will help us to compute gradients. It's okay if it doesn't make sense at this point. That's what the lecture is supposed to be about, right? So, and what's an objective function? Loss function. So I could just go with this loss function, right? Okay, there's an error here. I thought we corrected this. There's a summation. So actually these are vectors, right? So this doesn't make sense. So you should have summation j equal to 1 to k yij minus yij. Does that make sense? So this is the vector y hat. Okay. For the ith example, it will be called as y hat I, which will have k elements, right? So y hat I1, y hat I2 up to y hat ik, right? So that's what my predictions are, and I'll have the corresponding true vector also. I'm trying to take the difference between them, which is going to be an element-wise difference. Everyone understands the error in the slide? How many of you don't get it? How many of you get it? If you don't get it, please raise your hands. It's a minor thing, I can correct it. Okay. So, okay, is the paradigm clear now? Okay, and how does deep neural networks fit into this paradigm? Okay. Now we'll move on to the next module, where we want to learn the parameters of feed-forward neural networks. And we'll first start with some intuition and then get into the mathematical details. Yeah, so we have introduced feed-forward neural networks, and we are now interested in finding an algorithm which can allow us to learn the weights of this network. Okay. Okay. So recall our gradient descent algorithm. This is how it looked. Okay. I had initialized those two parameters W0, B0, and then I was iteratively doing this in a loop. At every step, I was moving in a direction opposite to the gradient at that step, right? Now, can I write this a bit more compactly? We can write it using vectors, okay? So, are you okay if I write it this way? So, these two was actually nothing but a vector at every point, right? So, I can just write it this way. So, theta is the vector containing W and B, okay? So, or theta is a vector of all the parameters that my network had. It just so happened that that network had only two parameters, okay? So, you see where I am going with this? How many of you see where I am going with this? Okay, good. So, where delta theta t, right? Just to remind you, it was this, the collection of all the partial derivatives with respect to all the parameters. In this toy example, all was equal to 2, right? We just had two parameters. Now you see where I'm going with this? Okay. So now in this feed-forward neural network, instead of theta equal to w comma b, what do we have? Theta is equal to so many parameters. Okay. So what would grad of theta t now be? Partial derivatives with respect to all the weights. But there is a problem here, right? This is a matrix. How do you take the partial derivative with respect to a matrix? Who asked you to use a matrix? How do you take the partial derivative with respect to the matrix? So what I'm interested in this, right? That's the question. I know there is some loss function, which is a function of theta. One of the elements of theta is this matrix W1, which belongs to R n cross n, right? And now I want the derivative with respect to W. So let's see what I'm trying to do. This is a scalar. I'm to take the derivative of that with respect to a matrix. What is that? The derivative with respect to every element of the matrix. Okay. So we can still use the same algorithm, except that this grad of, so now I could just say that theta 2, initialize all the parameters in theta naught, right? Compute the gradient with respect to all of them, and then do this update, right? I could just, instead of putting them in matrices, I could just think of them as a large vector. Just at initially I had just had w comma b. Now this vector is even more large. In fact, I'll show you actually how it is, right? So this is the grad with respect to theta looks very nasty now, and this is how nasty it looks, right? So you have this weight matrix W1. You have the derivative with respect to the first element of W1, all the way up to the last element, right? So with respect to all the n cross n elements of W1, what's the next entry going to be? W2, 1, 1 to W2 NN. Next, up to WL11, okay? And then after this, what is remaining? Biases, right? So you have B11 to B1N. There's slight error here, but intentionally, this actually is K, because K is not equal to N, right? The last layer has only K parameters, but I just, so that it looks okay, right? Is this clear? So these are all the partial derivatives that you need, right? You don't need to worry about taking a partial derivative with respect to a matrix. It just boils down to taking the partial derivative with respect to all elements of the matrix. So earlier you just had two parameters. Now you have these n cross n plus n cross n up to L, right? So L into n cross n plus L into n. That many number of parameters is what you have. You get the calculation, right? Or rather you have L minus 1 layers, each of which has n cross n parameters, right? And L minus 1 layers which also have the biases. So these are the W's, these are the B's. Then the output layer, one layer which has n cross k parameters and k cross 1 bias. So these are all the number of parameters that you have. And this is exactly what this size of this matrix is, right? It has all these parameters. And you need to compute the partial derivative with respect to each of these parameters. Okay? Fine? So this is what grad theta is composed of. It's composed of the partial derivatives with respect to all the parameters of your network. Okay? So now if someone gives you each of these quantities, some oracle gives you each of these quantities, then can you apply gradient descent? Right? You can use exactly the same algorithm that you were using earlier, just the sizes of all your vectors changes. How many of you are convinced that you can use gradient descent? This is not a trick question. How many of you are convinced? Okay, how many of you are not convinced? Assuming that someone has given you these quantities, right? I know this is hard to compute. We'll see how to compute that. But let's assume someone has given you this. then you can use gradient descent. That's what the case I made on the previous slide, right? That you could initialize with all the parameters, compute the gradients with respect to all the parameters, and just do this update, right? Okay, fine. Okay. So now we need to answer two questions. First is, this is the key question, right? Because we are taking derivative of what? Loss function. So we need to know what the loss function is, right? That's a crucial question, right? And then we are taking derivatives with respect to all these elements. So whatever I told you, that assume that Oracle gives you, now you have to do the hard work and actually find it out, right? So if you can answer these two questions, then we are done. We have an algorithm for learning the parameters of a feed-forward neural network. You will agree that if we have these two elements, then we are done, okay? So here's where we will end this module. We go on to the next module where we'll be talking about output functions and loss functions, okay? So the question that we are going to focus on is how to choose the loss function, but I'll show you that it's tightly coupled with the choice of the output function also. Remember that we had said that we have a spatial O function as the output function. I've not told you what that O is, and now that's what we are going to define. Now the choice of the loss function actually depends on the problem at hand. And that's exactly the question which had come up, right? That in some cases, it's okay to have sigmoid as the output function because your values are between 0 to 1. But what if there are cases where your output is not between 0 to 1, right? So it definitely depends on the choice of the, on the problem that you're trying to solve. So we'll illustrate this with the help of two examples. And these two examples will cover a broad range of problems that you will encounter if you're working in machine learning, right? So the first problem is, again, you're given the input as movie. You're using a neural network with L-1 hidden layers and an output layer, y hat, right? So this is, this is a true one. So you have an output layer, and the output layer is going to predict the IMDb rating, the critics rating, and the Rotten Tomatoes rating. Is that fine? Okay. So what kind of problem is this? People who have done machine learning? This is a regression problem. And notice that the output values that you want to predict are not bounded in by 0 and 1. They're still bounded by 1 to 10, but in general, you could imagine that there could be problems where there are no bounds at all, right? It could be a very large number. Is that clear? Okay. Now here yi belongs to R3. So remember, in all these cases, we were assuming that we just want to predict one value, but nothing stops you from predicting multiple values at the same time, right? So your output is now 3-dimensional. You're taking an n-dimensional input and trying to predict 3 values from it, okay? Fine. The loss function should capture how much yi hat deviates from yi, okay? So this is a valid, or maybe we corrected on this slide, yeah, okay. So this is the formula which was supposed to be there, right? So you have predicted 3 values, and you know the true 3 values, you just take the difference between these, right? Is that clear? The first element of the predicted value minus the first value of the actual value, and so on for all the 3 values that you want to predict. Okay? Now you have a loss function, but what should be the output function in this case? Can it be the logistic function? Yes, no? It will be bounded between 0 to 1, and you know that your output cannot be bounded between 0 to 1. Okay? So in such cases, then what is a good output function to use? One option is to scale it, right? So I'll keep that aside. Why do that? It's unnatural, right? You're actually clamping it and then trying to scale it, right? So can you do something more natural than that? Just use a sum, which is linear function, right? So what we could do is, we could have O as a linear function. So what that means is, again, remember that this is A of L, okay? And I know all the computations that have happened so far. Linear transformation, non-linear, linear, non-linear, and then again linear. So I've computed A of L. From that, I want to compute the final output, right? So I could just have it as a linear function of the input, which is A of L in this case. Does it make sense? How many of you feel it makes sense? Okay. Why? Because now it's no longer bounded, right? You could, this linear transformation, your weights could be adjusted in any way to get a value whatever you want, right? Whether you want it between 1 to 10 or 1 to 100 or 1 to 1000, these weights could be adjusted to do that, right? So at least you're not bounding it, and it is free to learn what's the range. From the data, it should be able to learn that how should you adjust these W's so that you get the desired range. Now tell me, why would it not happen that you learn W's which start predicting values like 1000, 10,000 and so on. In this particular case, where your input is bounded by 1 to 10, or sorry, your output is bounded between 1 to 10. Why would it happen? This is my argument, and you prove me wrong, right? I would say that, oh, if you have chosen a linear transformation which is not bounded, the network could learn weights which start producing a rating of 10,000, 20,000 and so on, because it's not bounded, right? But you know that that's wrong because the ratings can only be between 1 to 10. So why would that not happen? Because you're minimizing the loss function, right? So if you start predicting values like 10,000, when your actual rating was 9, then you'll have a 10,000 minus 9 the whole squared loss. That's a very high loss. So it will start moving you away from that configuration, right? So the training is always guided by the objective function. So if your training happens well, it will try to prevent this, right? Okay. Now suppose, let's take a simple thing, right? That you are given our same ball example for probability, right? So you're given an urn which has balls of 3 colors, say black, white and yellow, okay? And you have put the balls in that. So you know that the true probability distribution is actually 0.35, 0.25 and 0.4, right? For red, black and white, okay? This is the true probability distribution. You have put, say, thousands of balls in an urn, okay? Now what you do is, you just allow me to peep into the urn, or you allow me to take some samples from there. You tell me, okay, take these 100 samples, and you ask me, tell me what this probability is, right? So this is the true probability that you know is true, right? Because you know it because you have estimated it, okay? Now you just give me a small sample from there and ask me to estimate it. And based on that, I actually estimate this, okay? So there was a true probability distribution and an estimated probability distribution. Now I want to find out how wrong I went, right? Afterwards you tell me the answer. You tell me that this is what the true was and this is what you predicted. Now I want a way of computing how wrong I was, right? So how do I do that? You already know this. And these are 2 vectors. What can I do? You could just do the this is valid. Anything wrong with this? In principle, no, right? You could just treat these as any 2 vectors. You have a true value, you have a predicted value, you just take the squared error difference between them, right? But you know this is a probability distribution, right? So you should be able to do something better than this. You know this is a spatial quantity. This is not just any number that you're predicting. You're trying to predict a distribution. So you should be able to do something better than that, right? So that's what we want to see, how to do something better than this. Okay, that's what our quest is, okay? Now, again, while we are at this, right, I also want to make because this is something people don't immediately understand. So I just want to make a case for something else. I'll just do that, okay? Now, suppose there's this IPL, okay, and there are 4 teams in the semi-final, okay? Let's call them A, B, C, and D, okay? Now, I was not in town after the semi-final, so I just know the results up to semi-final, and then the finals also happen, and one of these teams wins. Let's call it the B team, right? The B team wins. Can you express this in terms of probability? Can you express this in terms of a distribution? What do you mean by 0 and 1? B has 1. So it's a certain event because it has 1 now. So what's going to be the distribution? 0, 1, 0, 0, right? So this event happens with 100% probability, okay? Now the same case, okay, so now let's do the same thing, right? As I said, I was not in town, right? And you asked me, tell me which team would win, right? So I know these 4 teams have qualified in the semi-finals, and I know who the players are and so on, and with my limited knowledge of cricket, I'll predict something, right? So say I predict this. Okay? Can you again tell me how wrong I was? You know what the true label is, and you know what I predicted. You can tell me how wrong I was? Okay? So the case which I'm trying to make is that even if the event is certain, you can still write it as a probability distribution where all the mass is allocated to the correct output, right? Can you relate this to a classification problem? When you see training data, you have already observed it. Suppose there were 4 classes possible: apple, orange, mango, and banana. If you've seen it's apple, and if you ask you what's the distribution, what will you tell me? 0, 1, 0, 0, right? You will express it as this one hot vector where all the probability mass is concentrated on the guy which is correct, right? So even certain events which happen with certainty, you can write them as a distribution, right? Where all the mass is allocated on the true label, right? So that's how all classification problems, when you're dealing with multi-class classification problems, it's often the case that you will write it as this, that your true label is given to you in this format. There were 4 possible events, 4 possible classes, or k possible classes, out of which only one is correct, right? And then you make a prediction, and you want to now find out how different was your prediction from the true label. Is that fine? You get the setup, how this relates to a classification problem, and that's why this is of interest to us. Okay. Okay. So this, so we'll see this soon. Now the next thing that we need is, how many of you know what is entropy? Forget about cross, just entropy. Okay. That's why I've left 2 slides intentionally blank. Okay. So now let's see, where do I go with entropy? Okay. How many of you know what is expectation? Please. Okay, good. Fine. So again, the same thing. Now, I knew that this was the distribution which I think. I'm into gambling. I'm not, but I'm into gambling. And I try to bet on these teams, right? And I bet some amount on each of these. Can you tell me what's the expected reward that I'll get? No, what am I saying? Okay. Wait. Suppose this is the case that if team A wins, I get 10k rupees, or my net profit is 10k rupees. If team B wins, my net profit is 20k rupees, and C and D, so on, right? You get the setup? For every event, there is an associated value with it. This is the value of event A winning, B winning, C winning, and D winning, right? So the net profit in each of these cases. So what's my expected net profit? No, give me a formula. Don't ज़्यादा दिमाग मत लगाओ. Huh? Sigma over all events, right? How many events do I have here? 4, right? So rather I should say I equal to A, B, C, D, right? Probability of I multiplied by the value associated with that event, right? So this is how you compute expectation. Okay, everyone gets this? Okay. So now suppose, say I'm doing this, right? There are suppose 4 symbols. I don't know what I'm teaching. Okay. And I am trying to communicate this from a source to a destination. Okay. And now suppose these are the 4 symbols that I give. And if one of these symbols is, say, with probability 1, and if I transmit it, what's the information that this guy gets? So this is assume that A is that sun is going to rise today. If I tell you this when you're sleeping in the night, what will you tell me? Ja, soja. Okay. So basically you're not gaining any information, right? Because it's a certain event. You know this is going to happen, right? Now one of these events, suppose I'm going to say that there's going to be a cyclone tomorrow morning. What's the probability of a cyclone happening? In Chennai, almost 1, but still, it's a very rare event, right? So if I tell you something which is very rare, that message has a very high information content, right? So an event which has a very high probability has a very low information content, and an event which has a very low probability has a very high information content, right? So you can measure the information content of an event. Okay. So the point is that what you can have is that the information content of an event, you can write it as, how many of you get this? How many of you have seen this before? Okay, all of you have seen this, right? So this is the value associated with an event. Okay. Now can you tell me what is the expected information content? For every event now I have given you the value associated with that event. So what's the expected information content? Summation P of I into information content of I. And this is of course log, right? So it would be, so what is this called? This is called the entropy. Okay. Now what is cross entropy? How many distributions are you dealing with here? One, which is the P distribution, which tells you how likely these messages were, and based on that you're trying to calculate the entropy of this situation, right? So now what is cross entropy? You have a true distribution, say you have a predicted distribution, okay? This is what you predicted. So that means according to your predictions, the information content of every event is going to be log of Qi, because that's what you predicted, right? But what are the actual probabilities with these, which these events are going to occur? Pi's, right? So then the expectation has to be computed over Pi's, right? So then what you will have is summation Pi log Qi. So this is what you estimated the information content to be, but the actual events are going to happen with this probability, right? So this is your value associated with the event, and this is the actual probability of the event, right? So this quantity is known as the cross entropy. Is it clear? Okay, and this is a way of measuring when would this be when would this be minimized? When both are same. So that means if your prediction is very close to your true distribution, this quantity will be low, minimized actually. So that's what you wanted actually. You wanted to predict some distributions in all of these cases, and you wanted a measure which tells you that this prediction was good. And what's the definition of good? It's as close to the correct value. So cross entropy gives you a measure of telling how close a predicted distribution is to a true distribution. Is that clear? Okay. So now instead of using the squared error, which was actually Pi minus Qi, right? So Pi was my true distribution and Qi was my predicted distribution. I can use cross entropy, which is given by this formula. And it does the same thing. It gives me a principled way of measuring how close my predicted distribution is to my true distribution. Do you get this? So now, so this was for whatever we have done so far, right? Till this point, this was for regression, right? Now I wanted to enter into classification, for which I have built this setup of how to take the difference between two distributions, right? So now let us consider this problem where we have this situation, right, which is a classification situation, that you're given 4 possible classes, out of which one is the correct class. And this is the true data given to you. This is the true distribution. All the probability mass is focused on one of these classes, okay? Now we want to, given an image, classify this into one of k classes, okay? We could again use the squared error loss, but since we are dealing with probability distributions here, we want to use something special. So before we get to what this special is going to be, what do I first need to tell you? In the earlier case, my output was not bounded. Was it also dependent? Was there any condition on if the IMDb rating is something, the critics rating should be something else, or the Rotten Tomatoes rating should be something else? No. Now in this case, is there a tightly coupled behavior between the outputs? Why? Because they should sum to 1. We are trying to predict a probability distribution, so the sum should be 1, right? So I need an output function which ensures this. You get the setup? Okay. Now we should ensure that y hat is also a probability distribution. Whatever we are predicting is also a distribution. Okay. So now can I use the sigmoid function? Yes, it will give me values between 0 to 1, and probabilities are between 0 to 1. But the sum would not be 1. So sigmoid is ruled out. Okay. So what we use is something known as the softmax function. How many of you have seen this before? Please everyone raise your hands, otherwise you'll get 0 on the assignment. Okay, fine. So what does this function actually do? Let's look at this function, right? So here you had AL, which was say AL1, AL2, AL3, right? Suppose we had 3 classes, okay? So from here I actually want to go to HL, or rather I want to go to y hat, right? Which is going to consider y hat 1, y hat 2, y hat 3, right? It's going to give me probability of each of the 3 classes. Let's assume there are only 3 classes, right? So now what this function does is, How is it going to predict y1 hat? Suppose these values were 10, minus 20 and 30. So what's going to be y1 hat? It's going to be e raised to 10 divided by e raised to 10 plus e raised to minus 20 plus e raised to 30, right? So now you see how the output is computed from each of these values, right? So why did we do this e raised to stuff? Why couldn't I have just taken 10 plus minus 20 plus 30 divided by the sum? Because we have negative values, right? So once we take the exponent, even the negative values become positive, right? So that's why we need the softmax function. I hope all of you wrote this in your assignment. They did? Okay, fine. So you get this? We have a different output function now, and this output function, does it make sense? Okay, it gives us a probability distribution now. The summation would be 1, and each of these values would be between 0 to 1. That's exactly what we wanted. Okay. And now that we have ensured that y and y hat both are distributions, what is the objective function that we are going to use? Cross entropy. How many of you are convinced it's cross entropy? We have two distributions now. We saw that a principal way of computing the difference between two distributions is the cross entropy. So we'll use the cross entropy. Now can you tell me something about this sum? There's something special about this sum. What are these? The true values. And these are the predicted values. Okay. What is so special about this sum? How many terms are there in this summation? K, as many as the number of classes. In this case, 4. How many of those terms will go to 0? All but 1, right? Except for the correct class, everything else will go to 0. So this just boils down to the following loss function. That if L is the true class, right? For that class, YC is going to be 1, it is going to be 0 for everything else, right? That's exactly what this vector tells you. Only that term will remain. So we're actually trying to minimize this quantity. Okay? Let's see. So for classification problems, this is your objective function. You either minimize the negative log of y hat L, or you can say you are maximizing this thing. Okay? Now what is this quantity y hat L? No. It's a predicted probability of the correct event, right? Okay, so this is a probability. Okay, now wait, this is an important question. So you have y hat L here, and this is a function of, this optimization problem is with respect to theta. Is this a well-formed objective function? Does y hat L actually depend on theta? Yes, it does, right? So theta, because y hat L is a function of all these things, right? Everything here, and then a log on top of that, right? So it is actually a function of all your parameters. So this is a properly set objective function. We are trying to minimize or maximize with respect to theta, okay? And you told me that y hat L is actually the probability of the predicted probability of the correct class, okay? Hence this quantity is also known as the ML class, pattern recognition class. Log dash of the data. You're all good at fill in the blanks. Okay, so is the probability of the x belonging to the Lth class, and then hence y hat L, because it's the probability, it's the likelihood of, it's called as the log likelihood of the data. Log likelihood. Okay, is that clear? Okay, so what have we done so far? We started with a feed-forward neural network. We defined the hidden layers and the input layers and the weights and the biases. We kept a provision for the output layer to be something special, right? Then we went to two classic problems. One is regression and the other is classification. In regression, we wanted to predict values of all sorts of ranges, right? So we decided to use a linear layer there so that there is no bound on the values that you can predict, and your objective function should take care of where the bound lies. It should not allow values which are way off from the true values, right? And that's why we use the squared error function there. The other problem that we looked at was classification, where we saw that the label actually can be treated as a distribution where all the mass is focused on the true label and 0 everywhere. And our job is then again to predict a distribution. So we are given the true distribution and we predict another distribution. So at the output again we want something special in this case, which is a distribution. So to ensure that, we use a spatial function which is called the, who said sigmoid? softmax function. Okay, right? Fine. And then we got a prediction, which is a probability distribution. And then how did we find what was the objective function? What's the difference between the true and the predicted? The cross entropy, right? So we use cross entropy as the objective function. And then with some simplification, we realized that it just boils down to maximize the log of the probability of the true class, or rather log of the predicted probability of the true class. Okay. So now let's look at the summary. So if your outputs are real values, what is your output activation going to be? Linear. What's the loss function going to be? Squared error. Okay. If your output is a distribution, what's the output function going to be? Softmax. Okay. What is this loss function? Squared error. Cross entropy, right? Now this grid, right, actually takes care of a wide range of problems that you will see, right? Think of any examples that I've been giving you so far, movie prediction or sentiment prediction or image classification, anything, all of that you can fit into this framework, right? And so if you know these two loss functions, how to deal with them, then you can deal with a large class of problems that you're going to deal with, okay? And for the rest of this lecture, which will happen tomorrow, we're going to focus on this. Now this particular output function and this particular loss function, how do we compute? I have the loss function. What am I going to compute now? The gradient with respect to all the parameters. So this is what we are going to focus on, right? So we have seen the loss function in detail. We have seen that the loss function is tightly coupled with the output function. Now we are all set that given this loss function, how do we start computing gradients of this loss function, right? Fine.
Now we'll go to the next module, where we'll first see how to compute the gradient with respect to the output units, because that was the first guy in our chain, right? That's the first person that we need to talk to, okay? So that's the part that we are going to focus on. So this is the output, and when I say I want to compute the gradient with respect to output unit, what do I actually mean? What's the quantity that I'm looking for? I'll help you out. Actually, what I meant by output unit is this entire thing, right? So I actually meant ALs, okay? But it's a fair answer. Even the y hat is a fair answer, okay? In fact, I'm going to start with y hat and then go to AL. So I'll have to start with this guy and then come to this guy, right? So this is the loss. This is y hat, which is equal to y1 hat, y2 hat up to yk hat. So these are the k values that we have here, and we are looking at cross entropy. That means we are looking at the classification problem, right? So we have got a distribution over the k classes. That's what y hat looks like. And we know that one of these guys is the right class, maybe say y2. So the loss function is minus log of y hat 2, because 2 is the correct class in this toy example that I'm considering, okay? So the loss function, I'm just repeating the definition, right? That's how the loss function is, okay? Now, oh God, okay, so again, this is what our y hat looks like, okay? Now I want to compute the gradient with respect to any of the output units, right? So it could be y1, y2, y3, y4 up to yk, right? So this I actually can take values from 1 to k, in this case 1 to 2, right? Okay. Now can you tell me what is this loss? Okay, this much is fine. Can you tell me what is this derivative? Minus 1 by y hat L, if I is equal to L, and 0 otherwise. How many of you get that? Cool, okay. So it's a very simple thing, right? You can think of this as z and this as y. Only if z is equal to y, then the derivative would exist, otherwise it was going to be 0, right? Okay, so how do I write this iffy part using? How many of you have seen indicator variables before? Okay, good. So this is what you are telling me, right? It's going to be minus 1 by y hat L if I is equal to L, okay? And if I is not equal to L, then these two things are not related, right? This is a function of something else and you're taking a derivative with respect to a different quantity. So it's a constant with respect to that quantity and the answer would be 0, okay? Now I'm going to write this as this, right? So this is the same as saying, so this variable actually, this is known as the indicator variable. It takes on the value 1 if the condition in the bracket holds, otherwise it takes on the value 0. So this is exactly, I'm writing exactly this, but in a more compact manner, okay?
Is that clear to everyone? Okay. So this is what the quantity, this is the quantity that we have computed with respect to one of the output units. Okay. So this is what? Derivative, partial derivative, gradient. How many of you say derivative? No one likes derivative. Partial derivative. That's always the safest choice. Partially to right hoga hi. Right. And gradient. Oh, there's one brave soul who says gradient. Okay. Don't worry, we'll fix that. Okay. So this is the partial derivative. Why? Because my y hat is actually a vector and I'm taking the derivative with respect to one of those guys. Okay. Now, if I want the gradient with respect to y hat, what would that look like? A vector which is a collection of partial derivatives. Okay. So let's see. This is the quantity that I'm interested in. I'm interested in the gradient of the loss function with respect to the vector y hat. So remember, the vector y hat is y1 hat, y2 hat up to yk hat, right? So this gradient is going to be a collection of the partial derivatives with respect to y1 hat, y2 hat and so on, right? Okay. Now what is each of these quantities? How many of you are fine with this? How many of you are not fine with this? I did not see as many hands as I would have liked. Okay, how many of you are fine with it? Again, please raise your hands up, up, up. Okay, fine. Is this okay? Right? So it's simple, right? So this quantity, the derivative is either going to be 0 or it is going to be 1 by y1 hat, right? If L is equal to 1, right? And that's exactly what I have done. So now how many elements here are actually going to be non-zero? At a time, how many of these is going to be non-zero? 1. Which one? The one corresponding to L, right? Everything else is going to be 0. So this is a dash vector, one hot vector. Okay. So now I'm going to write one hot vector like this. What have we done? Okay. Okay. Where EL is what? One hot vector such that its Lth entry is 1. Okay, that's how I'm going to define EL. Is that fine with everyone? Okay. And so you see the story, how we went about computing this. We started with a partial derivative with respect to one of the guys, right? We found a formula for yi. We saw that this formula is generic enough, and so now we can compute the gradient, which is a collective of all these yi's where I ranges from 1 to k, right? And then we just put that in a gradient vector. So this story is going to repeat throughout the lecture, where we try to compute the gradient with respect to one guy and then generalize, we compute the partial derivative with respect to one guy and then generalize and try to find the gradient. Okay, fine. Okay, so what do I have so far? I have this quantity. Till which part of the diagram am I currently? The dash green part, dark green part. Okay, I'm till here. I need to go till the light green part, right? That's collectively the output unit. Okay. Although I've divided into two halves, but when I say output unit, I mean that output neuron, right? Complete neuron. Okay. So what I'm actually interested in is these quantities, or more specifically, okay, this is what I'm interested in. What is this? One of those guys, right? This AL is actually AL1 up to ALK, right? So this is one of those guys. So this is going to be the gradient, this is going to be the derivative, partial derivative, sorry. Okay. Now how do we proceed from here? Okay. Now I'll again have to compute this. You already know that. Okay, good. But before that, I want you to answer one question, right? So y hat L, okay? What is y hat L? It's the output corresponding to the correct class. Does it depend on an arbitrary ALI? So in the previous thing we saw that only when I is equal to L, there is a connection. In this case, is there a connection always or only when I is equal to L? Always. Why? Softmax. So denominator has all the ALI's, right? So this is there, right? So y hat L in the numerator, of course, it only has this unit, which corresponds to the Lth. I probably did not choose my variables very well. So Lth component of a capital L, right? But in the denominator, you have the entire sum, which means that every output guy here, each of these dark green guys, depends on each of the dash green guys, light green guys. Okay, good. So that's at least settled that we can always compute this partial derivative. We don't need an if else here. There's no thing like L is equal to I, then what will happen, right? We'll always have this partial derivative. Is that clear to everyone? Okay. So we'll now derive the full expression for this. So this is what we are interested in. Is this fine? So this is a function of the form. So you're taking, okay, how do I say this? So, yeah, this is log of a function. So first you will take the derivative with respect to log and then push the partial derivative inside, right? So that would be minus 1 by y hat L and then the derivative with respect to y hat L. Okay. Now what is y hat L? The softmax function, right? So it's the Lth entry of the softmax function applied to that output vector. What's the output vector? AL, right? So it's the Lth entry of the softmax, or Lth entry of the function applied to the output vector. Is that fine? Everyone gets this? I don't see a lot of thoughtful nodding. Okay, right? So this was our AL. What is our output? Right? So now one of these guys here is the Lth guy and one of these guys here is the Lth guy, right? So what you do is you take this, you apply the softmax function to it, which again gives you a vector, and now you are interested in the Lth component of that vector. Okay, that's what this quantity means. Okay, it should be clear now. Now I'll just do some simple math stuff here and we should be able to derive this. Is it fine? I've just replaced it by the actual softmax formula. This is a derivative of the form u by v, right? So what's the formula for that? Yeah, perfectly right. Yeah. So this is what it would be, right? I mean, you all know this. I'm not going to spend time on this, right? So now I'm just going to substitute the values here. Yeah, it's getting a bit nasty, but it's not very difficult, right? So this is our g of x. So I'm taking the derivative of that. Then this is this 1 over h of x. You can just figure it out, right? I mean, everyone just read this for a few seconds and let me know if this is not clear. This is g, this is h in this formula, right? So I've just substituted the g's and h's in the formula. How many of you get this? Okay, how many of you are still struggling? Okay, not. Okay, if this is clear, then the rest of it should be fine. Now, what is this quantity going to be? It's derivative of the form e raised to x, right? So it's e raised to x, always. If I is equal to L, right? So now we have this dependence because we are looking at the numerator, but the numerator only depends on the Lth entry, right? So now you're trying to take the derivative of the Lth entry with respect to some arbitrary ith entry. So only if L is equal to I, you will get the derivative, right? So is this correct? Okay. Now what about this? How many terms in the summation would remain? 1. Which one? Where I dash is equal to I, right? So the ith guy would remain. Okay. The rest of it is straightforward, right? This square I have just divided into 2 parts. Okay. Now let's see. Can you simplify this? Because I can't. Yeah, I can. Okay. Can you simplify this? What is this? Softmax. And which entry of the softmax? Lth entry. Ith entry. Lth entry with the indicator variable. Okay. Okay. But what is this? This is our input. Hidden layer. Output. Okay. So, yeah. Okay. Now let's see. What's the next step? Okay. this is should have been y hat I, but y hat is equal to f of x, right? So we can fix this, Gunit. So okay, fine. So we have actually, what do we have now? We have the derivative of the loss function with respect to the ith unit of the output layer, right? And which part of the output layer? The pre-activation part. Okay. Now what am I going to do? I have a formula which tells me how to compute this. What was I actually interested in? So now how am I going to go from here to there? I'll just put all the partial derivatives into a vector, and that vector is the gradient. Okay, good. So we have this one formula. It's okay if some of you did not get this derivation, right? It's very, very straightforward. If you go back and look at it, I'm pretty sure you'll get it. There's nothing in this. It's very simple elementary stuff, right? Except for some trickery here and there. So, okay, now what would this look like? We should add actually L theta here. This would look like a collection of all the partial derivatives. We have a generic formula. What will we do now? What is the first entry? Minus indicator L equal to 1 minus y hat 1. Which is the variable that we are indexing over? I, right? Not L. Oh God. Oh, we are indexing over. Okay, have I goofed up? Oh, that is wrong, is it? Oh, yeah, that is wrong. Okay. Fine. Okay. Then this is fine. Okay, we are indexing over I, and then we can do this. Now, can you simplify this? I'm looking for. Okay. This is the element wise difference of the indicator vector and y hat. Oh, hey, we should change all this. Y hat is equal to f of x, right? But I just want it to be consistent as y hat. So is this fine? Is this simplification fine, right? So we have come a long way, right? We have finished this part. Okay, we have got the gradients with respect to the output units. Okay, this much part is clear to everyone. Modular bit of the math which you can go back and look at it. This entire derivation is fine, but you get the concept, right? That we start with one unit, from there grow the gradient, then keep going applying the chain rule, right? So we started with the dark green guys and then went to the light green guys. Okay, now we have the derivative with respect to the entire light green vector. Okay, and that's what we had started off with, right? We wanted the gradient with respect to the output units. Okay, so that's where we'll end that. Now we'll go to the gradient with respect to the hidden units. So this portion. So you already see there's a repetition here, right? I don't need to treat each hidden unit separately. I can just have a formula for the hidden unit and then I could compute it for all the hidden units. Okay, so that's what our aim is. So let's do some simple stuff first and then we'll come back to that. So suppose you have a variable x, okay? You compute two functions from that. One is x square, the other is x cube. Okay. I'll call this as y1 and I'll call this as y2. And I take y1 and y2 and compute a z, which is say log of y1 by y2. Okay. Now what I'm interested in is this. What's the answer for this? How do you get this? This is a fair question to ask. Y1, Y2 are functions of x. Z is a function of Y1, Y2. Hence, Z is a function of x. So I can compute this derivative. I can ask for this derivative. How would you compute it? If, oh, I can't really do this, right? So, if this path did not exist, then it's trivial. It's just the chain rule along one path. But now you have two paths. So what will happen? add them, right? So can you tell me a formula for that? So let me know if this makes sense to you. Okay, does this make sense? Okay, now let me complicate this a bit. Let me just do it as y3. Now what will happen? That's all, right? So you see that if there are multiple paths, you can just add up the chain rule across all these paths, right? That's what chain rule across multiple paths does. Okay, so with this, we'll go back to this figure. So now I'm interested in going to the hidden layers. Again, I'll do this two-bit calculation where I first ask for this guy and then I'll ask for the light blue guy, right? And I'm going to look at one unit at a time. Now, what am I interested in? The derivative of the loss function with respect to, say, dh22, right? The second unit of the second hidden layer, okay? Now, what I'm going to say here is exactly what I had written on the previous slide. This was our final function, right, which was z. So z was, so again, I've not chosen my variables well. Okay, but so we had exactly the same situation, right, which you see here. Okay, so we'll just have to sum up the derivatives, partial derivatives across all the paths which lead from this guy to this guy, and there could be as many paths as there can be, but I don't care. I'll just sum across all those paths. In fact, actually here there are not just two paths, because we have always assumed there are k classes, so there are actually k of these paths, right? So this is exactly the formula which I wrote on the next slide, right, this one, but just written in terms of the network that we are dealing with. Okay, so you can just go back and look at this, but as long as you understand this figure, from my point of view, we can go ahead. Okay, so everyone understands this figure, that we just need to compute the derivatives across all the paths and add them up. Okay, so now let's start. We again, the same recipe, we'll compute it with respect to one guy and then go towards the gradient. Okay, so what is this now? Okay, let me explain, right? So dl theta, there are k of these guys between, right? So there are k paths. So this summation has to happen over k paths. Just as you told me when there were two paths, the summation was 2, 3 paths, the 3, there's k paths, so the summation is over k guys. The derivative with respect to each of these guys and the mth unit, right? That's the index that I am iterating over, okay? And then the derivative of this guy with respect to whatever you are interested in, okay? That's just there are only two nodes in the path, in the chain, but there are k such chains. How many of you exactly get this? Okay. How many of you have a problem? Want me to repeat this? You have a problem? Oh, many of you. Okay. Good. Please do this. So I'm interested in this quantity. That means I'm interested in the partial derivative of this loss function with respect to this guy. And this guy is nothing but hij. That much is clear? Is the jth unit of the ith hidden layer. In fact, this is actually h22. So my I is equal to 2 and j is equal to 2. Okay. Now I just made a case on the previous slide that if you have such a function which first computes some intermediate values and then your final function is computed based on all these intermediate values, right? And now you're trying to find the partial derivative of this with respect to the original input that you had, okay? So then what you will do is you will sum across all the paths that lead from this guy to the output, okay? How many such paths are there? You already see two such paths here, right? But I'm saying there are k such paths because there are some other nodes here which I have not drawn. We have already said that in the output layer we have k nodes, right? So there are k paths. So that takes care of the first bit, that the summation is going to be over the k paths, okay? Now what is each of these paths composed of? This intermediate value and this quantity that we are interested in, okay? So first we will take the derivative of the loss with respect to this intermediate value. What is that? That's the unit in the previous layer, or the next layer rather. So I'm interested in I, so I'm looking at the unit in the next layer, hence I plus 1, right? Because that's what comes in my path. The next layer is what comes in my path. We have always this special case, right, that this guy feeds into k guys, but all the other hidden units before that feed into n guys, right? So let's just keep that complication aside for the minute, and we'll just look at this case. Okay, is that fine? Okay, so we have agreed there are k paths, and each path is composed of these two nodes, from the loss function to this intermediate value, and then from this intermediate value to the quantity of interest. Okay, and why is this I plus 1? Because the next node in the path, right? I am at the ith layer, so I'll be feeding to the I plus 1th layer, right? And in fact, I'll be feeding to all the nodes in the I plus 1th layer. That's why I'm taking over all the k paths, right? And then that node, which is this node, with respect to the quantity that I'm interested in. Is this clear now? Right? This is very similar to the toy example which I did. I just have k paths now instead of 2 paths there. Is it clear now? Sure? Okay. Fine. So let's move ahead. Now, what is, okay, which of these quantities do we already know? Is there any quantity that we know? This one, right? Why? Because in this spatial case, I plus 1 is actually equal to L, right? Because we are feeding into the last layer, and we have already seen how to compute the partial derivatives with respect to the last layer. So this quantity is known. We don't know this for the generic case yet, but we'll get there. But for this spatial case, when we are feeding into the last layer, we know this. Does everyone get this? Okay. Now, do we know this quantity? So what you have told me is that we know this quantity because that is what we have computed in the previous module. Do we know this quantity? We have to compute it. Can you compute it? Okay, let's just do it, right? So let's assume that this Hij that I'm dealing with is actually H22, okay? Fine. Now, what is Ai plus 1m actually? Which are the elements there? A31 and A32. I'm assuming that I only have 2 units in the output layer, okay? So my m is equal to 2. Now, is this fine? This is how the next layer is related to the current hidden layer, plus biases. Okay. Now, what am I interested in? One of these guys. Okay. Let me take one of these guys. So, can you tell me what is A31? First row multiplied by the first column. There is only one column, right? Plus B21, okay? Sorry? B31, okay, yeah. Okay? Fine. Now let me just clarify something. What is this in terms of variables I, j, k, m? What is this? Is this I? Is this j? Is this k? Is this m? This is I plus 1, right? Okay. This is one of the m's that I'm dealing with. Now I want the derivative of this with respect to h, I, j. Okay, in fact, I want it with respect to H22, where this is I and this is j. Is this clear? What's this derivative? W312. Everyone fine with this? Okay. Now help me find this. What is this? I, j, k, m, I plus 1. What is this? This is coming from the m. How many of you see this? Because that's the unit that you're connecting to, and this is j. So what's the formula? How many? As many as the number of neurons in the next layer. A bias will be connected to all the neurons in that layer, right? Everyone gets that? Right? There are only 2 units, so there will be only 2 guys. Okay. So what's the formula for this? W I plus 1 mj. Everyone comfortable with that? Okay. Fine. You can just go back and look at this and it should be clear, right? So whenever you're dealing with vectors and matrices, right, if you're really good at it, you can imagine the entries and figure out what is happening. If you're not good at it, don't be lazy. Just work it out, right? You just need to write down this product, and at the end, remember, everything is always element-wise, right? You're never dealing with a vector or matrix. You're just dealing with the individual components of them. So you should always be able to compute these derivatives or partial derivatives with respect to the individual components. And that's exactly what I did here, right? So if you just work it out, if you just write it out, then you'll always get it. If you can't, but eventually try to get to a point where you can just visualize it. But if you can't, at least try to work it out, okay? So this is what it will look like, okay? Now, consider these two vectors. One is this vector. What does this vector look like? This is a collection of all the partial derivatives. So this is just a collection of all the partial derivatives, nothing new, we have already seen this. Now what is this vector actually? In fact, I've started with a matrix and I'm saying look at this vector. What does this mean? This I plus 1 is just the layer in which the matrix is, right? So that index we don't really care about. For a matrix, what we care about is the I comma j index, okay? Now what does this dot comma j mean? All the i's belonging to j. That means the dash column, jth column. Everyone gets this? This is all the i's or all the entries belonging to the jth column. So it's effectively just the jth column. So it is 1 comma j, 2 comma j up to k comma j. Right? So these are two valid vectors. Now tell me, what is this quantity going to be? This is the dash between two vectors, dot product. Dot product between two vectors is a, okay, is a summation over element wise thing. Okay, I have said enough. Now try to connect this. This is a very simple match the column that you'll ever get in your life. Try to connect this to something which is already there in the slide. How many of you think the answer is this? This into this plus this into this plus this into this, and just write it as a formula, you'll get this. Everyone sees that? Okay. So now I have a compact way of writing one of these entries. Okay. One of these guys. I have a compact way of writing this. It happens to be the dot product between two vectors. One of them is the gradient, but do I know this already? Do I know this quantity already? In this special case, yes, because I plus 1 is equal to L, and that I have already computed. This of course I know, right, because these are the weights that I am dealing with. Where do I go from here? This dot. Yeah, it means anything from that column. So that means the entire column. No, these are weights, right? So this is a weight matrix. It has columns and rows. So I'm talking about the jth column. So I fixed the value of j. So I'm talking about the jth column, but I'm not telling you a given ith entry there. I'm just telling you all the entries there. That just means the jth column. We can take this offline. Okay, this is very simple, but I'll take it offline. Okay. Now where do I go from here? Huh? I plus 1? Okay, no, in this specific case, are we done? Where are we right now? With respect to 1 unit. Where do we want to go? The entire thing. So what is the quantity that I'm interested in? Gradient with respect to, always say with respect to, h I, right, where I is 2 in this case, the special case, okay? What is that going to be? Collection of all these guys that you have already computed. Okay, now simplify this. What is this? First column of the matrix multiplied by the same vector. The second column of the matrix multiplied by this vector. The nth column of the matrix multiplied by this vector. This reminds you of something very, very difficult. This is a very, very complicated matrix multiplication. Right? first row of the matrix multiplied by a column, the second row of the matrix multiplied by a column. How many of you get this? Right, so this is, can you tell me what this is? Wi plus 1 transpose. Perfect, right? So now you see that this entire quantity we can compute in one go by using a matrix vector multiplication, right? So that's what I meant when I was saying that we should not be doing these individual computations, but be able to compute that at one go, right? So now we can just do this matrix vector multiplication and get this entire quantity. Okay. Now what is still missing in this module? So what is the spatial case that I have assumed? I told you that I already know these quantities, but only if I plus 1 is equal to L. I need to tell you this in the generic case, okay? So we are almost there, except that I don't know this when I is not equal to L or I is less than equal to L minus 1, okay? That's the case that I am looking for. So that's again very simple. Again, what will I do? I will compute it with respect to, okay, what is this? This is the guy that I'm interested in, the generic I, not the Lth one, right? The generic I. This is what the vector looks like, the gradient vector looks like. I want each of these guys, okay? Now I'll take one of those and I'll write it as this, okay? What am I doing? I'm saying that I already have the entries up to here, okay? At a very general level. Even here I could have said the same thing. Remember that I had said that the output layer you can always write as HL, right? So even at the output layer I could say this. This chain rule always holds. How many of you agree with that? I want to go from the loss function to one of the lighter blue guys. So I'm saying that I can go through the intermediary dark blue guys. That's all I'm saying. I've just compressed this entire path into up to the dark blue guy. Remember I had said earlier that I'll be compressing these chains. Is this clear to everyone? Okay. Now how many of these quantities do you know? The first one is what we computed on the previous slide, okay? The second one looks very difficult. Sorry. So Hij is nothing but sigmoid of Aij or any non-linearity of the Aij. So I can just write this derivative as, I'll just write it as sigma prime, okay? Or G prime. Is this fine? Okay. Okay. Now I have it with respect to one unit. What will I do? Go to the gradient, fit it all these values. Now simplify this. What is this? A vector, right? What is this? Another vector. There is a one-to-one correspondence between them. So you have two vectors and you're doing a one-to-one multiplication. What is this? How many of you say dot product? Dot product is always a, what is the output here? Vector. Can it be a dot product? Can it be a dot product? No, please, emphatic no. No, okay. So what is it going to be? An element wise multiplication, and this is how you denote that. Okay. So what is this called? The Hadamard product, right? So this is every element of one vector multiplied by the corresponding element of the other vector. Okay. So now again, the entire vector we can compute at one go, right? When I'm teaching this, I'm telling you how to compute one element and then go to the gradient. But when you're going to implement this, you're just going to compute the gradient at one go. Is that clear? Okay. Before we move on to the next module, right, a quick summary of what we have done so far. So we introduced feed-forward neural networks, and we wanted to learn the parameters right from the last layer to the first layer. And we figured out that what we can do is that we can just use the gradient descent algorithm as it is, except that we have this small problem that we have so many parameters now and located at different points in the network, right? Some at the initial layer, some at the final layer. And we want to compute the derivatives or the partial derivatives with respect to all of these. If you can do that, put them all in this large matrix, then we can just use gradient descent as it is, right? So that's what we figured out. And then we wanted to find out the gradients with respect to the partial derivatives with respect to all these parameters. So then we realized that this can be done using chain rule, because there's a path from your output, which is the loss function, to any of these weights. So we just need to follow that path and apply this chain rule smartly and just sum up the derivatives across all the paths. that lead to that weight. Okay. So in that process, we started from the output layer. We just treated it a bit special because the output function is special, and this is the last layer. So we'll just first computed the gradient with respect to the output layers. Then we figured out how to compute the gradients with respect to any of the hidden layers. And now if you are at a particular hidden layer, now the weights that feed into this layer, we could, oh, we have not reached there, right? Oh, sorry. So now the next thing that we need to do is that we have computed the gradients with respect to any of these hidden layers. And now we want to find the gradients with respect to the parameters, which is the weights and the biases. So do you all remember this, or it's all long history, or just 2 days back, right? Okay, fine. Fine. So now we are at the last point, which is computing gradients with respect to parameters. So again, this is the overall picture. We were in this chain rule, and we have come all the way to the last point where we are ready to now compute these quantities. Okay, this should be clear. Okay. Okay. So now start by recalling that AK is equal to BK plus WK HK minus 1, right? This is our activation formula, pre-activation formula, right? So I'm talking about these light blue guys, okay, which is clear in the image. And now, what have I done so far? I have been able to come up with a formula to write the gradient of the loss function with respect to any of these light green guys, right? That's where we ended last time. We're able to compute the gradients with respect to the, light blue guys, okay? And now I want to compute the gradient with respect to any of these parameters or any of these parameters, right? So any parameter, it does not matter. I'm at some ith activation layer, pre-activation layer, and I just want to compute the gradients with respect to the weights which feed into this layer, okay? And that's what we are interested in. So we are just taking any layer K, and we want to find the gradient with respect to the weights there, okay? Now, can you tell me, what's the thing that I'm going to do here? What's the recipe that we have been following? I need to move. Okay. What's the recipe that we have been following? Apart from yelling at people who come late, we find the element-wise partial derivatives first and then put them all together to get the gradient. Okay, what's the element here? What am I looking for right now? I want to compute, just fill in this blank. What goes here? W, any of these W's, right? And in particular say WK. That's what I'm looking for. So what is the first thing that I'm going to attack? Good, WKIJ. And once I have this for one of these guys, I just know a generic formula with respect to I, J and K, and I can just put it into a gradient vector. Okay, is that fine? Okay, so now can you okay, now from here to here, if I want to reach from here to here, so this is what I'm interested in, right? Now how is a chain rule going to look like based on whatever you have already seen? Till where have you already reached? You already know this quantity, right? Now if I want this, how am I going to write it? I will find up to the light blue guys, which is this, I already know how to compute it. And then from the light blue guys, I'll go to the, is this fine? Right? So this is the quantity that I am looking for. Okay. Now what is one element of this guy? Dou AK by, is that fine? Okay. What's the dimension of this actually? Is it a scalar, a vector, a matrix? Matrix or a tensor? What's a tensor? What is it? Is it a matrix? What are the dimensions? What does this derivative mean, or this gradient mean? I change one element of WK, how much does one element of AK change? How many elements are there in AK? N. How many elements are there in WK? N cross N. So how many partial derivatives which I have? N cross N cross N. What is this? A tensor, right? So this is going to be a tensor. Okay. So when I say one element of this, I mean this. Okay. So So this is one element of this gradient. Okay. Now can you tell me the formula for this? What is this quantity? Hk minus 1 or hk minus 1j, or everyone gets this? Hk minus 1i. How many of you get this? Okay, so let's do it, right? So you have ak1, ak2, ak3. That's your ak vector. Okay. You have bk1, bk2, bk3 plus wk11 I know again this is one of those silly things, but if everyone doesn't raise their hands, I'm compelled to do this. So hk minus 1 1, hk minus 1 2, hk minus 1 3. Okay, so let's take one of these guys, right? So ak1, can you tell me the formula for that? Plus first row. Okay. It's 1, 2, 1, 3. Now can you tell me this quantity? So what is I here? 1. Okay. So I want this by wk I j, right? So I is 1, so I can take any of the j's. So let me take j equal to 2. So what is it going to be? This will go off, this is constant, only this term remains, and the derivative is hk minus 1 2, which is j, right? So that's what the formula says. So I have a formula for one of these guys, okay, and that's a generic formula. So always remember, if you can't figure out what it is, just write it down in scalar terms, just add up all the terms and you will get the formula, right? So now this is what the chain rule is going to be. Is this fine? Okay. So this is what it's going to be. This is one element of that tensor. Okay. Is this fine? This is how that entire thing is going to look. I've just flattened it out and put it here. Now let's take a simple example of wk belonging to R cross 3 cross 3. Everyone is fine so far, right? I mean, everyone is fine, please raise your hands. I mean fine, I mean not in life but with the lecture. Okay, fine. Okay, so this is what it looks like, right, for a 3 cross 3 matrix. Okay, fine. Now let's see. We already found out that this guy is equal to hk minus 1 comma j, right? So this is what this matrix looks like. Nothing rocket science here, right? So each of these quantities is actually can be written in this form where I appropriately substitute I, k and j, and I know that this quantity can be further written as this quantity, right? That this is R clear, right? Okay. So now I've written it as this. Now can you simplify this? I do use a lot of this. Okay. Can you simplify it? Does it look similar to something that you did on the assignment? Does this look like a matrix which has some very regular patterns? Yeah, I can see someone doing this and this. Everyone gets it? Okay, so let's see. So this, the first column, the second term in the product is all same throughout all the rows, right? What I mean is all these guys are similar. Same thing happens in the second row, the third row, right? The second column and the third column. What about the rows? These are all equal, right? So what does this look like actually? The outer product of two vectors. Everyone gets this? Raise your hands. Okay, good. So I don't need to do an example. Oh, so it's fine, right? This is an outer product of these two vectors. One happens to be the quantity that we already knew, right? And the other happens to be a quantity that we can figure out. right? I mean, we already know this. We know how to compute the hidden representations, right? The HKs we can compute, okay? So fine. So finally we come to the biases. This is what one entry looks like. This is exactly the sum which I had written out, right? Now I take the derivative with respect to bki of the loss function. So I could write it as this chain rule, where the first quantity is something I already know. I have computed the gradient with respect to the pre-activation layers. What about the second quantity? Unanimous roar is what I was expecting. 1, okay. Fine. We can now write the gradient with respect to the bias. What would it be? What is this? What is this? It's just the gradient with respect to the pre-activation layer, right? Simple? Okay, fine. So now we are done with all the gradients that we were interested in, right? So we'll move on to the next module, and now we'll write pseudocode for backpropagation. And pay attention, this is what your assignment is about. So this is how you'll write your assignment, okay? So we have all the pieces of the puzzle. We have the gradients with respect to the output layer. That was the spatial layer because the output activation function is different. We have the gradients with respect to all the hidden layers. That means I have the gradients with respect to the activations as well as the pre-activations, right? The H's as well as the A's. And I also have the gradients with respect to the weights and the biases. And this is all index agnostic, right? That means I'm just using K as the index everywhere. I have a generic formula which applies at any layer for the weights as well as the activations and the pre-activations, right? Okay. Now we can put all this together into a full learning algorithm. So let's see what the pseudocode looks like. So we have this t equal to 0. We'll run this for some max iterations. We initialize all the parameters to some quantity. We'll randomly initialize them. Okay. Now for these max iterations, can you tell me what is the first thing that I'll do? So there will be two functions here. Can you tell me what those two functions would be? Forward propagation and then backward propagation, right? So you do a forward propagation and you compute all these activations, pre-activations, output layer, loss, everything, right? And then you do this backward propagation where you feed all these things which you have computed, right? These are the quantities which you have computed. You'll pass this to your backward propagation algorithm. It will not look so nasty as this. It will not take so many parameters. You could write it smartly. And then you'll just do the parameter update, right? So what will the back propagation give you actually? All the gradients, all the partial derivatives, right? And then once you have the partial derivatives, you know how to compute the update rule. Is this clear? So now let's look at these two functions more carefully, the forward propagation and the backward propagation, okay? So forward propagation is simple. For all the hidden layers, that means from layer 1 to layer L minus 1, what will I do? Give me the code. AK is equal to, good. Then, okay. And what is h of 0? You're starting the loop from 1, right? So you'll need h of 0. That's x, okay. And then you'll have a spatial treatment for the output layer. And your final output will be whatever output function you use. Okay? This makes sense? You can write this in Python. Okay, you will have to write this in Python. Okay. Now we have computed all the h's and the a's. What have we computed? All the a's, all the h's, and the y. Right? Now you want to do back propagation. So back propagation, the loop will be from I equal to 1 to L minus 1. Okay, good. So the first thing I'll compute is the gradient with respect to the output layer. See, even here, the output layer was outside the loop. The same thing would happen here also in the back propagation also. First, you will compute the gradient with respect to the output layer, and this is the formula if you remember from last class, right? That's the formula which I have substituted here. And note that f of x is known to you because you computed that in the forward pass. And e of y, what is e of y? Y, one hot vector, which with a correct label set to 1. And you know what the correct label is because we have given you the MNIST data, right? Okay. Then what would the loop be? L to 1 or L minus 1, let's see. First you compute the gradients with respect to parameters, okay? Okay, it's L, correct. So because we are using k minus 1. Then you compute the gradients with respect to the layer below, compute gradients with respect to the pre-activation, right? This is exactly how you will proceed. Is this clear to everyone? The same three components that we have used. You might be a bit confused about the ordering in which we have put them, right? Because we computed the gradients with respect to pre-activation first and then the weights. But once you go back, you will realize because it's the way we have indexed it, right? Because this is already outside. So this has already been computed. So you can already compute the gradients with respect to the weights of the outermost layer. Okay, is that fine? So this is straightforward. You can go back and check this. Okay. Now anything remaining, or you have everything? Can you just take a minute and see if you can visualize the Python code, and we'll just assume that you're done the assignment. You can, right? You'll have multiple these vectors and matrices and so on, and you're just doing a lot of matrix operations using NumPy or SciPy or whatever you prefer, right? Is that clear? Okay. Now what is missing here? Input is missing. Okay, input we have given, right? The MNIST data set has been given. Is there something that I've still not shown you how to compute? Oh, I did not update the parameters here, is it? No, the parameter update will happen in the outer loop, right? So there's forward prop, back prop, and then update the parameters, right? So the main algorithm was forward prop, back prop, update the parameters. Then we saw forward prop, and now we are seeing backward prop, okay? So what is missing? 1000 iterations. Something in the last line. Before end, of course. Do you know how to compute this? Do you know how to compute this? Okay. Okay, let's see. So now we have that activation function, and we were taking the derivative of the pre-activation, of the activation with respect to pre-activation, and I just pushed this under the rug by saying, okay, we'll write it as G dash, right? So I need to show you what G dash is, okay? How to compute G dash. So this is, suppose G is the logistic function, okay? So that means, what is Z actually? It's one of those A's, right? So this is the activation that you're going to feed it, right? And then you're taking the element wise, Z is actually the pre-activation that you feed it, and then G is the activation function, so it'll do element wise activation function. Now what's the derivative of this? Okay, so I'll not do this derivation, it's there, and you end up with a very neat formula, which is G of Z into 1 minus G of Z, okay? So now that bit is also taken care of. Is there any more spoon feeding that I can do? Okay, you're ready for the assignment now? Okay, I'll do one more bit. You will also have to use the tan h function. Okay, so this is the derivative of the tan h function. It again boils down to a very neat formula, which is 1 minus G of Z the whole square. Okay, so we'll end this lecture. So for the next module, we'll need something known as cross entropy. So we'll just try to make some, develop some intuitions for cross entropy and get to the formula for that. And then I'll tell you how it relates to the problems that we deal with, okay? So first, let's start with something simple, that what is it that we're trying to do, okay? So with that, I'll give you an example, and I'll ask you a few questions, and then from there, we'll slightly try to go towards cross entropy, okay? So now suppose you have an urn which has thousands of balls, and these balls are of 3 different colors, which are red, black, and white, say, right? So you have an urn which has 3 different types of, and there are many such balls which you have put in it. And since you have put in it, you know how many red balls are there, how many blue balls are there, and how many white balls are there. So for you, it's very easy to compute the probability of each of these things, right? So that's, say your probability is 0.25, 0.35, and 0.4, okay? Now talking more formally, what is happening here is that you have a random variable x, which can take on the values red, blue, or white, right? And this is the probability of each of those, or the random variable x taking any of these values, okay? So this is the setup. Now I am your friend, and you tell me that you can peep into this urn. You cannot actually take out all the balls and count them and estimate the probability, but you can just take a look into this and try to give me an estimate of what are these probability values. That means what is the value, so what is the probability that x is equal to red, or x equal to white, or x equal to blue. So I just take a look at it, turn it around a bit, and try to get some feel, okay, I see a lot of red balls, but a fewer blue balls or white balls and so on. And based on that, I make my guesstimate, right? So I just say that maybe these probabilities are 0.35, 0.45, and 0.2, right? So this is actually the true distribution. I'll call it as P, right? Because this is the correct one. And what I have estimated, I'll call it as Q, okay? And remember now, P has, you can think of P as a vector which has these 3 values, P1, P2, P3, because there are 3 possible events here. and similarly Q has 3 values, Q1, Q2 and Q3. So in this case, I clearly know that I'm wrong, or when I give you these values, you know that you're wrong. So you tell me that whatever you have estimated is wrong. Then I obviously ask you, okay, tell me how wrong was I? So how would you give me that number? Right? That's the thing that we are interested in. So the general problem that we are interested in is that there is a true probability distribution and there is an estimated probability distribution, and we want to find out how bad was the estimation. Okay. Now, can you tell me a simple way of computing this? It may not be correct, but still it makes sense. You could just take the squared error. So what you're essentially telling me is that you could just treat these two as any other vector, right? And you could take the squared error difference between these quantities. So what you're telling me is this, where I goes from 1 to 3. Okay. So this is one valid way of doing this. But then we are ignoring the fact that this is a distribution and hence it has certain properties that the sum of the elements is 1 and so on, all of them are positive and things like that. So we are ignoring those kind of things. We are completely ignoring the fact that we are not dealing with a normal vector, but a spatial vector which happens to be a distribution. Okay. So now we want to find out a more principled way of computing the difference between two distributions. And in practice, why are we interested in this? Because we'll always have a true distribution and a predicted distribution, right? So that's what we want to do. We have some way of computing it, but we want a better way of computing it. Okay. Now, let me make a case for why do we care about such differences, right? So let me take a simple case of a classification problem. Okay. And to motivate that, I'll start from a different example and then I'll come to the classification problem. Suppose there is a tournament going on and there were 4 teams which reached the semifinals. Let's call them A, B, C, D. Okay. Now you were following the tournament up to the semifinals, and after that you didn't watch the tournament and you don't know who eventually won. But the tournament is over and someone has won it. Okay. I actually watched the tournament and I know that B has won it. Okay. Now can I express this in terms of a probability distribution, right? So first let's look at what is the random variable here. What is the random variable here? The team which won, right? So that's my random variable and it can take one of these 4 values. Okay. Now I know that team B won because I saw the tournament and I have seen that they won. So now how can I write this as a distribution? What does the distribution comprise of? It comprises of these probabilities assigned to each of these events. And there are 4 such events here. So how do I write this distribution? So what you're telling me is I could write it as 0, 1, 0, 0. So essentially you're telling me that all the probability mass is focused on one of these outcomes because that's the certain outcome. That's already happened. No one can change it. So that's the outcome for this tournament. So I know that the probability of that event is 1 and everything else is 0. So in other words, the probability that the random variable x takes on the value b is 1 and everything else is 0, right? So what I'm trying to tell you is that even for a certain event, you could still write it in terms of a distribution where all the mass is focused on that event. Okay. Now again, I'll bring the same setup that I did not watch the tournament after the semifinals. So now you ask me, give me your prediction, which team would win? Okay, or this is the prediction which I made just after the semifinals, or sorry, just before the semifinals, that I think one of these teams is going to win the tournament and the chance of each of them winning is something like this. So I know the teams, I follow this sport and I probably know that okay, B has a very strong team and they have a very good record in the past few months and so on. So maybe they have a higher probability of winning. So these are the numbers which I assign. Okay, fine. Now again I have made an estimate. Was my estimate perfect? When would it have been perfect? If I had predicted with certainty 1 that B is going to win, but I was not willing to bet everything on B. So I said there's a very high chance it will win, but there's still a chance that there could be some surprises. Okay. Now how wrong was I? Now again can you tell me what is P and what is Q here? This is the true distribution and this is my predicted distribution. And what am I interested in again? The difference between them. How wrong did I go? And what is a simple way of doing this again? Square error loss. So again, this is what my formula would look like. Okay. So this is fine in this toy case, but why do we care about in real life examples that we are going to deal with in machine learning, right? So in machine learning, we'll deal with a lot of problems which are classification problems, okay? And in classification problems, you would again have this setup where you have a label. You could think of the label as a random variable, and it could take off one of many values, right? So I'll again assume that it could take, suppose you're trying to take a picture of fruits, okay? And you're trying to classify them, okay? And I could again think that I have 4 fruits, say apple, banana, cherry, and dragon fruit, okay? And this random variable can take one of these 4 values, depending on the image that I'm seeing, okay? Now I've been given some training data. So for every training data, I've been given an image, and I've been given the correct label. So for that training data, what is this distribution? Suppose I've been given the image of a banana. What does this distribution look like? 0, 1, 0, 0. Right? Again, I have seen it, so I know it's certainly a banana. So I don't have any confusion. All the probability mass is focused on that. Now the same image, we are going to show to one of our models. Okay, and it is going to make a prediction. And we'll again ask it to give us a distribution. The model will give us values, perhaps like this. Okay, so this is the model's prediction. Again, the model has given us a distribution, and we have a true distribution. And we are interested in knowing how wrong the model was, so that we can correct the parameters of the model. So this is our dash function, loss function, right? So our loss function is some notion of difference between P and Q, right? And so far we have been dealing with a very simplistic notion of this difference, which is just the squared error loss, okay? And we want to do something better than this, right? So what I have told you is that you could always have a true distribution, always have a predicted distribution, and you would be interested in finding the difference between them. That's the first part. The second part is that even when you are given something with certainty, you could still write it as a distribution such that all the mass is focused on that event which has happened, right? Which was the label was banana in this case, okay? And then you could still predict this from your model. And now you're interested in knowing how wrong your model went, because that's the loss function that you'll use. And then you'll try to update your parameters with respect to this loss function. Okay? So that's the setup that we are interested in. Okay. Okay. So that's so I made a case for why we need to find differences between two distributions. How to do it in a more principled manner, we have not seen that yet. We'll get to that. Okay. So before I get that, I also need to tell you something about expectations. Okay. So let's return to our sports example where there were 4 teams. Okay. And say based on pundits in that sport, they have said that these are the probabilities of winning. Okay. And now you are into betting, and you place your bets on these teams, and you place your bets in a way that suppose team A wins, then you'll end up winning 10k rupees. If team B wins, then probably you'll end up winning 5k rupees. And if team C wins, probably 10k. And if one of the other team wins, maybe you'll end up losing money or something like that, right? Now, you want to know what is your expected reward. Okay. So now let's see what is happening here. This was a random variable which could take on one of these 4 values. These are the probabilities of the random variable taking that value, taking on the value A or taking on the value B, C and D. Okay. This is your value or the gain or the profit associated with the random variable taking one of these values, right? So you have a random variable, you have a probability associated with every value of the random variable, and you have some gain or value associated with every value of the random variable. Now, how do you calculate the expected gain or expected profit, which is this? There's a 30% chance that you will earn 10k. There's a 40% chance that you will earn 5k. There's a 20% chance that you will earn 10k and 10% chance that you will lose 30k, right? So the way you will compute it is that, and this is the simple expectation formula, which is the probability of, now the event here belongs to A, B, C, D. Right? This is one of the 4 teams that will win. Probability of that event happening into the value associated with that event happening. Okay? Is it a fair computation? You get the intuition that this is how you will compute the net reward that you have. Okay? So this is how you compute the expected value with respect to a particular distribution. Okay? So this is the background that we need. Now I'll just go on to the next slide. And now we'll talk about entropy first, perhaps information content first, then entropy, and then cross entropy. Okay? So now what is information content? So now again, let's take the same case that we have a random variable which can take on values A, B, C, D. Okay? Now what we're trying to say is that if I know a certain thing, what is the information that I have gained? So you and I are talking, you tell me something, okay, and I want to see whether my information was enhanced, whether my knowledge was enhanced. That's how we'll quantify information content. Okay? So if you're talking to me and you tell me that my name is Mitesh, there's 0 information content for me, right? Because I already know that. There's no surprise in that. Okay? But if you talk to me and you tell me that today there's going to be a lunar eclipse, then there's a possibility there's some information content gained for me, right? Because that's not an event which happens every day. If you just tell me you'll see the moon today and you live in a region where it's not typically cloudy, then there is no information gain there, right? So what do you see here? When is the information gain high? When the event which happens is a very surprising event. And how do you say surprise in terms of probability? It's a very low probability event, right? So if there's again this tournament and say D was the weakest team in the tournament and A was the strongest team in the tournament. If you come and tell me that D won, then I would be really surprised. That's some information which I had gained. But if you tell me that A won, then probably I already knew it at the back of my mind, right? Because A is clearly the strongest team in the tournament and there's no information gain for me. So one thing that we are trying to establish that the information content, the information content of an event is inversely proportional to the probability of the event. That's a fair intuition. Okay? Fine. Now I'm still talking in terms of vague things. I'm saying it's inversely proportional, but I still need an exact function so that I can compute it. So I want a function where I plug in the probability of an event and I get the information content of the event, right? Right now I don't have that function. I'm just building some intuition towards that function. Okay? But this is one requirement that I want the function to satisfy. This is something that all of us agree with. Okay? Now think of 2 events which are independent, A and B. Okay? So A is the event whether the AC is on here or not, and B is the event which tells you, sorry. So let's consider 2 different random variables. So X is the random variable which can take on values 0 and 1. So X is again this random variable which can take on these 4 values A, B, C, D, who won in the tournament. And Y is this another random variable which can take on the value on and off depending on whether the AC is on in this room or not. Okay? What can you tell about these 2 random variables? They are independent random variables. Okay? So this is on or off and this is which team won the tournament. Okay. Now I come and tell you something about the random variable Y and I come and tell you something about the random variable X. Okay. So now I want you to tell me this. What is the information content of X and Y? I tell you something about X and I tell you something about Y. And these 2 random variables are independent. Then what can you tell me about the information content? What is the condition that you would want? You gained some information by knowing things about X and you gained some information by knowing things about Y. Okay? So what can you tell me? It should be the sum, right? Because these 2 are independent events. So whatever information I'm getting from this random variable and this random variable, it's together enhancing my information, right? It's not cancelling out anything or there's no common intersection there, right? If the 2 events were not independent, then I wouldn't expect this to hold because knowing something about the first event already tells me something about the second event, right? Because they are dependent. So then in that case, the information gain would not be additive. Okay. So now let's see. I already made a case that this function which tells me the information gain is actually proportional to the probability. Okay. So that means this is what the input is going to be, right? And then what is the other condition that I want? Is this a fair thing? Right? I've just replaced information content by a function, and I know that the function should depend on the probability because that is what we have established here. So we know that the function depends on the probability. We still don't know what this f is exactly, but I am trying to impose some conditions on f. One condition of f is that this condition should hold. Okay. Now let's look at this condition which I have underlined. This is f of Is this fine? Because the two events are independent, you can write them as the joint probability as p of x into p of y. Is this clear to everyone? Right? You seem to be a bit lost. Arvind? Clear? Okay. Now what is happening here? I have a function f of a into b, and that is actually equal to f of a plus f of b. What family of functions do you know which has this characteristic? Log, right? That's why log is a good choice for this. That's why information content is going to be the log of the probability, but I want it to be inversely proportional, right? So it will be log of 1 by the probability. Okay, so that's why information content of this thing is, so you see this, how did we arrive at this log formula? Okay, and this log can just be to any base, it doesn't matter. Okay, so all of you get how we arrived at the formula for information content? Okay, now just give me a minute, I need to think of what is the next thing that I have to say. Okay, fine, so we have found out the information content of one of these events happening, okay, which was the x taking on the value a. Okay, now let's think of this random variable x. So here actually I should have said x equal to a, probability of x equal to a. Okay, does it make sense? Because the random variable is x and the event is x taking on the value a. How much information content is in that? So if I know that x was a, how much will I be surprised by it? Okay, now let's take this event, this random variable x, which can take on values a, b, c and d. As I said, with each value there is a probability associated with it, such that this sums to 1. Okay. Now, okay, I didn't need to draw this diagram. Okay, I should have just done this. So x is a random variable which can take these 4 values, which each of these values I have a probability associated. Okay, so these are the values, these are the probability values. Now what do I also have? I have the information content associated with each of these. Right? And the information content actually tells me the surprise of that event. Now if I ask you, what is the entropy of this random variable x? So remember, I had this case where I was betting, and with every outcome I had a value associated with it. I have the same situation here. With every outcome I have a probability, and I also have a value associated with this, and the value is the information content. Okay. Now if I ask you, what's the entropy or the expected information content of this random variable, then how will you compute that? I'm asking you for an expectation, right? So I'll compute summation I belonging to A, B, C, D, P of x equal to I, information content. What's the formula for that? minus, so I'll just take the minus outside. Okay, so this quantity is called the entropy of the random variable. Right? It is the expected information content in the random variable. Okay. Now, if you see what would be the entropy of a random variable if it's corresponding to a certain event. That means, say the sun rises always in the east, right? So what is going to be the entropy of that? 0. Why? You'll have one of the sums in the summation as 1 log 1, right? And every other sum would be 0 into log of something. So 0 into anything is going to be 0. Even though that quantity is not defined, 0 into anything is going to be 0. So the total entropy is going to be 0. Okay. So this is entropy. Now what is it that we are actually interested in? Cross entropy. So we have not gone there yet. Okay. So we need to perhaps add one more slide. So far everything is clear. Okay. So now we are interested in something known as cross entropy. So there again the situation is that there is something which is the true distribution and something which is the predicted distribution. Okay. Now actually before going there, so let me just erase this off. How many of you have heard that entropy is related to the number of bits that you need to transmit something? Do you know why that connection exists? No. Okay. Now again let's think of this, that you're trying to transmit a message. Okay. And that message is again a random variable which can take on 4 values: A, B, C, D. Okay. So think of these as 4 commands that we are trying to send to someone, right? And then based on that command, someone will take some action. Now in the digital case, how will you transmit this? Encode it to bits. So what is the encoding that you will use? 0, 0, yeah, we'll come to that. 0, 1, 1, 0, 1, 1. So how many bits are you actually using for every message? 2 bits. Okay, for every bit. So maybe this is A, this is B, this is C, and this is D. So for every message, you are using 2 bits. Okay. Now, okay, let me just see. Okay, so let's see actually what, when you're doing this, what are you actually assuming? You're actually assuming that all of these are equally likely. If all of these are equally likely, can you tell me the information content of any of them? It's going to be minus log of one by 4. Okay, that's actually equal to minus log, and this is to the base 2. Okay. Okay. 1 by 4 is just 2 raised to minus 2. That is equal to 2, right? So the information content is actually equal to the number of bits that you are going to use to transmit that message. Okay. Now let's see if this is just in this spatial case or in a different case also. Suppose this could take 8 values. How many bits would you use? 3 bits, right? So you'll have 0, 0, 0, 0, 0, 1. Okay. And this would be A to H. Now what are you actually assuming here? Each of these is equally likely. What's the probability? 1 by 8. What's the information content? 2 raised to minus 3. That's equal to 3, right? So the number of bits that you actually use to transmit something is, you can talk of it in terms of the information content of that, right? Now suppose I want to transmit this over a long distance. Okay, so I need to be a bit efficient in terms of number of bits that I use. Right? So now in this one of these cases, suppose it's of the following form, right? That let's look at the case where x can take one of 4 values, and say, let me just put the right values. So I'll say 1 by 2, 1 by 4, 1 by 8, 1 by 8. Okay. Now what's the information content of each of these? 1, 2, 3, 3. And this is the message that I'm going to send. Okay. So what am I doing here? I'm using a different number of bits depending on the probability of that event. Why does this make sense? Why is this a smart thing to do? If you want to transmit something which you're going to transmit a lot of times, you better use less number of bits for that. And this is exactly what is happening here. A was having the highest probability and you're using the lowest number of bits for that. Okay. Now what is the expected number of bits that I'll use up? If it's A, I'll use 1. If it's B, I'll use 2. If it's C, 3 and D, 3. So what is the expected number of bits that I'll use? Again, I have the same situation, right? I want you to cast it into the same situation. I have the probability values, and with each of these guys, I have a cost or a value associated. What's the cost? 1 bit, 2 bit, 3 bit, 3 bit. So what's the expectation now? Can someone compute the expectation? 1.75. Right? Actually, let me just write it down. It would be, again, I belonging to A, B, C, D, P of x equal to I into the number of bits that you will use, right? So that is just equal to log to the base 2 of P of x equal to I minus 1. What is this quantity actually? This is the entropy. We just saw this, right? This is the entropy of the random variable. And what is it telling us actually? That the entropy is 1.75. So what is the meaning of this actually? So on average, you will be needing 1.75 bits. Whereas if you are assuming everything is equally likely, on average you are using 2 bits. Right? So you see that on average you are making some savings here. Right? So that's what the entropy tells you. If you know what the probability of these events is, then you better use that to decide the number of bits that you're going to use to send each of these. Okay? Okay, so now let's complicate this a bit more. Now we have the entropy. Now let's complicate it a bit more. So there is some true distribution which exists. There is some true distribution from which these messages are coming, right? But you don't know what that true distribution is. We never know the true distribution. That's the entire problem that we have been dealing with in machine learning, right? So what you will do is, we'll somehow try to predict this distribution. And the recipe that you will use is the same as that I used for the example where I had an urn, right? So there are these thousands of 10,000s of messages which are going to keep coming on. You don't have access to the entire stream, but you have seen some 1,000 of those messages. Just as I had peeped into the urn and I had seen some balls and I had made an estimate that I think based on these messages that I have seen so far, I think these are the actual probabilities, right? So the true probabilities are say P1, P2, P3 and P4 corresponding to A, B, C and D. I don't know what these true probabilities are, but I can estimate them looking at some samples or basically using my domain knowledge, right? Maybe I would know that if one of these messages is stop, right? And I'm actually trying to talk to a computer or a computer program, then maybe stop is something which I use very rarely, only at the end of the program or something, right? So I have either some domain knowledge or based on some samples, I can estimate the value of this probability. And just try to relate it to the exact example of urns, where you had these 10,000s of balls, but you couldn't see all of them. You sampled some and estimated a probability. Here again, there's a continuous flow of message. You can't have access to all of these because they're going to continue. But you have seen some of those, and based on that, you estimate these probabilities. Now, based on this estimation, how many bits? Okay. So now this is the estimation that we have. Okay. Now, based on this, you will decide the number of bits that you'll use for each of these messages, right? Because you have some estimate, so you want to be smart. You don't want to keep 2 bits for all of them. So you'll just say that I'll use log qi bits for the ith message. Is this a fair thing? Because I know that the information content is proportional to the probability. In fact, it's exactly given by this formula, minus log of qi. So based on my estimated probability, I'm going to do this. Okay, and this is the number of bits that I have reserved. Now, do you see a problem with this? This is my estimation. But the data is actually going to come from the true distribution. It's not going to follow the distribution Q. It's going to follow the distribution P. So now what has actually happened is this, right? This is the situation that we are dealing with. We have P, which was the true distribution. That is the rate at which the data will come. But with each of these events, the value that we have associated is now related to Q. Because Q is what I have access to. I don't have access to P. I just have access to Q. So I have associated a value based on Q. Does this make sense? I should have actually used log P1 bits, log P2 bits, and log P3 bits, but I don't know what P1, P2, P3 are. I just estimated them based on some samples, so that is Q1, Q2, Q3, and these are the number of bits that I am using. Now if I have to compute the expectation, how will I do it? I'll have to use P, because that's the true distribution from which the data is coming, right? So what would the expectation now look like? Everyone gets this? The actual probabilities are this, but because I am poor at estimating them, I ended up associating these values, which could be wrong, right? Because I would have overestimated the probability of one of these messages, and hence I have reserved lesser bits for that, or underestimated the probability of one of these events, and hence reserved more bits for that, right? Or vice versa, right? I could have assigned a wrong number of bits to them, right? P. No. So, do we have access to P in the sense?
How do we know the values P when we compute?
Yeah. So someone knows that, right? I mean, there's again in the same case as in the label case, right? We have access to the true P there, and we are estimating a Q. When we are given these images for the training data, we know that the distribution is 0, 1, 0, 0 if the image is B for banana, right?
Experiment run and then it's validated.
Then it's validated, right? So now this is, what is this quantity called? This is called the cross entropy, okay? You get why it is called the cross entropy, because now you have two different distributions involved here. Okay, you have the Q distribution based on which you made your decisions. You assigned values to these events based on the Q distribution, but the true distribution is the P distribution. So the actual number of bits that you'll use up on average is going to be based on the true probability, right? Try to understand that. Now what will happen is, for event A, you have assigned a certain number of bits. Now how many bits will get used up? It depends on the actual probability of P. If that message is repeated many times, then that's how this summation would be computed, right? Is that clear? So this is called the cross entropy. But now why is this the difference between two distributions? That is what we wanted. Given two distributions, we wanted to be able to find the difference between them. Now I'm telling you that cross entropy is a way of finding that difference. Why is it so? So what would you want this difference to, what is the property that you would want this difference to have? If P is equal to Q, then if P is equal to Q, then not 0 maybe, it should take the lowest possible value, right? So this function, right, it is actually telling you loss of P comma Q, right, is what this is, and we're calling it as the cross entropy. This function should take its minimum value when P is equal to Q, right, because now at that point you are not really making any loss. That's the best you could have done. Does this function take its minimum value when P is equal to Q? Yes. Why? How is that obvious? But why? There could be something else which is lower than the actual entropy, right? Why? How? You have to, you're trying to minimize something, so you have to give me an answer. Okay, so yeah, so let's do that. Okay. So to how many of you it's obvious that Q is the answer? I mean, the answer is P is equal to Q. It's not. Okay. Now this is the part which I'm a bit worried about, but I'll just do it anyways. So this is what we want to do, right? So, okay. So let me see, how do I put this? Okay. So remember that we had a P and we had a Q, and we want to find a Q such that this quantity is minimized. Okay, that is what our objective is, right? So we want to minimize this with respect to Qi. Okay. Now, how do I find the minimize? Suppose I have this problem. How do I find the minimum value? How do I find the value of x which minimizes this? Take the derivative and set it to 0. Okay. And then in this case, I'll get x equal to 0 is that value. Okay. Can I do the same thing here? And suppose it was this. So now this is a function of two variables. Again, I could do the same thing. I could take the partial derivatives and set them to 0, right? And I'll get the minimum value. Now here, this is actually a function of how many variables? K in general, right? So Q1, Q2, Q3 up to Qk, okay? Now can you try doing the same thing? Can you take the derivative and set it to 0? This is again a sum, right? It's very similar to this situation, right? It's actually, let me just write it down. It's P1 log Q1 plus P2 log Q2 up to Pk log Qk, right? Now I want to take the derivative with respect to one of these guys, say Q2. What would it be? P2 by Q2 is equal to, what will I do? That's the derivative, P2 by Q2. I'll set it to 0. Do I get anything? What is it that I'm doing wrong here? There's something that I'm deliberately doing wrong. Is this an unconstrained optimization problem? There is a constraint on the variables. What's the constraint? So why my true optimization problem is minimize with respect to Qi's such that summation Qi is equal to 1. Do you know an easy way of dealing with these problems? How many of you know the Lagrangian multiplier? Okay, how will I use it here? What will my objective function become? Then summation of Qi minus 1 lambda, then minus. Okay. How many of you understand the intuition behind this? Okay, that's a good answer. Okay. Now let me try to explain why this makes sense, right? This is the constraint that we have. We have to operate within this constraint. Okay. What I've done is I've taken the, so now if the constraint is not satisfied, what will happen to this quantity? If the constraint is not satisfied, that means my summation is not equal to 1. That is what means by the constraint is not satisfied. What will happen to this quantity? It will be a non-zero quantity, right? Fine. Then what will happen to my overall objective? I think we have made a mistake. This should be plus, right? Yeah, I should add it, right? Should be plus? No, it does, right? Oh, the lambda can be, oh, okay, sorry. Okay, so let me assume this is plus. Okay, so what I'm trying to do is that this is my objective function which I'm trying to minimize. I've added another quantity to it. If this quantity is not equal to 0, then I will not be at the absolute minimum. I'll be at the minimum plus something, right? But if this quantity, if the constraint is satisfied, then this quantity will go to 0. Then I'm actually at the minimum of the function. Do you get this? Right? So this is the function that I want to minimize. I've added some quantity to it. Now that quantity is actually related to the constraint that I don't want to violate. If I violate the constraint, this is going to be non-negative, right? So whatever minimum value I achieved, I'll be slightly higher than that because some non-negative value has got added to it. Okay? Is that fine? But if the constraint is satisfied, then I can achieve the minimum value. So that's roughly the intuition behind using this Lagrangian multiplier. It's a very crude intuition, but there's of course a lot of math behind that, but I'm just giving you the intuition behind this. Which one? Yeah, that's what you could adjust the lambda and ensure that it's non-negative, right? Okay. So now can you do the same thing? Can you equate this to 0? Can you take the derivative and equate to 0? What will you get now? This term will give you Pi by Q2 as before, oh sorry, P2 by Q2 as before, plus lambda times, yeah, plus lambda times 1. Okay, fine. So equal to 0. So then what will you end up getting? P2 is equal to, I think there's something wrong here. this should be minus P2 by Q2, right? So P2 is equal to lambda times Q2, okay? And then further actually, you can show that lambda is going to be equal to 1. How can you show that? No, constant is fine. So do you see how you will get lambda equal to 1, right? So what does it actually tell you then? P2 is equal to Q2. That means all, in fact, you can show that all Pi's are equal to Qi's. That means the distribution P is equal to distribution Q. So this cross entropy term will be minimized when your true distribution or when your predicted distribution is the same as the true distribution. And hence it captures the difference between the two. Okay? And that's exactly what we were interested in. We were interested in a quantity which can allow us to capture the difference between the true distribution and the predicted distribution. Fine? So we have arrived at that quantity, and that quantity is cross entropy. So therefore, for all our classification problems where we have this scenario, that we are given the true distribution where all the mass is focused on one of the labels, and you are estimating a distribution where you could give non-zero quantities to many of those, and you want to find out how wrong your estimates were with respect to the true distribution, you can use cross entropy as a measure for that, right? So now your loss function, which you wanted to depend on the difference between P and Q, it can just be the cross entropy between P and Q. Okay? Is that clear? So welcome to lecture 5 of the course on deep learning. And so today we'll look at some variants of gradient descent. So we'll just quickly do a recap of gradient descent, and then look at some variants of it, or some ways of improving it, which is momentum-based gradient descent, Nesterov accelerated gradient descent, stochastic gradient descent, Adagrad, RMS prop, and Adam. Okay. So just to set the context, right? So we started with this gradient descent algorithm for a single sigmoid neuron, and then we saw how to extend it to a network of neurons with backpropagation, right? So we realized that all we need is the gradients or the partial derivatives with respect to all the weights and biases. Once we compute that, we can just use the gradient descent update rule, right? Now today what we're going to see is, are there better update rules which lead to faster conversion or better performance in various ways, right? So that's why we are going to look at all these different variants or methods of improving on gradient descent. Okay, so that's the context. I'll just quickly rush through. Okay, so for most of the lecture, I have borrowed ideas from the videos by Ryan Harris on visualized backpropagation, and some content is based on this course by Andrei Karpathy and others, where I talk about some tips for learning rate and so on. So you can just look at those also. Okay, so we'll just quickly rush through the first two modules, which we have already done, which was, we were interested in learning the weights and biases for this very toy network with just one input and one output. And we started by doing something known as guesswork, where we were just trying to adjust these weights and biases by hand, and we realized that it's clearly not good. But we still try to do a very smart guesswork where we were driven by this loss function, which was telling us whether this guess, the current guess, is better than the previous guess or not. And we just kept following our guesswork and tried to reach to some solution. And for this toy network, it was very easy to do that. And what we were actually doing is, there is this error surface which exists, which can be plotted for all possible values of w comma b. And what we were trying to do with this guesswork is trying to find our path over this error surface so that we enter into the better regions. So red is bad, blue is good. Okay, the darker the shade of blue, the better. And this of course becomes intractable when you have many parameters and so on. So we wanted to have a better way of navigating the error surface. So this is exactly what we were doing with the guesswork algorithm. So then this better way, actually we realized that we could arrive at it from a very principled solution starting from Taylor series. And we went through this derivative where we finally came up with this rule that move in the direction opposite to the gradient, right? So that's the rule that we have been sticking to since then. And we also along the way realized some of these things which we defined carefully, which was what exactly this quantity means, right? Which is the partial derivative with respect to w evaluated at a particular weight comma bias configuration, right? Because this is an iterative process. You are at a certain value of weight and bias, and you need to change it from there. Okay. And we then created an algorithm out of this, and when we ran this, we actually derived the full derivative and so on. And then when we finally ran this algorithm, So this is where, now I'll slow down. So when we ran this algorithm, so let's see what was happening here, right? So I'll just start the algorithm from the beginning, okay? So we are now going to run this code, and you tell me something that you observe, okay? So I'm just clicking, so there is no change in the pace at which I'm clicking this, right? So every click of this is one time step, and I'm just continuously clicking this. Okay, I'll start now. Do you observe something? No. Okay. Do you observe something? It was initially slow, then suddenly picked up, and then it again became slow. Why did this happen? The slope is small. Okay, why? Okay. How many of you completely understand why the slow and fast movement was there? Please raise your hands. Good. So that's what we'll focus on now, right? So we'll try to see this. So we'll, I hope this has been fixed. Okay. So let's take a simple function which is f of x equal to x square plus 1, right? This is how it will look like. Okay. Now, in these portions of the curve is actually very steep, right? And in these portions, the curve is a bit gentle, and of course it becomes very gentle over here, right? All of you can see the pen marks properly, right? Okay. So now let's see what this means, right? The steep and fast and small. So let's look at a region which is steep, okay? Now what I'm going to do is, I'm going to change my x by 1. Okay, I moved my x from 1 to 2. How much did my y change? All you need to do is just substitute it in this formula, right? For 2 it evaluates to 5, for 1 it evaluates to 2. So when you move from 1 to 2, your function changed from 2 to 5, okay? So there's a large change in the function for 1 unit change in your value of x. Everyone sees that? Okay. Now let me do the same at a gentle portion of the curve. I'll do it here. Now when I changed the x by 1 unit, again 1 unit, right? It's the same change which I did earlier. Now I changed from 0 to 1. How much did my y change? 1. Okay. Now actually what is this quantity? Delta y1 by delta x1 is the slope. It's the derivative at that point, right? So what are you inferring from this? What happens to the derivative when you are at steep slopes? The derivative is high because the change in y is much faster than the change in x. What happens to the derivative when you are at the gentle slopes? Smaller, because the change in y is small or relatively smaller as compared to the change in x. Okay, or it could also be same. But these two are relatively different is what I'm trying to impress upon, right? And so that means the derivatives at the steep slopes are larger in magnitude, whereas for the gentle slopes, they are smaller in magnitude. Now can you relate it to the observation that you had on the previous slide? When we were at the plateau, it was a very dash slope, gentle slope. What would the derivatives be? Small. Now what are our updates? You have w is equal to w minus the derivative, right? Now if the derivative is small, what will happen to the updates? They will be small. What would happen if the derivative is large? The updates would be large. Therefore, in the gentle areas, you were moving slowly, and in the steep areas, you are moving fast. Okay? You get this picture very clearly. Now this is going to be the basis of a lot of things that we do today. So it's very essential to that you understand this perfectly. Okay? All of you get this properly? Okay, good. Now you might say that, okay, this was only that special point again, right? I always get those questions. So let's see what happens if you start from a different point, right? So now again, the same gradient descent algorithm I'm going to run, but instead of starting at this point, which was my random initialization, I just happened to choose a very different random initialization, which is here. Okay? Everyone sees that? Okay. Now let's see what happens. What do you expect initially? Fast movement, because the slope is a bit steep. Now what would happen? It will become slow because you have entered a gentle slope region. And then again fast, right? So, and then again it will become slow. So see, in this gentle region, right, the changes in W are so small that all your black points are actually indistinguishable from each other. Right? It's almost like a snake's body. Whereas in these steep slopes, you can see a large change in the W, right? You can see gaps between the values of W, right? So this is irrespective of where you start from. Gentle means slow movement, steep means fast movement. Okay, that's the basis. Okay. Okay, so we look at something known as contours. Okay, so now visualizing things in 3D can sometimes become a bit difficult, especially for the person who is making the slides. So we can we do a 2D visualization of this traversal? Have I done this in the ML course? No. Okay, good. Can we do a 2D visualization of this traversal along the error surface, right? So for that, we need to understand something known as contours. How many of you have looked at contour diagrams before? How many of you know how to read them? Okay, all of you know how to read them. So let's see. Now, suppose this is what my error surface looks like, and I have a single scalar variable, right? So this is just a function of w, for example, and this is what my error surface looks like. Okay. Now, what I'm going to do is I'm going to take horizontal slices on this error surface. Fine. Now, can you tell me how this is going to look from the top? Oh, sorry. Let me. Yeah, you just start answering before understanding the question. This is this error surface is actually. So I was wrong in saying this is theta. Assume this is w comma b, and you're just seeing the front view of the error surface. What you're seeing here is just the front view. This error surface is actually like a Dementor's hat. So right. So imagine that it's a hat placed like this, and you're just seeing the front view of this. Otherwise, the top view doesn't make sense, right? So now I'm going to slice this hat at 2 vertical positions, and now you're looking at it from the top. What are you going to see? Ellipses. Okay, everyone agrees with that? Okay, so you'll see something like this. Do you see something peculiar about this? Is this a contour map? Is this? No? Okay, and all of you raised your hands when I asked, do you know contours? Okay, so do you see something peculiar about this? What is it? How many of you get that? So what you're seeing here is this portion, right, where the slope was very steep. The difference between the 2 circles or the 2 ellipses is small, and you can visualize it. If you try to look at it from the top, this distance is actually going to be small, right? And in the areas where the slope was gentle, relatively gentle, the distance is more, and you can again visualize it, right? If you look at it from the top, this is the distance that you're going to see, right? Okay. So, and what do you say about these guys? What does that indicate? They have the same value across that entire region. The value is same because you have taken a horizontal slice at a particular vertical position, right? So you have taken a horizontal slice at this position. That means the error is going to remain the same throughout that rim. Is this clear to everyone? Okay, it's very important that you understand this. Okay, so there are only 2 things that you need to understand if you want to read contour maps. One is a small distance between the contours indicates that a steep slope exists along that direction, and a large distance between the contours indicates that a gentle slope exists along that direction. So everything today is going to be about steep and gentle slopes. And the other thing that you need to know is that whenever you see one circle, the error is the same along that circle or ellipse, or whatever boundary that you see, the error is the same because we are taking these vertical slices. So we are ready with this rule. Everyone understands this perfectly. Okay. So I'll just give you a couple of exercises, and you have to tell me whether you understand this or not. Okay. So I've plotted a 3D surface, 2D. What is this? No. This is a contour. Yeah, everything is not going to look like clean circles always, right? Okay. So this is a contour. Every line that you see here represents one cut along the vertical axis, right? That means the error is the same there. Now what you are seeing is a contour. I want you to guess the 3D surface from this. No, just guess it. I mean, just keep it to yourself. I mean. Oh, the color is the same, right? Blue is good, red is bad. So blue means the darker the shade of blue, the lesser the value of the error. The darker the shade of red, the higher the value of the error. Okay. I want you to imagine the 3D surface. If you can do that, then I'll be sure that you understand how to read a contour. How many of you can imagine this? You can just say yes, right? I can never figure out whether you actually figured it out. Okay. So let me help you with the first one, and then we'll do a few more. So let's start with the extremes, right? So let me see how to do this. So this portion. Okay, I also need to do it for the video. Okay, so let me just do it here. So this portion, what do you think about the slope there? Very flattish. Why? Because This is the line that you see, and the other line is not even in the figure, right? So it's basically very flat. The slope is very gentle. Is it a low region or a high region? High region. Fine. Okay. Now what is actually happening here? What is the slope here? Very high. That's why these two regions are very close to each other. So from this high region, what is happening? Suddenly there is a slope and you're going down. And you know you're going down because we are reaching a blue region. Right? Okay. Now what is happening here? Very flat. And this? Also flat, but slightly upper than the lower guy. Is that fine? Now can you all imagine this? Okay. And is this what you thought it is? Perfectly yes, right? This is exactly what you thought. Okay. Just a minute. So the orientation here has been changed a bit, right? So this portion actually corresponds to this portion. Are the two, this is clear? This portion corresponds to this portion, right? So just orient it accordingly. So you start off this high plateau region, which is here. Then you start going down, you go down, and then you see a fold here, right? That's this fold. So you went to a darker shade, and then you came up to a slightly lighter shade. Maybe the shades are okay. Everyone gets this? You all understand this? Okay, guess the 3D surface. How many of you want to play this forever now? Start with the extremes, the bad guys, the good guys, the plateaus and the valleys, and then see how do you go from the plateau to the valley. Okay, tell me the corners first. This, plateau or valley? Plateau. This, plateau. Higher than this or lower than this? Lower than this. This, towards the valley. It's still between red and blue, right? It's not like right down there. And what happens to all these guys? All are very steep slopes, all converging down into the valley. So can you perfectly imagine this? And you'll tell yes when I show you the 3D surface. Right? Again, you need to reorient yourself. So this corner here is this corner. This corner here is this corner. So we had these two plateaus at the top. We had these slightly higher valley, slightly lower valley, and then all of them going into a very deep valley. Do you see that? Everyone gets this? How many of you have a problem with this? If you have a problem with this, you'll just sleep off in the rest of the lecture. So I want you all to understand this very carefully. I don't mind repeating it. How many of you understand this? You understand the regions with gentle slope? The regions where you have a steep slope and you end up into that valley. Which is the valley here? Can you point it out? Fine? Okay, so we'll move ahead. So now we know what contour maps are and how to visualize them and so on, right? So now we'll try to see the gradient descent algorithm. Instead of running it on the 3D error surface, we'll try to run on this 2D contour map, okay? So this is what I already showed you, right? I started from here and I showed you how it comes here or something like this, right? That was the gradient descent, let me just erase this. Okay, that is something like what the gradient descent algorithm did. Now, again, you just need to reorient yourself. So let's see. This corner is this corner. This corner is this corner, and so on. Right? So you get the reorientation, right? It just shifted. Now I'm going to start my gradient descent algorithm from here, from this point. Okay, everyone sees that? Okay. I'm going to start from there, and you have to help me. Right? I'm not going to just keep clicking. You have to tell me what is going to happen. So what will happen initially? Fast movement, slow movement. Slow movement, right? So I'm running it 1, 2, 3, 4, 5, 6, 7, 8. It just keeps running very slowly, very, very slowly. Now what will happen? Fast, okay? Now you see, actually you can see the arrows. These arrows are the quantity, the magnitude of the movement, right? So earlier this movement was so small that you could not even see the arrows. I've been drawing arrows right from the beginning, but you could not see them at the beginning. Now you can see them, right? Now what will happen? Slow, right? So you see the exact same movement that I did on the 3D surface. Now you can visualize it on the 2D surface, right? And you can easily tell me where it will go fast, where it will go slow, right? And where it will just keep moving very, very, drag its feet and so on, okay? So this is where it starts dragging its feet. And the same thing happened when we were in this region, right? So you just make the connection that we are in the corresponding 3D region there, okay? Fine, so we are moving very, very slow. Okay, and it just keeps running, okay. So that's where we'll end this module. So we just revised gradient descent. We saw that things are proportional to the gradient, that's why gradient descent. And the smaller the gradient, the slower the movement, the larger the gradient, higher the movement. Gentle the slope, smaller the gradient, steeper the slope, larger the gradient, okay? Okay, so now we'll do momentum based gradient descent, okay? In this module, we'll look at momentum based gradient descent. So what were the observations about gradient descent? That it takes a lot of time to navigate regions having a gentle slope. So what's the practical implication of this? In practice, right, what does this lead to? What does this mean? Right, it takes more time. So remember we had said this max iterations equal to 1000. Now if your initialization happens to be such that you are stuck in this large flat region, then those 1000 iterations you just keep moving around that flat region, right? You will not enter into one of the valleys. And valleys is what you are interested in, right? Because valleys is where you'll have some minima for your function, right? So if you have a very, very gentle slope, then for 1000 iterations you'll keep moving around that gentle slope, right? That's why this has a practical implication. Now, this was because the gradient in this region was small. Can we do something better? That's the question, right? So yes, we can, and we'll take a look at momentum-based gradient descent, okay? So here's the analogy which I give. My TAs have heard this at least 10 times, so I'll just repeat it the 11th time for them. So I hope that's the one which I want to use here. Yeah, okay. So now suppose you are standing at the Velachery gate and you want to go to Phoenix Market City, something that all of you can relate to today. So you want to go to Phoenix Market City and you ask the security guy at the gate that, where do I go, right? So he'll say, take a left. No, take a right. So I am slightly dyslexic, actually I have a left-right dyslexia. So take a right, okay? So you will say, okay, he has told me to move right, but you'd still be a bit cautious, right? You'll just keep moving slowly in that direction, right? That's how we ask for directions. You keep moving slowly in that direction, right? Now 100 steps later or 100 meters later, you find another guy and you ask him or her, where is Phoenix Market City? He again points you in the same direction. Keep moving left, right? Right, okay. So now what will happen? You'll increase your pace, okay? And then you ask again someone when you reach the signal where it is, and he again points you in that direction. What will happen? It'll move even faster, right? So what is happening here? If a lot of people are pointing you in the same direction, you better start taking larger and larger steps in that direction. Does that make sense? That's how we find directions and move around, okay? So just like a ball gains momentum as it goes down a slope, right? It's constantly moving in that direction, so it starts moving faster. So now can you tell me a way of incorporating this? I've been moving in a certain direction. These directions are nothing but the gradients, right? And now at this point, someone asks me again to move in the same direction. What should I do? Take a bigger step. So can you think or try to imagine how would you do this mathematically? Okay. Okay, so it's probably there are a few ways to do it. So let's see. So what I'm doing here is, this is my current gradient, right? So I asked that guy at the signal, he asked me to move in that direction. So that's this direction. And this is all my history, whatever I did till step t minus 1. Okay. So now what I'll do is, so earlier I was moving like this. This is what my update rule was. Wt plus 1 is equal to Wt minus in the direction of the gradient, right? I was moving in the direction opposite to the gradient. Now what I have is, in addition to that, I have this gamma update t minus 1. So that means whatever I had done up till step t minus 1, I'll also take that into account. So I'll end up taking a larger step. Is that clear? If it's not clear, it will become clear on the next slide. But is it clear? Okay, so let's see what this means, right? So it basically means that in addition to the current step, also look at the history. There are 3 guys who earlier pointed you in the same direction. So maybe this direction makes sense, right? So start accumulating that and move faster, okay? So let's just break this down and see, right? So this is what the update rule is, okay? this is all my updates and this is the update rule. So at time step 0, my update is 0 because it was not started yet. At time step 1, this is what it will look like. Right? And this is nothing but just move in the direction of the opposite to the gradient, because this minus sign will come later on, right, in the next equation. Is it clear so far? Okay. Now what will happen? Update 2. So it's gamma times update 1 plus the gradient at the current step. So remember, here everything is positive. I'm adding the gradients because my final negative sign is going to come in the next equation. Okay. So don't get confused with that. Okay. Eventually I'm going to move in the direction opposite. That opposite will come from this negative sign. Okay. So what is happening? I am moving in the current direction plus a fraction of the direction which was pointed earlier. Right? Okay. Then does this make sense? So can you tell me in general what is happening here? At the tth time step, what is happening? What kind of average am I taking? Weighted average, but it's a dash weighted average. This is an exponentially weighted average. Okay, so let's look at this, right? So when I am at step 4, I have most faith in the current gradient, right? And this gamma is always, I'll just set it to something less than 1, right? So I have a fractional trust in the previous gradient, even smaller trust in the previous guy, and even smaller trust in the previous guy. So I'm taking an average of all my gradients, but it's an exponentially weighted average. Does that make sense? Okay. My maximum faith lies in the current guy and then decaying faith in the previous guys. Okay. And as I move further and further away from the last guy that I checked, right, I'll give lesser and lesser weightage to that. So everyone understands what is happening here? Anyone who has a problem with this? Just raise your hands if you understand this. Okay, good. So in general, this is going to be the formula, and you see that as is there a problem here? No. As t is larger, this fraction is going to become smaller and smaller, right? So the first step that you take will have lesser and lesser weightage as t increases. Everyone gets this? Okay, fine. So now this is the code for momentum-based gradient descent. I'll just give you a minute to stare at the code and see if it makes sense. So this much part is okay. You're just computing the gradients with respect to all the points, right? And now we are keeping this running sum, okay, which is the previous gradients and the current gradient, right? And then you're just subtracting that running sum. Is that clear? Everyone gets the code? Okay. Now this sorry looking black curve that you see here, that is gradient, this guy. Okay, this black curve that you see here, that's gradient descent when I have run it for around 100 iterations. Okay, now I'm going to run momentum based gradient descent, and each click is going to be one step. Okay, and I want you to observe what happens. Okay, so slowly a red curve will start appearing on the figure. Initially it will not be visible, so don't worry, there's nothing wrong with your eyesight. 1, how many of you already see the red part? Okay, I see it. 2, 3, 4, 5, 6, no, now you can see it, there's nothing great about it. 7, 8, 9, I want you to observe something here. 11, 12, 13, 14, came back, right? So gradient descent, I ran it for 100 iterations, it was just stuck here, right? This was the point at this, and I ran this for less than like around 15 or 20 is what we counted, right? And it's already entered into the value, right? So momentum based gradient descent is good. You see that wicked smile on my face, and you know it's a trick question. Okay, so we are moving fast, right? Even in the regions where the slope was gentle, right? That's the beginning of the beginning of our trajectory, right? This was the gentle region. Even that I was very quickly able to navigate, right? Within 5 to 6 steps, I was away from that part, right? So even in the regions where the slope was gentle, I was able to move fast. But is moving fast always good? Philosophical question. Right? So would there be a situation where momentum would cause us to run past the goal? Same thing, now instead of walking, you are in a car. You ask the person at the security whether I should go there. He says yes, go in the right direction, you keep moving there. Someone else, you keep accelerating. What will happen eventually? You'll go past Phoenix Market City. Then what will you do? Take a U-turn, come back. Again, while taking a U-turn, what will you do? Overshoot and come to the signal and then go back again, right? So you see this, you'll end up taking a lot of U-turns. So let us change the input data a bit and see what happens to momentum based gradient descent, okay? So this is what my data looks like now. So this is not what my data looks like, this is what my error surface looks like. So earlier we had this error surface, something like a flying carpet. Now I have a very peculiar error surface. This is again for the 2 parameter problem, right? W comma B, that means I want to learn a sigmoid function, where I have these 2 plateaus at the top, the dark red regions that you see, and then a very sharp valley, okay? Fine. Can you tell me how I would have come up with this kind of an error surface? What are the points that I would have chosen? Just hold on to that thought, okay? So I have this kind of an error surface, fine. The error is high on either side of the valley, right? Now, could momentum be detrimental in this case? Yes, no, maybe, I don't care. I don't care, okay. Fine, so let's see. This is the, is this the 2D equivalent of that 3D surface? Everyone gets it? I can perfectly verify that you get it. Okay, everyone gets it, I'll assume, right? So these are the very high plateaus where the error is very high, very sharp and narrow valley where the error is low. Okay, so now again this sorry looking black curve is what I have done with gradient descent after some 100 iterations or something. Now I'm going to run momentum based gradient descent and you have to help me in understanding what is going to happen. Okay, again you'll soon start seeing that red curve appear. 1, 2, 3, 4, 5, 6. Okay, what will happen now? It's already fast, that's known, right? Because that black curve was after 100 iterations or so. It's fast. Now tell me what will happen. It will go out. It's actually almost come out of the valley, right? It's almost at the top of the valley. Now what will it do? Take a U-turn. Now what will it do? Again take a U-turn. Now it will keep doing this. It will take now smaller and smaller U-turns and it will converge, right? So what happens here is because of this speedy movement, and which is very analogous to that car movement which I described, you just overshoot your goal, you'll have to take the U-turn, come back. If you're again careless, you'll have to keep taking these U-turns, but you'll finally end up at the location that you want to be, right? It takes a lot of U-turns before converging. Despite these U-turns, it still converges faster than gradient descent, right? Because gradient descent can just not move at those gentle slopes, right? It just can't move from there because the gradient is almost zero because the slope is flat, right? And it just can't move. But even with this, a lot of U-turn and a lot of rework, after 100 iterations, momentum based gradient descent has reached an error of almost zero, whereas gradient descent is still stuck at the plateau at an error of 0.36. Yeah, so see, you have reached the minima now, right? And now you will be navigating there, right? But you know that now your loss is very low. So you could end that, right? You know that your loss is very close to zero. So you could have a condition that once you have reached something very close to zero, you could end that. Even if you are making these very small movements now, you could just stop there.
But in the plateau region, it's also zero.
But the loss is high, right? So if the loss is high and you're not moving, you cannot stop. But if the loss is low and you're not making movements, you can just stop there, right? So you can just end, you can define that as your convergence condition, right? Okay, fine. So let's look at we'll come back to 3D now. We'll look at a 3D visualization and a very different interpretation of what is happening. And I really want you to understand what exactly is happening in this example which I had picked up, right? So this is what the 3D surface looks like, viewed from a different angle. You have these 2 plateaus and a very sharp valley. Now, this is the corresponding sigmoid function where I started with. So what I'm trying to tell you is that this is the sigmoid function corresponding to W equal to 6, W equal to 2 and B equal to 6. This is the sigmoid function that I got once I plugged that value. So sigmoid is 1 over 1 plus e raised to minus Wx plus B. and I've plugged in the values of w and b and plotted it for all the values of x, and this is the sigmoid that I got. Okay, so that's my starting point. Is this good? How do you define good or bad? What do you expect at the end of training? It should pass through all your training points, and these are my training points. Okay, is it passing through them? No, it's way off, right? Okay, so now let's start this momentum based gradient descent, and just see how my sigmoid function changes. Okay, so right now I am on the gentle slope. Even with momentum based gradient descent, it's going to be fast, but not dramatically fast, because it's still building up the momentum, right? So you see that these sigmoids that I'm drawing here, they are almost indistinguishable from each other. I've already drawn 3 sigmoids here, so I'll just go back. So there was this initial guy, then I drew a red one, then one more, and then one more, but they're all very close to each other. Now keep viewing both these sides in parallel. What happens here on this figure and what happens to the sigmoid? Okay, and I'll ask you questions. So still I'm moving a bit slowly because I'm still building the momentum, right? It takes time to build that momentum. Now I've slowly started building the momentum. My sigmoids have started moving towards where they should be. Everyone gets this? What is happening here? Okay, now tell me what will happen. As I enter the valley, I'm almost entering the valley. What will happen? I've gained this momentum now. So my w comma b values are going to change much faster now. So what will happen to these sigmoids? They'll no longer stick to each other. We'll start seeing a difference. They're already moving away from each other. Okay, so that's what's happening to the function. Okay, now you see even faster changes. Okay, now what will happen? I have entered the valley. This is how my sigmoid looks at this point. Now tell me what will happen. It will go past. What will happen to your sigmoid? How many of you know what will happen to the sigmoid? Okay, I'll tell you what happens and then it will be obvious, right? So now I'm entering the valley. All of us know that I'm going to come out of the valley of the other side, right? So let's see what happens when I come out of the valley from the other side. The sigmoid changes. That's why you have this situation that your error is high on both sides, right? Because on this side you have these kind of sigmoids, on the other side you have the other sigmoids, and somewhere in between lies the solution. Where does the solution lie? At a very flat sigmoid, right? So now I start, this is where the oscillations will happen. So notice what will happen to the sigmoids. They will toggle between these two orientations. Okay, just see what happens to the sigmoids. You see it again moves, keeps moving, keeps moving. It keeps oscillating around the solution, and then finally you reach the solution. So you see that? Should I repeat this? Okay, so when I'm on one side of this valley, I have one kind of sigmoids, right? Now when I move to the other side of the valley, I have this other kind of sigmoid and take a U-turn. So when I take a U-turn, I again overshoot and go to the other side. And this keeps happening and I keep toggling till I reach my final solution. Right? So these are all the oscillations that you are seeing. So can you visualize this? What is happening? Do you understand how this relates to the actual function that you are trying to learn? Okay, is this fine? Okay. Okay, so that's where we'll end this module. This was on momentum based gradient descent. Now we'll see Nesterov accelerated gradient. Okay, so let's look at Nesterov accelerated gradient descent. So now we know that momentum based gradient descent is good at these gentle regions. It moves really fast, but we still don't like it because it has this problem of oscillations. It has this problem that it overshoots its objective, right? Its goal, and then it has to take a lot of U-turns. So can we do something about reducing these oscillation? So the answer is always yes. So let's look at Nesterov accelerated gradient descent. Okay. So the idea here is very simple. Look before you leap. Okay. Now remember that this was the update rule for momentum based gradient descent. Okay, and I'll write it down again. Wt plus 1 is equal to Wt minus gamma into update t minus 1 minus eta into the gradient at the current point. Okay, so you see that actually I am taking 2 steps. One is this step and then one more step. And I could just, this is one way of visualizing it, right? That I move according to the history and then I move a bit more according to the current gradient. So everyone sees that there's a 2-step movement happening here. Okay, Now can you think what could have been done? Look before you leap. Okay, so we'll see what we can do. So we know that we are going to move at least by this one, right? That's fixed. We know that our history is telling us to move at least by this one, and then we'll move a bit more by the gradient. Okay, so now can you think about it? I'm at least going to move this much. What if I had some way of looking ahead and then do something at that point? Is this what you're saying? Of course, I can verify it, but I am sure it will become clear once I show the equations, but I just want you to think about it a bit more. Right? It's very simple. It will become absolutely clear once I show you the answer, but just think about it a bit. Okay, so here's the answer, right? Why not compute the gradients at this look ahead point, right? So you are again adding it in two steps, minus the history and then minus the current gradient. So take this value, call it the look ahead point. I know that I'm going to move by this much. So let me not compute the gradients at the current point. Let me move by this much, then compute the gradients and see what happens at that point. Does it make sense? Okay, so this is the equation, right? That first I move by that one step. I had to make a two-step movement. So I'll move by that one step, right? Then I'll compute the gradient at that position, not at my current position, right? This was earlier gradient at point T. Now I have already moved a bit, so I can compute the gradient there and then move in the direction of that gradient. Does that make sense? How many of you are completely lost? You are completely lost? Okay, good. I mean, not good, but yeah, good that you raised your hand. Okay. So, okay. So you understood this, that there's a two-step movement, right? Wt minus history minus the current gradient. Gradient computed at time step t. Okay. Now you know that you're already going to move by the history, right? So why not just move there? And then compute the gradient at that point. So you're anyways made some movement. You compute the gradient at that point and then decide which is the direction to move in, right? So that's what this look ahead value is. Okay. I know it's still not clear to many of you, and I'm very confident it will become clear in the next 5 minutes, because I'll show you one more visualization for this. But just stay with me for a while. As long as you get the intuition, I'm fine. I'll move ahead and then I'll explain it again in a different way. Okay. Is this fine? That should become clear. Good that you asked that question. Okay. So ask me again on the blank slide that I have, and then it should become clear. Okay. So for right now, let me just show you what will happen with the code, and then I'll again explain it with a different way. Okay. Okay. So this is what momentum-based gradient descent did. Okay. Now let's see what nested of accelerated gradient descent will do. Again, the code is simple. You can just read it up. And now I've started executing. You see this blue curve coming over there. Fine. Okay. And now I keep running this. Now what will happen? You see that all the U-turns of the blue curve are inside the U-turns of the red curve. So the objective is being achieved. At least empirically I've showed you that, right? It's taking shorter U-turns. What is probably not clear to all of you is why is this happening? Is it clear to everyone why is this happening? Can everyone visualize that? Okay. So let's see why this is happening. I'll give you an alternate explanation for this. Okay. So, okay. So suppose this is my error surface. I drawn it too big. And I have a single variable with respect to which I'm trying to optimize. So this is my W. Okay. I started off with some initial value W naught. Okay. Now what is the gradient at this point? Positive, negative? Negative, right? Because when I'm going to increase W, the function is actually going to decrease, right? So, right, so the slope is negative. So where will I move? this is the number line, right? So this line is actually the number line because it's a single variable. So where will I move? Positive side of the number line or the negative side of the number line? Positive side. The derivative is negative. I'm going to move in the direction opposite to the derivative. So I'm going to move in the positive direction, right? So I'll end up somewhere here. Is that clear? Fine with everyone? Okay. So now I am somewhere here. What's the derivative at this point? Okay. Now what's the derivative here? Positive, negative? Negative, right? When I'm increasing W, my loss function is decreasing. So my dl by dw is going to be negative. This is positive, this is negative, right? Okay. So again, I'll move in this direction. So what is happening? A lot of negative updates are getting, a lot of positive updates are getting accumulated, right? And now because of my momentum, I am not going to move only by this derivative. I'm also going to move by the history, right? So I'll end up somewhere farther. Okay, is that fine? So now at this point, what is the derivative? Again negative. When I'm increasing W, the function is decreasing. So what is my update? Positive or negative? Positive. So now you see that a lot of positive updates are getting accumulated, right? My momentum is building up. So now what will happen? Now if I just move further, then again I'll get a, let me just put it here, right? So I'm again moving largely in the positive direction because this guy is also positive. All my history was also positive. So I moved in the positive direction. Now what will happen at this point? What's the derivative here? No, it's still, it's negative, sorry. So again I'm going to move in the positive side of the number line, okay? Now at this point, I want to break down the movement into 2 points. One is what my history was telling me, which was all these positive updates. But of course, I'll not make such a large update because I'm weighting them exponentially, right? So, but it's telling me to move in the positive direction, okay? And I know that the gradient at this point is negative, but I want you to ignore that for now. I just want you to focus on the history. If I just move according to the history, where will I end up? I'll end up somewhere here, right? Because the history is very positive. So I'll keep moving in the positive direction. And this is my W look ahead. Okay. Now, what will happen if I compute the gradient here? The gradient is positive. So where will I move? Negative. So you see now why momentum works? Because you are able to look ahead to this point. Instead of what should I have actually done is I should have looked at the gradient at this point. The history is positive. The gradient is also telling me to move positive. So I would have moved a large positive and I would have ended somewhere here. Instead, I just moved by the history. I checked where I end up. I end up here. Now let me see what's the gradient at this point. Have I already overshot my objective? When will I overshot my objective? It is the sign of the gradient changes, right? It became from negative to positive. And now since it's positive, because as I'm increasing W, the loss is also increasing. So now where will I move? Negative. So now what's the second step actually? It's again bringing me close to here. So instead of taking this large U-turn, I end up taking this small U-turn. Is this clear to everyone now? How many of you still don't get it? How many of you get it now? Good. Sure? Okay. So this is what, and now you can relate it to what was happening on the figure. So let's go back, right? So you saw that I was making these smaller U-turns because when I was at this point, right, I already moved by the history. I knew I would end up somewhere here where I would need to go back, right? So I already accounted for that and made a very small movement. Is this clear? Everyone gets this? How Nestor of accelerated gradient descent works? Sure? Raise your hands. So looking ahead helps NAG in correcting its course quicker than momentum-based gradient descent, right? So it's already looking ahead, where do I land up, and already making a correction if required. If not required, it will again move in the right direction, right? So the update is this guy plus the gradient, and my update happens on the original value, not on the look ahead value. So her confusion was perhaps that I am doing W look ahead minus update, where this update again has this quantity, right? That's what your confusion was. But I'm not doing W look ahead, I'm using WT there. Everyone gets this? Okay. So that's where now it's clear that why the oscillations are smaller in the case of NAG. and it's able to correct his scores quicker. Okay, so that's where we'll end this module. And now we'll look at stochastic and mini batch versions of these algorithms. Okay, so we'll digress a bit. Actually, we should have ended up somewhere else, but I'm just going to digress a bit. Okay, so this is the original gradient descent code that we had, and I've highlighted something in this red box. Okay, so notice that the algorithm actually goes over the entire data once before making an update. It is going over this entire for loop, which is over all the data points. Of course, in this toy example, I had only 2 data points, but in practice, I'll have many data points. I go over all the data points, compute the derivatives, and then make this one update. Okay, why? Because that is the right thing to do. Okay, this was the exact formula that we painfully derived, right? That the gradient with respect to the loss function, right, which we had this summation I equal to 1 to n, remember? And the true derivative was a sum of the derivatives with respect to all the data points. That's what we analytically derived, and hence we are doing that, right? Because that's the right thing to do, not for any other purpose. Okay, that's what it should always be, right? So that's the right thing to do, because this is a true gradient and we actually derived it. Okay, and hence this was not an approximation, so all the theoretical guarantees hold. If I do this, I know that now this is the true gradient or the true derivative, and if I move in the direction opposite to the gradient, everything falls in place because I proved it using Taylor series. Okay, but what is the flip side of this? This is the right thing to do, but what's the flip side? If you have millions of points, you'll go over all these million points and make this one update. Now imagine the consequence when you are in a plateau region, right? Even with momentum or whatever, your movement in the plateau is going to be relatively smaller, right? You're going over these million points and making that tiny delta update, right? So imagine how much time it will take your algorithm to converge. You get the problem? Okay. So the algorithm will take a million calculations and then make one tiny update to your W. Okay. This is going to be very slow. Can we do something better? Always, right? So let's take a look at stochastic gradient descent. Fine. So I've done a very subtle change to the code. What is it? Don't tell me indentation. But that's what I've done, so you can tell me that. So what is happening now? For every data point, I'm making an update to my W values. This is perfectly fine. Yes? Okay. Now the algorithm updates the parameters for every single data point. If you have a million data points, how many updates will we make in one pass over the data? A million. For every data point, we'll make an update, right? So that's slowness factor in what is known as batch gradient descent, right? Batch gradient descent is when you look at the entire data and then make one update, okay? What is the flip side? What was this module titled? Stochastic gradient descent. So what is the flip side? These are not the true gradients. The true gradient is summation over all the points. Now this is no longer the true gradient. This is just a point estimate, right? This is just a approximation of the gradient, right? And stochastic, because we are calculating the gradient based on a single data point, right? We're just sampling one data point and computing the gradient, that this is what the entire population looks like, right? This is almost similar to tossing the coin once and saying that this is what the probability of heads is. If it lands at heads, then the probability is 1, otherwise it's 0. Right? You see the error? You see the problem with that, right? As opposed to tossing the coin 1,000 times and then deciding the probability, you're just tossing it once. So this is always going to be erroneous, right? This is going to be bad. So now there is no guarantee that each step will decrease the loss. Why? Because the guarantees were only when you are doing the right thing, which was to compute the gradients over all the data points. Now there is no theoretical guarantees, right? Because it's all stochastic now. So it is possible that in a particular data point, your loss might increase also. The overall loss on the data. With respect to that point, it might decrease, but with the overall loss, right? So now let's see this algorithm in action, and I want you to make certain observations about this. So this is the code that I'm going to run now, okay? So let's see. Okay, so I'll start, and you have to observe and let me know. This is really becoming an eye test for all of you, but that's good. Okay. So far nothing interesting to observe, or already maybe. Okay. Remember, I'm running gradient descent. This is not momentum, not Nesterov. This is gradient descent. Okay, I've already given you the answer. What do you observe? I can still pretend an answer, right? Let's do that. We see many oscillations. Why? Why do we see the oscillations? Are these oscillations the same as the oscillations that we see in momentum? No, these are different. Everyone gets that, right? Why are there oscillations? What does each click here correspond to? One data point, right? So what is happening here? Because we are making greedy decisions, right? We are looking at one point. This point says to decrease the loss with respect to me, move in this direction, and we blindly move in that direction, right? Now we look at the next point. It says, oh no, wait, you need to move in this direction. So we again move in that direction. So all these points are actually trying to just make things better for themselves. They are not thinking about what is happening to all the other points in my data, right? So all these points are actually competing with each other. So some decision which I took with respect to where to move, which was locally favorable for one of these points, may not be good for the other point, right? Hence I keep these tiny oscillations which I make, right? These are the stochastic noise that you are seeing now, right? Everyone gets this? Okay? Is this fine? Okay. Now, can we reduce the oscillations by improving the stochastic estimates? Always yes. Okay, fine. So let's see, what do I mean by that? So we'll look at a mini batch version of this. So what I'm going to do is, instead of, so this code is actually for mini batch stochastic gradient descent. It's a very minor alteration on the stochastic gradient descent. I'll just let you stare at it for a minute or so. What I'm doing here is, instead of doing it for every point, I'm waiting for a certain number of points and then making the update. Right? That's what I'm doing here. Okay. Now for this, I've kept k equal to 2. What does that mean? I look at 2 points, compute the derivatives with respect to them, and then make an update for 2 points at a time. Okay. What do you expect? No, what do you expect with respect to this code? Okay. Okay. So let's see. We'll try to run this now, and you'll start seeing a red curve here, and make some observations about this. Okay. So this is the red curve. Yeah, it's visible. Oops. Don't read any of those. We need to fix this, right? These bullets should come only after the curve has finished its journey. Okay, don't read any of that. So what do you see about the red curve? It's completely contained inside the black curve. That means its oscillations are smaller than the black curve, right? Does that make sense why this is happening? Because now you're not listening to just one point, you're listening to 2 points, and then at least you're doing something better, right? Instead of just taking one. So what's the analogy with respect to our coin toss experiment? You're tossing the coin twice and then deciding what's the probability of heads or tails, right? So it's always going to be slightly better than tossing it only once, right? And now what will happen in the limit if I keep increasing this? You'll end up with a batch gradient descent where you look at the entire data. So looking at only one data point is bad because it's very noisy. Looking at the entire data is bad because it's very time consuming. So you need to do something in between, which is mini batch gradient descent, okay? And typically you look at values of 16, 32, 64, but it also depends on the amount of data you have, right? If you have 1 billion points, you might actually want to look, because if you have 1 billion points and you have a batch size of 64, you'll take 1 billion by 64 times to finish the data once, right? So you might want to keep a larger batch size at that point, right? But just ignore that, but you will try different batch sizes and see which one works better. So in the assignment, are we asking them to experiment with batch sizes? Yes? Okay. No, sorry, wrong question. Are we asking them to implement stochastic and mini batch also? Or only vanilla? Mini batch. Okay, fine, that's fine. Okay, so you'll see this in your assignment, okay? So everyone sees what was the difference between stochastic and mini batch, right? You have better estimates now, and therefore this red curve is contained inside the black curve. Okay, fine. Okay, so these are some things to remember. One epoch, get used to this terminology. One epoch is one pass over the entire data. One step is one update to the parameters. N is equal to the number of data points and B is equal to the mini batch size. Now you have to fill in the second column. In vanilla or the batch gradient descent, what is the number of steps that you take in one epoch? 1. In stochastic gradient descent, N. N. In mini batch gradient descent, N by B. Everyone gets that? So get used to this, okay? So this epoch, step, batch size, all this is something that you will see regularly when you are reading papers on deep learning, okay? Fine. So similarly, we can have the stochastic versions of momentum-based gradient descent and Nesterov accelerated gradient descent, okay? So these are just the codes. It's very easy to see what is happening here. Again, basically this is just an indentation, right? So if you look at the difference between the two codes, I've just indented it inside. That means I'm making these updates for every data point, right? And same thing you could do for Nesterov also. Okay, now let's see. This, guess, what is it? This is the gradient descent, stochastic gradient descent, okay? Now let's see if you have really understood NAG and momentum-based gradient descent. One of these curves here corresponds to stochastic NAG. The other one corresponds to stochastic momentum. Tell me which one is which. Blue pill, red pill. Blue is? How many of you say that? Okay, I'm confused. Okay. How many of you say that blue is momentum? How many of you say that red is momentum? Oh, there are so many who don't have an opinion. Not clear. Okay, I'll buy that. So, okay, so look at this. Who is taking longer U-turns? Momentum or NAG? Momentum. Roughly, which guy is taking the larger U-turns? Red guy, right? I mean, roughly speaking. There's only one point to judge by this here, because here they're almost same. And that could happen in practice, right? Because this is now noisy, okay? So the red curve corresponds to momentum because it's taking a larger U-turn. We saw that momentum takes larger U-turns, and the blue curve is corresponding to NAG, okay? So, no, okay, I remember, this was an error on the slide, yeah. So this has to be red and this has to be blue. So, okay, so the momentum is actually red and the NAG is blue, okay? Because it's taking a shorter U-turn. And the reason you don't see it very clearly here is because both of these are running in the stochastic mode, right? Okay, but you still see the relative advantage of them, that NAG still takes shorter U-turns. Both of them are faster, still faster than vanilla gradient descent. You see that black curve at the top, and both of these are faster than that. Both of them, all three have run for the same number of iterations, right? After 60 steps, you see what happens to stochastic gradient descent and what happens to NAG and momentum-based gradient descent, right? Okay, fine. And of course, you can have the mini-batch versions of momentum and NAG also. Okay, so tips for adjusting the learning rate and the momentum. So before moving on to these slightly advanced optimization algorithms, we'll revisit the problem of learning rate in gradient descent, okay? So one could have argued that we could have solved this problem of this slow movement on the gentle slope by increasing the learning rate. Remember that we have this eta and we deliberately chose to be conservative, that we'll take a small value for the eta. But what if I just blow up the eta? I could just take a very large eta. What would happen? It will overshoot, right? So what will happen is, I'll see what happens when I take eta equal to 10, okay? So I'll see what happens when I take eta equal to 10. So this is step 1, step 2, step 3. It's moving very fast on the regions where the slope is gentle, but it also moves very fast, much faster on the regions where the slope was already steep, right? So when the gradient was actually high, you ended up blowing it further by multiplying it with the eta, which is 10, right? So it's again going to have this effect that you will move much faster in the steeper regions, and again you will see these oscillations because you will overshoot your objective. Does that make sense? Right? So it's not that you can always choose a high eta and get away with it. So what do you actually want? What is your wish list? Regulate theta. You want a adaptive eta, right? That it somehow figures out that I'm on a gentle slope, so I should move slowly, I should move fast. And I'm now on a very fast slope, so I should move slow. So having this one eta is not working for every point on the error surface, right? For everywhere on the error surface. Is that clear? Okay. So we'll see such algorithms soon where we try to adjust this learning rate. Okay. Now here are some tips for the learning rate. So how do you, if you're just going to deal with this gradient descent or nag or momentum, how do you adjust these learning rates, right? How do you fix the learning rate? So a learning rate is typically something known as a hyperparameter. So why is it called a hyperparameter? So what are the parameters? Which are learned using the objective function. Eta is not a part of the objective function. You're not computing gradients with respect to that. It's a hyperparameter. So we'll try to tune this hyperparameter. So what you will do is, in practice, you could try these different values on a log scale. Okay. Next, what will you do? Run all these for a few epochs. Note down the dash. Just note down the loss function, right? So run all of these with different learning rates for say 5 epochs. You'll get some loss, right? Now which one will you pick? The one which led to the maximum decrease in the loss. So you'll keep that learning rate, and now what you will do? You just stick to that. I started off with a dash scale, log scale. Now what will you do? Okay, so now run it for a few epochs, figure out which of these learning rates on the log scale works well. Now do a finer search around the best learning rate that you discovered, right? So say 0.1 was the best on the log scale. So now look at 0.2, 0.3, 0.4, 0.5. Look at values around it and see which one works better, right? So this is how you will tune the hyperparameters. Otherwise, there's a very wide range, right? If you tune from 0.0001 to 0.1, there are just too many values to consider, right? So you'll have to do this log scale and then a linear scale. Does that make sense? Okay. These are just heuristics. There's no guarantee that will always work or which of these is a clear winner strategy, but you have to try this. So tuning a learning rate is an important part when you're working in deep learning, right? So at least when you're working with gradient descent or nag or momentum based gradient descent. Now, here are some tips for annealing the learning rate. Okay. So there's something known as step decay. So what you can do is halve the learning rate after every 5 epochs. Can you tell me the intuition for this? What do you expect after 5 epochs? That you have moved enough and now you're closer somewhere to the solution. So if you're closer to the solution, if you're closer to Phoenix Market City, do you want to move fast or slow? What will you do? Decrease the learning rate, right? So after every 5, now this is again, what is so sacrosanct about 5? It's just a magic number, right? So this is again a hyperparameter. So you could fix some number of epochs, and after these epochs, I'll just halve the learning rate, okay? Now this second one is what my favorite is, and I typically use this. What I do is, I compute the loss after epoch t. I run epoch t plus 1, I compute the loss again. If the loss has increased, what will I do? I'll just throw away all the updates that I've made in this epoch. I'll decrease the learning rate and again start this epoch. What do I mean by throw away all the updates? So after epoch t, I'll save my model. I'll save all the w values that I have computed and I'll let it run for one more epoch. After this epoch, if my loss function actually increases, I'll reload this model which I had saved, halve the learning rate, and then run this epoch again. Does that make sense? Okay. Okay. So I've run till epoch t. I have some values of w's and b's. I'll save this values. I'll just save it as a numpy array. Okay. Now with the same learning rate that I've been using so far, I'll run the epoch t plus 1. Okay. And I get some new values of w comma b. Right. I'll plug this into the loss function. I'll plug this into the loss function. I'll get 2 loss values. If this loss value is greater than what I was at the previous time step, that means things did not work out well in this particular epoch. So I'll throw away all these updates. I'll just reload the model which I had saved. I'll just start from where I was at epoch t. I'll decrease the learning rate. I'll make it half and run this epoch again. Right? And hopefully now I should do better because there's something, I'm just making a hypothesis that The reason I did not get to a better loss function was because my learning rate was not adapting to it. Right? So I'll just halve the learning rate because this solution was good. This was a low loss function. I just want to be something around it. I don't want to make any drastic steps. So I'll just halve the learning rate from there. So then you'll not see this drastic change, right? Your loss function should not improve. So first of all, local minima is a known problem in deep neural networks, right? So what happens is that in deep neural networks, you don't have something which is like a neat convex function as your loss function, right? It's a non-convex function, which means there's no one unique minima. There could be several minima, okay? And there are several analyses which show that a lot of these minima are equivalent, okay? So in practice, these are the things that you do. Either once you reach a minima, you just stay there. The second thing that you could do is, you have trained your algorithm, trained your parameters for say 100 epochs and you have stopped now. Now again go back and start with a different initialization. So you started with some W0, B0 and you have reached to some solution. Okay, keep this solution. Now start with a different initialization. That means if you look at your WB plane, you have started from some other point. That means you started from some other error location. Right? And run this algorithm again and see if you reach a different minima. So the only thing the way you counter this is, you just try different stochastic things, right? You try to start with 10 different initializations, every time reach a minima, and then at the end select the lowest possible of these. Did this make sense to most of you? How many of you got this? Oh, cool. Okay, I thought I was just rambling, but yeah, okay. Fine. Does that make sense? To you at least, okay. Does it? Okay, fine. Yeah, so local minima is a severe problem in a lot of deep learning optimization, okay? And typically, people get away by that by just picking up one of these minima, okay? Fine. Now, the other thing is you could use exponential decay, where with each time step, you just keep decreasing your learning rate, right? And if this k is 2, that means that every time step you are halving the learning rate. So you just get with something like this, okay? But the reason I don't like this is that you have one hyperparameter which is eta, which you are trying to tune. And now to tackle that problem, you have introduced one more parameter which is k, hyperparameter which is k, right? So it becomes harder to tune that now. And there's a similar thing which is 1 by t decay, where you try to use this formula to decay your learning rate, okay? So both of these I typically don't use in practice, I use the second one. I prefer the second one, okay? Now, tips for the momentum. Can you make sense of this? You just stare at it, it will just come at you. Okay, let's see. What happens at t equal to 0? This becomes 0. Log 1 is 0. This is 2 raised to minus 1 minus 0, which is just 2 raised to minus 1, which is 0.5. So what is your mu t at t equal to 0? 0.5. Okay. Does that make sense? Is it fine with everyone or is it confusing? No. Okay. Mu max is typically this. Okay, let's assume mu max is this. Okay, fine. Now what happens at time step 250? This is 250 by 250, so this becomes 1. 1 plus 1 is 2. The best thing that you learn in this course. Then log of 2 is 1. So this becomes 2 raised to minus 2, which is 0.25. So what is this? 0.75. Okay, let's do one more. At t equal to 750. Okay, 1 minus 1 by 8, so that's what it's going to be, right? Okay, so then what is happening as my time steps are increasing? What is happening? I'm having more and more faith in the history or the current gradient. What am I increasing? Actually, I made a mistake. Actually, this is mu is gamma. This is not. We did not use mu anywhere, but you guys just went along. So this is gamma actually. Right? That was the momentum term that we had. So as the number of time steps is increasing, my gamma is increasing. That means I am having more and more faith in my history. Learning rate is eta, momentum is gamma. So it's gamma into update t minus 1 and eta into gradient at the current time step, right? And here gamma is actually equal to mu. Is there any more confusion that I can add? Okay. So when I say gamma, I mean mu, okay? And so that's how it is. So as I'm increasing the number of time steps, I have more and more faith in the history. So that means I don't want to now get distracted by this one update which I'm making, right? I want to go by the history. And I'm not increasing this gamma or mu indefinitely. I'm capping it by a max. So at max, I'll have this much faith, which is 0.999 in the history. Does that make sense? This is again just a heuristic. Don't worry too much about it. So that's how it is. So we were looking at these different variants of gradient descent. We saw that gradient descent has this problem that it finds it difficult to navigate the gentle slopes. So we came up with these tricks on momentum-based gradient descent and also Nesterov accelerated gradient descent. The trick in momentum was that if a lot of your history is telling you to move in a direction, then just continue, gain momentum in that direction. So instead of just updating based on the current gradient, you also update based on the history, right? And there we saw that, okay, this is always going to be a problem that you'll end up taking U-turns. And we had this analogy of how you look for directions and you just overshoot your destination, then have to come back and take a U-turn and come back and so on. So to prevent that, we realized that the update done by momentum-based gradient descent is a two-step update. You actually, the first step is based on the history, and then another step based on the gradient at the current time step, right? So then instead of doing this two steps at one go, why not just update based on the history, see what the gradient there tells you, and then we saw this nice figure, I hope it was nice, and where you saw that if you look at the look ahead point, then you will be immediately corrected with respect to your errors, right? So that was about nag and momentum. And then we saw the stochastic versions of these algorithms where we realized that if we do the batch version, then we go over 1,000,000 points and then make only one update, which could be very slow in cases where you have large data. So we then decided to do the stochastic version where we just update for every point. That again had these oscillations because we were taking greedy decisions. We were just relying on one point to tell us which was the right direction to go on. And we saw that these estimates become better as you increase the value of this k, right? So k equal to 1 is the most stochastic version. And then k equal to 2, you get the mini batch version, and then you could just have different values of k so that you have more reliable estimates of the gradients, right? And in the limit, if you have the entire data, then you're just doing the full batch gradient descent, right? Which is the vanilla gradient descent. Anything else did we cover? Then we had some tips on the learning rate and the momentum. These are again heuristics. I gave you some ideas. You could try these in your backpropagation assignment and see which one works better for you. You could see if you have any peculiar observations while implementing the backpropagation assignment, okay? So now there are a few more things left in this lecture. So I'll start with line search first, okay? So this is one more thing before we move on to some more interesting algorithms, which are the current state of the art in a lot of deep learning solutions, right? So most papers that you read would have algorithms that we'll see after 10 minutes, okay? So now just to contextualize things, right? So we are still trying to see what's the right learning rate to use. Now line search is one such method where instead of just doing one learning rate, so can you look at the code and just focus on this part and tell me actually what are we trying to do? How many of you get what the algorithm is trying to do, right? So far what we were doing is we were just having a single learning rate, okay? And we saw that this learning rate can make a lot of difference, right? Because if you're on the gentle part, you want a larger learning rate. If you're on the steep parts, you want a smaller learning rate. So just fixing the learning rate to one value does not really help, because then you will suffer on one of the two cases, right? Either on the gentle case or on the steep case. Now what line search does is, instead of just using one learning rate, at every step, now whether it's vanilla gradient descent, which is the batch one, or mini batch or stochastic, right? Just use a bunch of learning rates. So I've used 5 different learning rates here, okay? And I've computed the gradients. That part remains the same, right? The computation of gradients does not change. Now you have the value. Now you want to be conservative. You want to multiply the gradient with this eta, right? But you know that you don't always want to be conservative. In fact, in some cases, when you're on the gentle slope, you don't want to be conservative at all. You want to actually blow up the gradients, right? So now try these different learning rates and update W and B, okay? So if you have 5 learning rates, you'll get 5 different updated values for W comma B. Now plug in all these W comma B values into your loss function, right? And see whichever is the minimum. Retain that W comma B value and repeat the process. That means again you will compute the gradients with respect to this new value of W comma B and the new loss function. Again try out these 5 different learning rates and continue. Everyone gets that? Okay. So now are we using a fixed learning rate at every step? No. And now do you see that if we are at a gentle slope, it would pick probably this as the learning rate, and if we are on the steep slope, it should probably pick one of these as the learning rate, or even lesser than that if you have that as option. Does that make sense? So you see the advantage of this. Now we are in some way heuristically trying to adapt to the slope of the error surface, right? By just giving it different learning rates. Okay, so you're saying try all of these, whichever works best, pick it up. Okay, so that's about it. You're trying different values. Now what's the flip side of this? Now if you have k different learning rates that you're trying, then at every step you have now increased your computation k times, right? So earlier you just had one learning rate, you're just going by that, but now you have k. So now this is again a trade-off which you'll have to see. Now I'll give you an example where this trade-off clearly works, right? So now if you are at the gentle slope, now making k more computations and moving out of that slope is definitely worthwhile as compared to just sticking to that slope, where even after 100 more computations, you will not really move out of that slope. So remember that gradient descent algorithm that we had seen, where you just stick to the gentle slope after 100 iterations also, right? But instead, if I tried 5 different learning rates, then there is a high chance that I could have moved out of the gentle slope. Does that make sense? You see the advantage of this? Okay, fine. Okay. So this is something that you have to talk about when I come back to second order optimization, which my TAs don't allow me to teach, so I'll see when to teach that, okay? So let us see line search in action. So this is again gradient descent, this black curve which is visible there, okay? This is the one I'm talking about, which is run for few iterations and it's just stuck on the steep slope. You know this story now, right? It just gets stuck there, okay? Now let's see what happens if I run. So now I'll start running the line search based gradient descent, okay? So what do we expect now? Okay, so it will just move very fast, right? So on the first step itself, it is crossed wherever gradient descent was stuck after 50 iterations or so. I'll keep moving fast, okay? Now here's an interesting question. Would you see oscillations here? So when do you see oscillations? When your loss has actually increased from whatever it was currently. Will that happen in line search? Is the answer always no? It could happen. When could this happen? So it depends on the learning rates that you have chosen, right? So if you have chosen the learning rates not, so suppose at one point to really be effective, you needed the learning rate to be 0.01, okay? And now if 0.01 learning rate was not in your set, right? That means everything that is there in your set is faster than 0.01. So then it will again have the same problem as momentum, because you will move faster than what you should actually move. So it depends on this careful choice of the learning rate set. How many of you get this? Okay, good. Right. So that's all I had to say. So there is a slight, so convergence would be faster than vanilla gradient descent, that is obvious. And we see some oscillations, okay? And this statement is actually wrong. We need to remove that, okay? We see some oscillations, and these could be the similar ones to the ones that we see in momentum, because we overshoot, because we have not chosen the right set of learning rates, right? One of the learning rates which was actually needed at a particular point, right? Say at this point, suppose I needed to move very slowly, and that very slowly is say 0.001. And if that was not in my set, then any other learning rate is always going to be faster than, right? So you could see oscillation.
In this video, we'll try to look at an explanation for why we need bias correction in ADAM. Okay, or in other words, I want to explain why do I do this particular step. Why did I take MT and VT as it is, but why did I do this particular step which I had called as the bias correction step. Okay, so note that in the case of ADAM, if you look at this equation for MT, we are actually taking a running average of the gradients and storing it as MT, right? So this is the gradient, and we are taking a running average or exponential running average of these gradients, okay? Exponentially decaying running average, right? So the reason we are doing that is that we don't want to rely on a single estimate. So we don't want to rely only on gradient of WT. We want to look at the overall behavior of the gradients over multiple time steps and then take a decision. So that means if one particular gradient at time t is actually pushing us in some direction, we don't want to be very hasty and start moving there. We want to accumulate the history and appropriately weigh everything in the history. That's the idea behind taking this running average of gradients. Okay. And the other way of looking at it is that we are interested in the expected value of the gradients and not the point estimate at time WT, right? At time t rather. So gradient of WT, which is this quantity, is just the point estimate at time t. We are not interested in that. We are interested in the expected value, and our behavior should be according to the expected value. That's what we desire. So, however, instead of computing the expected value of this quantity, which should have been ideal, we are computing MT as the exponentially moving average. So, in the ideal case, we would want that these two quantities are the same, that the expected value of MT, the way I am computing it, and the expected value of the gradient of WT should be the same. If that is the same, then I am fine, because then that means I am just taking the expected value or of the gradient instead of relying on the point estimate. Okay, so let's see if that is indeed the case. So for convenience, we are going to just denote this gradient WT as GT, because it's cumbersome to write this grad symbol, and it will just not make it so readable, the derivation that we are going to do. So I'm just going to replace that as GT. So what I have written is GT here instead of grad WT, right? So from now on, I'll just use GT for grad WT. Is that fine? Okay. So, so we have this expression for MT. So now let's just try to expand it and see what happens, right? So at M0, it is going to be 0 because that's my starting point. So I have no history, nothing. So I'm just going to keep it as 0. M1 is my first time step, at which it is going to be beta into M0. So I've just substituted t minus 1 and t here. In the original expression, I've just substituted appropriate quantities for m of t minus 1 and g of t. So m of t minus 1 is 0, m0, and g of t is g1. And of course b0, m0 itself was 0. So what you will be left with is 1 minus beta g1. Now let's look at what happens is m2. m2 is going to be beta m1 plus 1 minus beta g2. But I already have an expression for m1, so I'm just going to substitute that here, and this is what I get. Okay. Now let's look at m3. m3 is again going to be beta times m2 plus 1 minus beta times g3, and I have an expression for m2, so I'm going to substitute that here and see if that leads to something interesting, right? So I've just substituted the value of m2 here, right, and I already had the m3 part here, this term here as it is. Okay. So now let's see. So this already starts looking something interesting. You see some pattern here. In particular, we could take these 1 minus beta terms outside. They can be taken common, and then you'll be left with beta square g1 plus beta square g1 plus beta g2 plus g3. So let's try to write this more compactly, right? So I've taken 1 minus beta common, and then I've written the remaining terms as this particular summation. And you can verify, right? So when I is equal to 1, this is going to be beta 3 minus 1, which is beta square into g1. When I is equal to 2, this is going to be beta 3 minus 2, which is going to be beta into g2. And when I is going to be 3, this is going to be beta raised to 3 minus 3, which is beta raised to 0, which is just 1 into g3, right? So we get back the same expression that we had here. Of course, there is a 1 minus beta outside. So this is a more compact way of writing it. And this was for the 3rd entry, right? This was for M3, the 3rd entry. Now, what if we want to write it for the 10th entry in general? What if we want to write the expression for MT? right? So in general, mt we can write it as 1 minus beta as I equal to 1 to t, beta raised to t minus I into gi, right? So this 3 is here, I have just replaced them by t's, right? You can just verify that this is you can just generalize from the third entry to the tth entry, okay? Fine. So now let's see, we have the following expression. We have simplified the expression for mt and written it more compactly. But what we were eventually interested in the expected value of mt, right? We wanted to show that certain things holds for the expected value of mt. So just take expectation on both sides. So this is what we'll get, okay? Now 1 minus beta is of course a constant, so I can move it outside the expectation. So then I get an expectation of a sum. Now the expectation of a sum is the same as the sum of expectations. So I can write it as a sum of expectations, okay? Now again beta is a constant, so I can take it outside the expectation. So what I will be left with is beta raised to t minus I outside and expectation of gi, right? So this is actually expectation of g1 when I equal to 1, then expectation of g2, expectation of g3 and so on, okay? Now we will make an assumption that all these gi's, that means the gradient at time step 1, the gradient at time step 2, the gradient at time step 3 and so on, they all come from the same distribution, okay? We are going to make that assumption. So let's try to understand the implication of that, right? So let's say this was the distribution from which g1 came, right? Suppose I am dealing with a scalar quantity and maybe this was the distribution from which g1 came. Now g2 could have come from a different distribution, g3 could have come from a different distribution, and if that was the case, then expectation of g1 would be different from the expectation of g2 and so on. So what we have assumed to make things simple for us is that g1, g2, g3, any gi comes from the same distribution, and hence we can say that the expectation of all these gi's is going to be just the expectation of g, that is this one single distribution from which these entries come. This is of course a very strong assumption, but we are going to live with this assumption, okay? So then this expectation of gi just becomes expectation of g. So I have gotten rid of the index I, that means I can move it outside the summation, right? So this is what I will get now. These two have come out of the summation and inside I have this quantity. Now let me just expand this quantity. This is nothing but beta raised to t minus 1 plus beta raised to t minus 2 plus so on. At last you will reach t minus t, which is just going to be beta raised to 0. So this is nothing but a sum of a gp with common ratio beta, and I can replace that sum by this formula. This is the formula for the sum of a gp with common ratio beta. So I have just replaced that. And now what happens is this 1 minus beta and 1 minus beta cancel out. So I get this particular expression that the expected value of mt is equal to the expected value of g into 1 minus beta t. So I'll just take 1 minus beta t on the other side and I can move it inside the expectation because it's a constant, it does not matter. So I'll get as, I can just move it inside. So I'll get it as expectation of mt over 1 minus beta is equal to expectation of gt, right? And this quantity, the one which I have circled, is nothing but m hat t, right? This was exactly the bias correction that I was applying. If I go back to the previous slide or the slide before that, so this was exactly the bias correction that I was applying, right? So what I have inside is this. So what I have shown is that if I apply the bias correction, then the expected value of the bias corrected mt is equal to the expected value of the gradient, and that's actually what I wanted. I wanted that whatever mt I am computing, if I look at its expected value, it should be the same as the expected value of my gradients, and that's what I have arrived at, right? Hence this bias correction makes sense, and hence we apply this bias correction for Adam. So this we have shown for mt. We had a similar expression for vt, right? So for mt we had this bias correction as m hat t, and similarly for vt also we had this bias correction as v hat t. So you can derive the same kind of derivation for vt also and show that that bias correction makes sense, right? So this is an explanation for why you do bias correction in the case of Adam. Okay, so we'll end this lecture here. Okay, thank you.
Okay, so finally we come to the more interesting part. So in this module, we'll look at gradient descent with adaptive learning rate. So first we'll see motivation or intuition for why we need this. And once we get the motivation, I believe the rest should be straightforward. Okay. So far what we have been doing is, so please pay attention on this slide. I need to define some notations and you shouldn't get confused with them, okay? So far we have been dealing with a situation where we had just one feature, which was X, and one weight corresponding to it, which was W, and one bias, which corresponded to the always on input, right? Now we are going to look at a situation where we have more than one inputs. That means earlier we were basing our predictions only based on the director. Now we have the director, actor, genre, IMDb ratings, and so on, right? So here X1, X2, X3, X4, these are 4 different features or 4 different inputs that I have, okay? And these are not, this is not X squared, just, I know it's obvious, but I'm just making it clear, right? So this is X1, X2, X3, X4, okay? Not probably the best choice of notation, but I'll just stick to that. So now each of these has a corresponding W1, W2, W3, W4, okay? And this is how your decision looks like. It's the dot product between the weight vector and the input vector, okay? This is how I'm going to decide, and that's a single sigmoid neuron again. Now, so given a single point X, Y, do I need to again go through this computation? Sorry, W comma P. Oh, sorry. Okay, I'll just erase this. So this W is actually the vector W, so it includes W1, W2, W3, W4. And I am trying to take the derivative with one element of that vector. Do I need to show you how to compute this? Have you seen this before? Okay. Can you tell me, I will show you the derivative with respect to W1. Can you tell me, it will be a product of some terms. Can you tell me what is the last term going to be? Everyone gets this? You remember this from, so only thing which is changing is this guy, right? So this part is exactly what we had derived. And when we had one input, we are just calling it X. Now we have multiple inputs. So it will depend on that particular input, right? Whichever W1 corresponds to. Okay. Now make an interesting observation there. Okay, so, okay, sorry, before that, yeah, this is obvious. If there are endpoints, we'll just take the sum of the gradients with respect to the endpoints. Okay. Now, what happens if the feature X2 is sparse? What do I mean by that? It's mostly 0. Okay, what does that mean? So I'm looking at a lot of movie data. Okay, Amir Khan acts in a very few movies. So if I have a feature which says is actor Amir Khan, then that's going to be 0 for most of the movies in my data set. Right? That's what I mean by sparse. Okay, so if I have 10,000 movies, then probably only 50 of them would have this feature as on. Okay, does that make sense? So it's going to be very sparse. Now, if the feature is sparse, why do we care about it? What will happen? What do we really care about when we are talking about optimization in this course? The gradients, right? That decides how well we move in the plane that we are considering, WB plane or the other, in the n-dimensional region that we care about, okay? So now, if X2 is sparse, what would happen to this? It will be 0 a lot of times because X2 is 0 a lot of times, right? So now, just take a minute to understand this, right? So now remember, let's talk about stochastic gradient descent or mini batch gradient descent, or even batch gradient descent. You're going over all the 10,000 points that you have. You're computing the gradient with respect to all the parameters. One of those parameters happens to be W2, right? You have gone over 10,000 points, but in how many of those you will actually get the gradient for this? Only in the 50 in which X2 was present, right? Everywhere else the gradient would be 0. So that means your sum of the gradients over all the n points is going to be small or big? Small. For this particular feature or for this particular weight, it's going to be small, right? Because you don't have enough samples where you're seeing this. So now, what would happen to the update? You started at a random value for W2, okay? After one epoch or making one entire pass of the data, what would happen to the updates for W2? Very small, very few updates. Compare this to a feature which is dense. It will get a lot of updates. So you see there is something unfair happening here. If a feature is sparse, it's not getting updated enough, right? Now that was okay in one situation if this feature was not really important. Okay, but now consider the exact example which I gave you, which is this an Amir Khan movie or not? Now suppose I'm doing a classification whether this movie is going to be a hit or not. I would believe this feature is very important because almost always when he is the actor, the movie is a hit, right? So you really can't ignore this feature. You want to learn the parameters correctly for this feature. Do you get the setup, right? There could be cases where your feature is very sparse, but at the same time very predictive of the output that you're trying to learn, right? And in this case, the output is whether the movie would be a hit or not. Okay. The other example could be is Christopher Nolan the director? So he has probably directed less than 10 movies, but all of them have been at some point in the IMDb top 250 or something, right? So that's a very important feature, but you will not get it very frequently in your data, right? So you can't really ignore these features. That means you still want to learn these features properly. So you have sparse features, you have dense features. We understand that for the sparse features, the updates would be slower. For the dense features, the update would be faster. Okay, all of us get this? Fine. No, the sparse would be 0 in most cases. No, so you will do this 0 mean thing, right?
Yeah, but I'm saying that.
No, but if it's the same value and you're going to 0 mean the data, right? So the value, even if it's 1, it is going to be very close to 0, right? So you always assume 0 means, otherwise all this does not make sense, right? Because if your features are not in the same range, then anyways you're in trouble, right? Okay, fine. So this is what I was trying to say, that the gradient with respect to W2 is going to be 0 for most inputs, and hence W2 will not get enough updates. And as I said, if this is an important feature, we can't really ignore it. We have to make sure that it learns better. So what is the case that I'm making for? What do we actually need? Can you relate it to the discussion on learning rate that we have been having? So if the feature is sparse, you know it's going to get very fewer updates. So can we change its learning rate so that that feature gets updated a bit faster as compared to the other features? So you get the motivation, right? How to do this is a separate story, but at least we need to do this. Is that clear? How many of you get this? Okay, fine. So the intuition is decay the learning rate for parameters in proportion to their update history. So you have been recording the update history. You have been looking at a parameter. You know all the gradient W2 that you had calculated so far, right? How many times you had computed the gradients and what those values were actually. Now for the sparse features, those are going to be 0. So your accumulated history is going to be small, right? For a dense feature, it's going to be high. So why not make the learning rate inversely proportional to this history? That means if the feature has been updated fewer times, give it a larger learning rate. If it's not updated, if it's updated many times, give it a smaller learning rate. Can you give me a mathematical formula for doing this? This is the intuition. Just think about it for a minute. Learning rate inversely proportional to update history. Okay? Okay, good. How many of you get that? But most of you will get it once I show you the answer. This is my gradient which I had computed so far. I mean at this time step. I'll keep accumulating it in a history vector. Okay? So at time step 0, I'll take the magnitude of this. Again, I'm taking the magnitude, right? Because it doesn't matter whether you made an update in the positive direction or the negative direction. It just matters that whether by how much did you move. So I'll just square this quantity so that I can get rid of the sign. Okay? So I'm taking the magnitudes and I'm storing all that. So at time step t, what would Vt contain? Grad W0 square plus W1 square, grad W1 square and so on up till time step t. Okay? Now, this was my, if I ignore this quantity, this was my normal gradient descent update rule. Okay? Now, do you see what I have done? I have divided the learning rate by whatever history I had accumulated. So for the dense features, what would happen? The learning rate will increase or decrease. With time, the learning rate will decrease, right? And for the sparse features, relatively less, right? And in fact, if you have gotten 0 updates so far, so when you are updating it the first few times, you'll have a very high learning rate. Does that make sense? Right? Because this quantity would be 0, so your eta would actually be very large. Okay? So you see how that intuition got converted into some reasonable formula. Okay? Fine. And now, can you tell me a way of actually realizing this? I want to show you that what happens when you have sparse data. And I want to do this with the toy example that we had, where we had only one feature and the other feature was always on. Right? So how do I create this sparse data? So you should think about these because these are things you'll have to do when you're practicing machine learning, right? So if you're working with the problem and you want to create some simulated data so that you can verify some hypothesis that you have. So how would you do this? Say I'm going to create 1000 data points, right? Which is x comma y points. And of course I have this x0 which is always on, right? So x0 is always on, I can't make that sparse. What about the other feature? If I'm creating 1000 data points, what should I ensure? That 80% of them or some 90% of them is always 0, right? Just as the Amir Khan case, right? That most of the data is going to be 0. So what we'll do is, as I said, we just have two parameters w and b. B we cannot make sparse, it's always going to be on. So what we'll do is, we'll make x sparse. We just create random x comma y pairs, and then for 80% of those, we'll set x to 0, right? So now this x feature is going to be very sparse. Is that fine? So now I have created some data which is sparse, one of the features is sparse, and now I want to see what happens when I run gradient descent, momentum, and Nesterov accelerated gradient descent, and how does the algorithm behave. And now if I apply this algorithm, which I did not name, it's called AdaGrad, okay, this algorithm is called AdaGrad. If I apply this algorithm, then how does the situation change, okay, fine. So this is what gradient descent, momentum, and nag do. Now at least the difference between momentum and nag should be clear. The nag blue curve is inside the red curve, right? So the oscillations are slightly smaller, okay? This is how they behave, okay? Now there is something very interesting that these three algorithms are doing for this particular data set that I have created. Can you spot it? What is the interesting thing happening here? I want you to take some time and think about it. And relate it to the discussion that we just had. How many of you see what is happening here? Okay, very few. I'll give you a hint. Okay. It's almost as if these algorithms went to a school where they did not teach Pythagoras theorem. Now relate it to the discussion that we just had. What is happening initially? So initially what is happening is, you started from here, okay? And this is the w comma b plane. So you have w on the horizontal axis and b on the vertical axis. What is happening to all your updates initially? Where are you moving? You are moving along the b direction. Are you making any movements along the w direction? No. Why? W was sparse, its gradients are mostly 0. It was not being able to make any updates in the w direction. All it was able to do, make updates in the b direction. It did as much as it could do. After reaching here, it realizes that there is no point in going to B further, right? It actually took a U-turn because it realized that there's nothing, I can't really go ahead. I have to now start walking in the direction of W. So now in practice, although in this toy example, it still converges fast. But in practice, what will happen is you have just moved in one direction, reached a point, and now from there, again, you're going to take a right turn and reach to your destination, right? So you're doing something which is not faster. This is not how you would go from this point to this point. There has to be a better way, right? And this is happening because W is not getting updated frequently. All the updates are initially done for B, and now when it's no longer possible to change B because you have reached the optimum value for B, then only you start changing W, and that too very slowly because you'll have to wait for many updates for that to happen. How many of you get this? So this is exactly what's written on the slides. Because in our data, the feature corresponding to W is sparse, and hence W undergoes very few updates. And B is very dense, and it undergoes a lot of updates. Okay. Now, such sparsity is very common in large neural networks, which have thousands of features. Right. So you could imagine this. Now, if I have thousands of features, now suppose I am doing credit card fraud detection. Okay. Now, say one of my features is corresponding to some education that the person had, and suppose he has done some very less sought after degree or less sought after curriculum, right? So that feature is going to be sparse for most of the cases, but I can't ignore it. Maybe this is the most predictive feature that I might have, right? So you could think of various cases where you would have thousands of features, out of which many are going to be off for a given example, right? Everyone sees that this is a real world scenario where a lot of your features are going to be sparse, and in many cases you cannot ignore the sparse features, okay? Fine. Now let's see what AdaGrad does. Any guesses? Okay, good. So I'm running this. You should start seeing something, a green curve starting from here. Okay. Do you see what is happening? Expected. Now try to guess if you are going to run into a problem. I have deliberately halted the algorithm. I just want you to think if you're going to run into a problem. Okay, all of you are thinking of something which makes sense. So now I've run it for, in this case, again this is a toy example, hence you don't see a lot of difference between these algorithms in terms of number of steps taken to converge. But in a real world application it would be very different. But now what has happened is, I've run the algorithm for as much as I can and I've been stuck here. I'm not being able to move forward. Why is this happening? Well, the history is accumulating, it's growing. Now what am I doing to the learning rate? I'm just killing it, right? It's eta by a very large constant now, and that's going to be very, very, very small. So no matter how big my gradient is, it's going to get multiplied by a very small learning rate, and I can't just move any forward anymore, right? So you see that will happen. That's why this, in this case, okay, this is some point here which I don't want to go over now, and it's this, in fact I don't have an explanation for that, but this is one observation which people have made, that remember we had the square root in the denominator. If you remove the square root, in principle you are still doing the same thing, right? You are still making it inversely proportional to the accumulated history, but it doesn't work well when you do that, right? So I don't know why it happens, and I just read these comments at several places that it does not work when you remove the square root from the denominator, but that's not important for this discussion. That's just a point for reference later on, okay? So right now what I'm trying to say is that it did the right thing. It started making updates for W also, and started making larger updates, hence we see this simultaneous movement in both W and B direction. But the flip side is, over a period of time, the effective learning rate for B will decrease so much that we will no longer be able to move in the vertical direction, right? And if you're not being able to move in the vertical direction, will not reach the minima in this particular example. Not always, but in this particular example, you need to move further in the direction of B, but your learning rate is not allowing you to do that, right? So that is what is happening. So now can we avoid this? Yes. How? Multiply by? So first divide it so that it decreases, then multiply it so that it does not decrease. All of these are interesting ideas. I mean, it's very hard for me to say upfront whether this is wrong or right. But yeah, these are, you get the idea basically. Something is happening which is, you are aggressively killing the learning rate. Now we just want to make sure that we are not so aggressive, okay? So what happens because of the aggressive killing is the frequent parameters, they start receiving fewer updates. Now this is what RMS prop does, okay? I want you to stare at this for a minute, okay? Assume that beta is going to be something which is greater than 0.90 or 0.95 or something, and try to make sense of what is happening. Try to imagine what is VT going to look like, okay, in terms of grad W0, grad W1 and so on. So start from V1 and see what happens. What was V1 earlier and what it is going to be now? Okay, but that still grows my magnitude, right? I'm still adding stuff. So how does it help me in not blowing up the denominator? Okay. So yeah, I think most of you get it. So again, this is the trick, is basically you're using this exponential moving average, right? So even at the first step, earlier I was doing grad WT square. Now I'm actually doing 0.05 into grad WT square. Oh sorry, grad W1 square, right? So that's what my V1 is going to be. Now what is my V2 going to be? It's going to be 0.95 into 0.05 grad W1 square plus grad W2 square, right? So this quantity is even shrinking further. And at each step, this is going to keep a 0.05. Okay? And you see now that at each step, this is going to get multiplied by this quantity and shrink further. Okay? So now I'm not aggressively growing the denominator. I'm not considering the full gradient, but only a fraction of it, and in fact, a very small multiple of it. So I'm still accumulating the history, but I'm not being very aggressive while doing that. Right? So you understand this? Everyone gets this? Okay. So now let's see if we run, what would happen. Any guesses? Okay. So initially now, this is I think a brown curve. It's already there, but you can't see it. So I'll keep running it. At some point it will diverge from the green curve. Yeah. Do you see that now? It's reached its destination, right? So at the point where the B learning rate, the learning rate for B was getting killed, in this case that does not happen because you have prevented the denominator from growing very large. You have actually multiplied by its small values so that it does not grow very fast. How many of you get this? Okay. Not as many as I would like. Can you please raise your hands? Okay, some people are just lazy. Fine. So ADA grid got stuck when it was close to convergence because the learning rate was killed and it was no longer able to move in the direction of B. But for RMS prop, it overcomes this problem by not growing the denominator very aggressively. Okay. Now, can you think of any further modifications to this based on everything that you have learned so far? And by everything, yeah, so I'm not very sure why that. I agree that I am also a bit surprised that it completely overlaps with it. I've checked it and that's how it turns out to be. I'm guessing it's an artifact of the artificial data that I've created. So what he's trying to say is actually making sense that it should not overlap so much, right? Initially, it should slightly be biased towards B and then probably, that's what you're trying to say, right? But I don't know, it's just an artifact of this data that I have. But what matters is from the, I was going to say illusion, but from the illustration, is that it actually does not kill the learning rate, okay? Fine. Okay. Yeah. So what is the one idea that, now think of everything that you learned in starting from gradient descent, then you tried to improve it using something, then you try to further improve it and so on. And now you have taken a slight detour from there, you're now focusing on the learning rates, but there were other things which you were doing earlier. Can you bring those back? Add momentum. How many of you say add momentum? As if it's just, I can just add it. No, you're right actually. Okay, so let's see what we can do. So it does everything that RMS prop does. That means it tries to make the learning rate inversely proportional to a sane accumulated history. By sane I mean it does not allow the history to blow up, and it also uses the cumulative history of the gradients. So let's see the update rule for Adam. So what is this term doing actually? It's taking a moving average of the, this is the same as the momentum based rule, right? This is taking a moving average of your gradients, okay? The same analogy that I'm going to Phoenix Market City, I'm just taking all my history into account, okay? And VT is again a cumulative history. This is the same as what was happening in RMS prop, right? Why are you guys lost? Is this fine? Everyone is okay with this? Okay. Now what would the next step be? Can you give me the final update rule? At least think about it. MT into VT, no? Okay, just try to think about it. Right? It's very hard to say it out. There are too many grads and suffixes and so on. So just think about what you did in the momentum case. Okay. So now there's one more step which I'm going to ignore. I'll just say what that step is and then I'll come back to that later on. So this is something known as bias correction. Okay. Just ignore it for the time being. I'll come back to this discussion. Just for the time being, just assume that I'm taking MT and dividing it by some quantity, right? So for all practical purposes, I'm just using MT, just dividing it by a quantity. Okay, just for now, that should suffice. And then my final update rule is going to be this. How many of you expected it to be this, or at least understand that this is fine? Not many. Okay, so let me go over this. What did you expect here? In the normal gradient descent, this should have been grad WT. That means the derivative with respect to current W. Okay. Instead of that, I'm using the accumulated history. Instead of using just this quantity, I'm using the accumulated history. Does it make sense? This is the same as momentum based gradient descent. How many of you get that? Okay. And now this quantity, there is nothing new. This is the same as what RMS prop suggested, that you divide the learning rate by the accumulated history of gradients, right? So it's just a combination of these two. One is take care of the learning rate, the other is use a cumulative history. Does it make sense now? Okay, fine. Now this part is something that I need to tell you about. So I'll tell it to you after I run the algorithm and then I'll come back to that. But is the update rule clear that it's a combination of momentum plus killing the learning rate? Okay, fine. And a similar set of equations for BT. Now let's see what happens to this algorithm is actually called ADAM. It stands for adaptive moments, right? Yeah. What is? Can you tell me why that name? Huh? Why moments? Good. Where is the mean here? Is this a mean? This is a moving exponentially weighted average, right? This is exponentially weighted mean. What about this? What is this quantity if you take the average of this? This is the second moment, right? Exponentially weighted second moment, right? So using the first moment and the second moment to come up with an adaptive learning rate. Okay? Is that fine? Okay. So now I'll run this algorithm. Are you able to see the cyan colored curve? Okay. So it's here. You see that now? Okay. Do you see what happened? Do you see this curve? Everyone sees that? Okay. So what is happening? It's taking U-turns, right? So again, whatever happens because of momentum is happening in this case also. And then finally it will converge. Again, let me be clear that in this, now it should be very clear. We need to change, who is the TA for this slide? So this color needs to be changed, or it should be bright right from the first. So what is happening is it's getting overlaid and then it becomes bright, but we need to have a brighter color right from the beginning. Okay. So yeah, so this again in this toy example, right, you don't really see the speed as such because all of them are converging in almost the same number of steps, but this again I repeat for the toy example, but at least you see that the behavior is very different. And behavior is consistent with whatever you have put into the update rule, right? In one case, the learning rate gets killed. In the second case, it does not decay. And in the third case, when you're using this this momentum term, you again have this behavior similar to the momentum gradient descent where you actually overshoot and then you come back, okay? So is that clear, all these algorithms? Okay. Now, here's the million-dollar question, right? Which of these do you use in practice? So what are the options that you have for your backpropagation assignment? Even if you have not read the assignment, you should just tell me based on whatever you have learned. You have gradient descent, momentum, nag, RMS prop, adagrad, ADAM. Okay, so which of these would you choose? And in fact, there is one now which is called Eve. Okay. But it did not really gain much momentum. But ADAM, okay. So in practice, ADAM seems to be more or less the default choice. I should tell you that recently there was a paper or a couple of papers which actually show that there is a slight error. You could show cases where ADAM will not actually converge as expected, right? But still then after that, as is the case in whole of deep learning research, is that one person says this works and immediately the next day someone else says this does not work, or vice versa, right? So someone showed that this does not work, ADAM does not work in some cases, but then someone else did a detailed study showing that in most practical applications, okay, you have taken a toy data set where you can show some things under some conditions, ADAM will not converge. But if I look at real world data sets like MNIST or ImageNet or something, those conditions don't hold there, and so ADAM really works with. So in practice, ADAM is more or less the standard choice nowadays, at least all the image classification work which deals with convolutional neural networks and so on, that uses ADAM as the optimization algorithm. We have used it largely for a lot of sequence to sequence learning problems, and it works well. Although it is supposed to be robust to the initial learning rate, right? Because you are tampering with the learning rate as you go along, right? You're not sticking to eta, but you're conveniently blowing it up or shrinking it based on your requirement. So it should not be sensitive to the initial learning rate. But we have observed that at least for the sequence generation problems, if you use one of these learning rates as the starting point, they work best. Of course, these are again heuristics, right? Because it also depends on how much data you have and so on. If you're going to train with only 1,000 samples, then first of all, of course, you should question why are you using deep learning. But if you have gone past that question already, as everyone else has, then you would still be using a deep neural network. And in that case, maybe these learning rates are going to be very small. But in general, for a large number of data sets out there on which a lot of academic research happens, which are of a reasonable size, these learning rates happen to work well in practice. Okay. Now, having said that, many papers report that SGD with momentum, either the Nesterov momentum or the vanilla momentum, with a simple annealing learning rate, right? We remember we did this learning rate decay, either a constant decay or that heuristic decay that after you look at the validation loss and then decide whether to decay or not. That also seems to work at par with ADAM, right? So my advice would be that if you really know what you're doing with SGD and momentum, right? That means if you really know how to look at the loss, how to track it, how to adjust the learning rates and so on, with a little bit of manual tampering, it should work as well as ADAM. There are papers which show that it works well as ADAM. But if you're just a practitioner who doesn't really want to bother too much about setting the learning rate, setting the momentum, setting the schedule for both of them. Remember, for momentum also we had a schedule and it was just given by one of these papers, right? And it might differ for your application. You might want to tweak that a bit. So if you're not really bothered about doing all these things, then ADAM would just be overall the best choice, right? With very minimum tempering of the initial learning rate, right? And as I said, some recent work suggested there is a problem with ADAM and it will not converge in some cases. But then that's, it's still, I would say the jury is not out on that yet. Because there is this, of course, theoretical angle to it and also the practical angle to it. In practice, it has been used widely for the last 3 to 4 years at least, and it works well in a large number of applications, right? So, so that's why ADAM would typically be the overall best choice, okay? Now, there's this one thing which I need to do, which is I need to tell you why do we use this bias correction. So now what do you actually want to do? You're taking a mean, okay? You don't want to rely on the current estimate of the gradient, but you want to take a exponentially moving average of the gradients, right? Now, what would you actually, why are you doing all this? What's the intuition behind this? Since you're talking about moments and so on, can you think in terms of probability distributions? So, okay, let me just try to say it this way, right? That your gradients, your values of grad WT, right? And I'll just, I think, alternately use GT instead of grad WT. It just means the gradient at that point. It actually comes from some distribution. Depending on the point at which you are, right, the gradient would change, but it comes from a certain distribution. And now what do you actually want at any time step when you're making this update, this particular update, okay? Is it clear? Yeah. When you're making this update, what would you actually want? It should not move too much away from the, sorry. So now your gradients, how are you computing? Say if you're doing a stochastic version. You're computing it for every point that you have, right? With respect to that point, you would have some loss function and some derivative with respect to your parameters. If you move on to a different point, you will have some different parameters. So there's some randomness in this, okay? So I'm saying that these gradients could be treated as random variables, which can take on values according to a certain distribution, okay? And now what do I mean that, so what would I actually want when I'm making an update? So I have to, the basic choices I could have just used grad WT, right, which is the derivative with respect to the current time step, at the current time step, okay? Instead of that, I know, why am I not happy with that? Because it has this problem that it could pull me to the extremes, right? That this point is actually saying, okay, it changed your W value in a particular way, which is most suited to me. Some other point would say something else. So what we want is that whatever update we make should be very close to the dash of the distribution, mean of the distribution, right? And instead of computing the mean, we are computing a moving average, an exponentially moving average, okay? So now what do we actually want? Say I said that GT is the random variable for the for denoting the gradient, okay? What do I actually want? I want the expected value of MT should be equal to what? The true expected value of GT. This is what I want, because I don't want my updates to move in the extremes. It should be closer to the average, to the mean of the distribution. Do you agree that this is my wish list? This is something that I should desire for, okay? Now let's see what is mt actually if I want to write it as a formula. So I have mt is equal to 1 minus beta, no, I'll call this as gt, right? So remember that gt is grad of wt, okay? So now let's try to write a formula for this. So m0, I'll set it to 0. So m1 is going to be 1 minus beta into g1, okay? m2 is going to be beta into 1 minus beta into g1 plus 1 minus beta into g2, and m3 is going to be beta into 1 minus beta square g1 plus beta into 1 minus, sorry, beta square minus beta, wait, is the first term correct? No. Beta? Okay, so wait, what am I, oh, beta is getting multiplied, okay. To G2 plus 1 minus beta into G3. So what is the general formula going to be? MT is equal to, so 1 minus beta can come out, okay. Summation I is equal to 1 to T 1 minus beta, oh god, sorry, beta raised to T minus I and GI, right? Okay. So this is what my MT is. Okay. Now let me take the expectation of this. Okay. This is fine. Now, okay, this should be 1 minus beta. So now this is going to be is that fine? Okay. Okay, okay. So what is this? It's an AP, GP, GP. What's the sum going to be? It's going to be 1 over 1 minus, no, it's actually, no, sorry, 1 minus beta raised to T over 1 minus beta. Is that fine? Okay. So what will happen? This will get cancelled, and what you are left with is 1 minus beta raised to T into E of GT. Okay. So what is the relation that you have? E of MT okay, E of MT is equal to 1 minus beta raised to T into E of GT. What did you actually want? Right, so now how will you ensure that? Divide MT by 1 minus beta raised to T, and that's exactly the bias correction that we had done. Okay, sorry about this messy derivation, but I guess most of you get it. If not, we'll just type it properly and upload it in the slides. How many of you got this? Okay, most of you got it. Fine. So that's, and the similar derivation for VT also. Okay, fine. So that's why we need the bias correction.